How are you?
Good. It's a little bit sparse, as you can imagine, the last day of the lecture this morning. We'll give you a little bit of time.
Yeah.
I'm also going to announce the final results.
Yeah, it's about 2 gigabytes of photos from yesterday on it. But don't worry, I made a backup on it also. Yeah, that's why I went in for If it shows like 2.5 to 3 hours, then it shows like
Yeah, I don't. So it's, I'm not sure if. Yeah, I'm not onto the banquet as much as just.
that would mean it's.
So I don't know. A lot of people have already left.
Yeah. You don't want to do it.
I hope not.
You need to reject.
Yeah, I'm going to reject it. Just repeat.
Let me check. Check the server? Yeah. All the definitely focus. I don't think it makes much, but I have to go. You break my clock.
This year's
Oh, okay, no. Yes. Good. This was the wrong. Oh, just keep it. Oh.
very simple. Alex, do you happen to have your adapter?
Should be actually on
Oh,
the
there it is. Let's go with that.
left hand. Actually, thanks for the delay because we just need to.
Yeah, we don't have to start recording.
Yeah, we just need to recalibrate a few things about the camera. You can you do sound check?
Oh, are you on?
Well, this is a bad idea to run the table around here because we gave it a lot of conductive. See, what it does is basically expand this machine to verify transformer.
This one's recording.
The one the red one.
Yeah, no, it's basically, you're taking the
One of the NES one, wrapping paper, AC current around it. That basically maximizes the interference.
But also, I think it's dishwasher plate.
So actually,
I had a really nice one from Princeton.
can you do the sound check now? Or
He's putting on the mic now.
I'll show you.
See the volume here.
Okay, can you just speak more? Yeah, actually, I think the gain is a little bit high on the amplification. Do you mind turning down the
This one?
big volume?
This one I can put it down.
It's the gain is actually.
Oh, the gain.
It's the gain. Try
Hello?
to.
Yes, yes. Better now? Hello? Yes?
Yeah, so that should work.
last morning.
It's
not recorded.
This is getting win, G it's like
Okay.
All right. Well, we don't have to record this. It's just me talking about the leaderboard. Hello, everyone. Those that are here, thanks for coming here. I know it's the last morning before you go, so it's the morning after the banquet. So there's two factors working against coming here. Thank you all for being here. I just wanted to point out or not to point out, but to highlight the winners of the contest. I think it is officially over now. You can't submit anymore. This is the final ranking. Is anyone from the top 3 here? All right. Oh, all 3. All right. Well, then let's actually come down and do these. We've been waiting to give you extra goodie bags. Not that you really need these, but if you want them, you're welcome to come down. So,
well, actually, we can have Xavier hand it out, and it's the Netflix prize, right?
The Netflix prize. You can stay. So how about let's first have I can butcher these names. I apologize. Wei Ling, third place. Round of applause. Right now, if you want it. Okay, let's have Jin Seok. That has been and Wang Jing, who has won I think was on the leaderboard every single day of the contest. So let's see all right. Well, thank you for those that participated. Hopefully, you learned something and it was fun. We'll switch over to the actual content now.
Okay, so welcome back. Again, thanks for those of you that could make it. I'm hoping that people start replaying during the rest of the session. But today I'm going to move on to the second part of the talk, in which I'm going to be talking about more novel stuff. Not that I didn't talk about novel stuff before, because we were talking about methods that haven't been around very long, like using RVMs, for example, for collaborative filtering. But today I'm going to be talking about those things that are probably not that well known, or so those things that people, when we talk about recommendations and personalization, don't immediately think about. And the first topic I'm going to be starting with is, for me, one of the most important ones, which is learning to rank. So if you think about it, the final goal of most recommendations is to produce a ranking, right? And you could think of the recommendation problems as that one of ranking. You have a set of possible items in a collection that you want to present to the user, and you have to come with an ordered list or a ranking of those items. So we already talked about yesterday, popularity is the obvious baseline. And then anything that you can add on top of that, for example, ratings, can be thought as a secondary input that you can input to the ranking function in order to make it personalized. And of course, you can add as many features as you want to personalize that ranking. So if we think about, let's have a rating prediction algorithm like the ones we were talking about before related to the Netflix prize, and let's rank things by rating, sorry. That's an obvious thing you can do, right? You just predict the rating, and then you rank your items from the highest rating to the lowest rating. Actually, that's what we would have done in the Netflix prize situation, right? So what happens in this case is that you might end up coming up with rankings like this, in which very niche titles, like this anime title, which might be an awesome title, I don't know it, has a very high predicted rating. And this happens many times with very niche titles, or titles that have a very sort of devout and strong audience that likes them a lot. And then, of course, all the ratings we have are very positive. So even these two titles might not be very popular, they might come up with a very high predicted rating. And if we rank by rating, we come up with situations like this. On the other hand, if you remember the Netflix prize, we were optimizing for the root mean square error. Root mean square error is not a ranking metric. So it's not necessarily a metric we want to optimize when we're optimizing for a ranking, right? So among other things, RMSE is going to weigh exactly the same an error that we make on a high rating than an error we make on a low rating. However, on the low ratings, if we're using for ranking, they're going to come very down the tail of the ranking, and therefore are less important. This is just one example of something that tells you why a metric like RMSE might not be an ideal ranking metric. So whenever I talk about learning to rank or personalized learning to rank, I like to put this picture. I think it illustrates exactly the point of what you want to do. So let's imagine we've been talking about these two concepts, which are popularity and predicted rating. Let's think about coming up with our first learning to rank approach on a two-dimensional space, right? So the idea here is we have two features, or two dimensions, which are popularity of the items and the predicted rating. And of course, the predicted rating is the predicted rating for a given user, right? So that's going to be personalized. So we have a set of items here in our collection, and we put them somewhere in the space. So this means, of course, this item is more popular than this one, and this one has a higher predicted rating than this one, right? So the first thing we can try to do is say, hey, let's try to come up with a linear model, because, of course, whenever we don't know what to do, it's better to go for a linear model. That's the easiest thing we'll get started with. And that linear model is going to combine the two features that we have, the popularity of the video and the predicted rating of the user and the video, in a linear function. And of course, we're going to have some coefficients here, W1, W2, that are going to be determining the slope of the line in this space, right, of the linear model, this line over here. So we project those items into this linear model, and we produce the final ranking. This seems a very simple idea, and it's very simple, but it's very powerful. This is giving you the initial thought on how to come up with your first personalized learning to rank approach, in which you're using two different features. One that is unpersonalized, which is your popularity, and the other one that is personalized, which is your predicted rating for a given user. Okay? Of course, one thing that I didn't talk about, and that's going to be what I'm going to be talking in the next slides, is how do you learn this model? And if you are going to learn a linear model, you have two parameters here, which are the W1, W2, which is going to be determining the weight that you give to each of the two features in your model. That's the real question here. Is it more important to rank popular items first? Is it more important to give more weight to the predicted rating? And that's something that there's only one way you can answer, and it's with data, right? So we're going to be using the data to fit this model, to fit the model parameters. There's another way you can do it, also with data, but that's going to take a lot more time, which is actually asking your users, right? So that's something that people and companies will do, right? It's like, well, I don't exactly know what to put here, so let me start doing A/B tests and putting different versions of this linear model in front of the user to try to determine what these parameters are by looking what works best. That's a possibility, but it requires time and it's a little bit clumsy. You can do this much better with historical data and optimizing your model and the parameters, feeding them to the data. Any question about this? No? So again, we've come from the idea of predicting a rating and the thought, which was initially in the Netflix prize, that, well, we'll use the rating prediction to produce a final ranking to say, well, rating by itself is not probably good enough, and we might want to throw in the baseline, which is the popularity, and come up with a two-dimensional model, and then fit the model parameters to the data that we have. Okay, so learning to rank is a machine learning problem, and where the goal is to construct a ranking model from training data, a ranking model like the one that I just showed you was a linear model. And we obviously can produce a ranking model by producing a score, which is a number, and then rank the items according to that score. So that's typical. And one initial way and easiest way to treat the learning to rank problem is to treat it as a supervised classification problem. And actually, I'll talk about that in a second. The other important thing to understand when you're doing a ranking problem is what is the metric that you want to optimize for. I said before, RMSE is not a good ranking metric. It's not even a ranking metric, right? So we can think about optimizing other metrics like NDCG, mean reciprocal rank, fraction of concordant pairs. Each of these metrics has a different set of properties, and all of them are interesting and good, and you can actually measure your ranking model using all of them. And when I say they have different properties, we usually are interested in how much are they weighting the head of the ranking versus the tail, or what kind of decay do they have in the way they weight the errors you make on the head of the ranking versus the ones you have on the tail. And you can think about, of course, making a mistake on the first position, it's huge, right? So you want to make sure that your ranking metric weights more an error on the first position than an error on the 10th position of the ranking. Now, how much more? That's going to be determined by the ranking metric you use. So, for example, fraction of concordant pairs FCP is out of the three the flattest one. The other two are kind of heavy on the head. Okay. If we knew how to, and we will get there, we would want to optimize a machine learning model directly to one of these metrics. But these metrics are hard to optimize for, and one of the reasons is that they're not differentiable. So if you have a method that is going to be using something like gradient descent, you're kind of stuck with something that is not differentiable. We'll find ways of doing it, but initially it's not obvious how to do it. So what are the different approaches to learning to rank? The first, easiest one, I already mentioned it, is to treat it as a regular supervised classification problem. And that's really what's called the point-wise approach to learning to rank, right? So in this case, you basically only need binary judgments on your items, good or bad, right? You just have a class label, and then you use some kind of classification approach. And in theory, you can use any classification approach, as I say here. You're better off if you use a classifier that outputs some sort of probability, like logistic regression. Tree ensembles, like gradient boosted decision trees, are also very commonly used. SVMs not so much, because it's not so obvious how to go from the classification of the SVM to the ranking score. But in any case, you can use any classifier as the first approach to a ranker. Any questions to hear? Yes.
If you consider personalization in your supervised learning, what is the true order in your training data set?
What is your true order?
Yeah. How like if you consider personalization, what is the person's like true order?
I mean, there is so that's so it's a good question in the sense that usually when you talk about learning to rank in an unpersonalized fashion, when you're doing, for example, search, you construct a ground truth data set, and I think that's what you're referring to, in which you have maybe a panel of experts or people telling you, oh, this is relevant for this query, this is not relevant for this query, right? So in this case, you don't really need such a thing in the sense that you don't have a query. The query, you can think about it is a user, right? So basically what you're going to be doing is you're going to be constructing a data set in which you have, for this point-wise approach, for example, you're going to have positives and negatives from a given user, and then you're going to have a value for the feature in your model, in our case, popularity and predictive rating, and that's it, right? So basically, think about the matrix of data that you're going to be constructing is basically zeros or ones, whether the user clicked or didn't click on that item, and then the values of the features, which represent the predictive rating for that user, and that's where the personalization comes in, right? So there's not a ground truth data set in the sense that it's equal for everybody. There's a ground truth data set in the sense that you have positives and negatives for each individual user. But those positives and negatives are going to be different for each user, but that's okay, because that's going to be reflected in the fact that the personalized feature, the predicted rating, is going to be different for each user, right? Okay, so moving on from the point-wise approach, we go to pairwise, and pairwise, the idea here is that we're going to be defining the loss function on pairwise preferences. So basically, our goal here is we want to minimize the inversions that we have in our ranking. So we're going to be training models in which we say, well, item A has to be better than item B. And we're going to be optimizing using, again, a binary classification problem, but in this case, optimizing to a pairwise comparison. There are a number of approaches here, and one of them is the ranking version of SVM, rank SVM, rank boost, rank net, FRank. All of these are pairwise approaches to learning to rank. However, this is not ultimately what we want to do. Sorry. So that's not ultimately what we want to do. I mean, pairwise is a good step forward, but what we really want to do is to do a list-wise optimization. List-wise meaning we want to have the whole catalog of items, and we want to optimize whatever metric we chose, NDCG, fractional concordant pairs, for the whole list. Right? There are different ways to go about it. And the first way is saying, well, given that optimizing those ranking metrics, as we said before, is tough because they're non-differentiable, let's come up with an indirect loss function, right? So, for example, rank cosine uses the similarity between the ranking list and the ground truth as the loss function. And that's indirectly, obviously, related to some of the ranking functions. Or ListNet uses KL divergence in a similar way. And these methods are okay. The only issue, the only problem is that you're not guaranteed that this indirect loss function that you're optimizing is at the same time optimizing your ranking metric. Right? But again, it's difficult to optimize directly the other metrics. Okay. So how can we directly optimize those? When I say IR, I mean those ranking measures. So there are actually some smarter papers out there which do, by the way, all of these are going to be in the references at the end of the slides. They do things like using genetic programming or simulated annealing to just like almost do a brute force approach to optimizing those ranking metrics. And more recently, there's been other approaches that are going around the problem in a different way. And one of them is trying to come up with a smooth version of the objective function. And there's a couple of papers starting in 2012. They're actually by the same authors, and they've come up with different ways to smooth different versions of CLIMF or CLIMF. That was optimizing for mean reciprocal rank, and then TF-MAP was optimizing for mean average precision, which is another ranking metric. So they've come up with definitions, smooth definitions, so smooth meaning differentiable definitions of the ranking metrics, and then added them to different methods like matrix factorization. In a similar way, SVM-MAP does a similar thing and relaxes some of the constraints of the mean average precision metric, and for this particular metric, adds them to the SVM constraints. And add rank uses boosting to optimize NDCG, right? So here, in this last method, you basically have to be a little bit smarter about how to optimize for one particular metric, how to either relax it, smooth it, or add it to the constraints of the method that you're optimizing for. But it's possible to do. And again, this would be, in some sense, the preferred way, because here you're, on the one hand, optimizing for your whole list. On the other hand, you're optimizing for the metric that you want to optimize. Okay. Yeah, there's another one I forgot to add here. There's an interesting one was presented in KDD last year, which is called direct rank, which I would also recommend if you're interested in list-wise approaches. And what else? I think all of the others I already mentioned. So any question about this idea of learning to rank? And again, remember back to how I started with this two-dimensional space, popularity and predicted rating, and this linear model, which we needed to estimate the weights. And we do that by fitting the parameters to some of the data. And in order to fit them to the data, we need to figure out how to do that. We can go from the easiest approach, which is use a classifier, which is the point-wise, to more advanced methods like pair-wise or list-wise approaches to learning to rank. Okay. And now we've added a step forward from where we were yesterday, where all, quote-unquote, all we were doing is predicting the rating using some of those methods. Now, we've done a second step, predicted the rating, and we've added another feature, which is the popularity, and we've optimized a ranking model to it. Okay? Yes?
Is there any ranking method that works better than the others? Or, I mean, if I were
build a system, which one of these should they try at all?
Yeah, I mean it's a fair question. I don't have a good answer for you because it's really dependent on the kind of data that you have. Many things related to the distribution of your data, and not only your data points or your labels, but actually your feature space, right? This is like, if you ask me, what's the best classifier? Well, it depends, right? It depends on dimensionality of your feature space. It depends on the kind of features you have and their distribution and many other things, right? What I would say, which is what I always say, is start with the simplest and only make things complicated if they're really worth it, right? So the idea, some of these methods are interesting and fun, but they're very costly, right? Think about simulated annealing and so on, right? So if you're really going down that path, you really need to make sure that you're getting something out of it. Okay, so in the next part, I'm going to be talking about context-aware recommendations. Now, we're moving a step beyond in our quest for more dimensions, right? We started with having a prediction problem, which was the rating. We added popularity and we turned it into a two-dimensional, or by the way, n-dimensional, right? Because I said we added two features, but you can think about adding absolutely any feature into your learning to rank approach, including content-based features. So you can use it as a method to hybridize and add different things, right? But now we're going beyond that, and we're going to be throwing in context into the equation. So what I think it's pretty obvious that context is going to be, or it's an important part of a recommendation or a personalization. The idea here is that the user, depending on outside conditions like the location, the weather, or the time, is going to have different preferences, and those are going to influence whatever we want to recommend. We usually talk about three different kinds of context-aware recommendations: pre-filtering, post-filtering, and contextual modeling. And pre-filtering and post-filtering are pretty simple. This is illustrated here in this diagram. So in pre-filtering, basically you add your context as a filter to your input data. Then you build your recommendation model, and you continue as if it was a regular two-dimensional recommendation problem. In contextual post-filtering, you do it the other way around. So you build your model and you operate on all your data that includes all the context. And then when you're going to do the recommendation at the end, you do the filtering step and you remove those things that don't make sense for a given context. So the idea here is basically you build your recommendation on everything, and then you say, well, if it's midnight, now all those other things that seem to be more appropriate for morning, I'll just remove them, or I'll re-rank them using that feature. Those two are okay, and I think they're pretty obvious. That the most interesting one is how do we do contextual modeling, right? So how do we throw in context into the model itself? And that's basically what I'm going to skip through this because, again, it's pretty obvious how you do pre-filtering and post-filtering. And I'm going to go basically directly to the contextual modeling. So in contextual modeling, what we want to do is use the contextual information directly on the model. And the obvious challenge here is that now what has traditionally been a two-dimensional problem, where we have users and items, becomes a multi-dimensional problem. Now we have users, items, and time of the day, or day of the week, or weather, or location. And those are all dimensions that we add to our multidimensional problem. So we can have things like user, movie, which are the 2 dimensions, and then time, company, place, and so on. So this 2-dimensional problem we have has now become an n-dimensional problem. There's an obvious side effect of this, which is if we were worried about sparsity before, now we have an even worse problem, right? Because we have sparsity on this 2-dimensional problem, but now if we add more dimensions, we're going to be even having more sparsity because we have few ratings, few users rating a given movie, let alone users rating a given movie in a particular day of the week, in a particular location, right, and with a particular weather. That's going to be very, very sparse. Okay, so how do we deal with this? And there are different ways. I'm going to talk about 2 of them. One of them is actually comes from a paper that I published on tensor factorization, and the other one is going to be factorization machines. So one of the clear and obvious things that we need to do is we need to reduce the dimensionality of our problem. There's really very hard. There's no way that we can address this problem directly with the kind of sparsity and dimensionality that we have, right? So one thing we can think about is, well, let's try to factorize, just as we did with matrix factorization. And this leads us to the idea of tensor factorization. So in the case of matrix factorization, we had a 2-dimensional matrix that we wanted to represent as a combination of 2 different matrices, the user factors and the item factors, and we had the diagonal matrix in the middle. Now what we have is this, which is a tensor, right? And I'm going to be representing always a tensor as a 3-dimensional, so as a cube. This is really not a cube, right? This is an n-dimensional tensor with context being many different dimensions. So what we want to do is something like this. So we want to decompose, and this is what's called a higher order singular value decomposition. So we want to decompose this cube into a number of different 2-dimensional matrices, and one of them is going to be the item matrix that we had before, the user matrix, and we have another one here, which is the context. And then we're going to have a tensor here in the middle, which is going to have the dimensionality of the 3 other matrices. And this is the basic idea, same idea as we did before with matrix factorization, but extrapolated to the idea of tensors and n-dimensions. So here I'm going to introduce some notation that I think should be probably, or I thought that it could be well known because you already talked about matrix factorization again with Deepak. I know I skipped through most of this yesterday when I was talking about matrix factorization. Then when I was talking after the class with some of you, I wasn't sure it was clear, but the basic idea is that when you're, even in a 2-dimensional problem, when you are trying to find or to estimate these matrices, or in the case of the 2-dimensional problem, the user and the item matrix, you formulate this as a traditional sort of like regression problem where you're going to have a loss function and some regularization, right? And the key issue here in the tensor factorization case is that you have a loss function here, and then you're adding 2 regularizations, and 2 regularizations, one of them is on things that you really care, which are the 3 matrices, the M, the U, and the C, and another one on the central tensor, which is the S. And basically, this is going to be a convex function that you are going to optimize using some gradient descent technique or any other method. But the idea is what do you put here? What is your loss function and what is your regularization? And this is really the same thing as what you would do in the matrix factorization case, right? When you are estimating the matrix factorization and the quote-unquote SVD, you're not really computing the closed form SVD. You're doing something like this. You're also having loss function and some regularization, and you're using some iterative optimization method to optimize this function for a given method. So in our case, the regularization, regularization that we're going to be using is an L2 regularization, both for the S and for the F here is this one here. So it's an L2 regularization for both the F, which includes the three matrices that we care about, the M, the U, and the C, and for the S. And for the loss function, we can do different things, but what we did in this paper is we use simple square error loss function. So basically, we're optimizing the loss function, which is the 1/2 of the F minus the value that we have, the data squared. So, so the idea here is you have some data points, you're optimizing to the error between the F and you're computing the F just as we were doing yesterday when I was saying how do you compute the ratings giving matrix factorization approach. So basically this is going to be the dot product of the user and the item. In this case we have the context also, but it's the same. And you subtract the data point that you have, you square, this is going to be your loss function, you add your regularization terms here, and you optimize from there. So basically the loss over all users and all items is going to be just the sum of the loss of each of the items that you have. Any questions?
Your number of regularization parameters is grows linearly with the marginality, right?
Yeah.
How do you tune them? Do they have a special procedure?
It's a good question, and in this particular case, the only way you have to tune them is to basically, as you usually tune hyperparameters, doing a hyperparameter search on your space. And if you have many dimensions, that's going to be costly. Mm-hmm. You have ways of, and we'll get to there when I talk about factorization machines, of using other approaches like MCMC, where you can the number of hyperparameters. But in this case, you will have to determine your regularization parameters for all the dimensions you keep adding in your context. Yeah. But I mean, this is it's a typical limitation on any method that you add some dimension that you need to come up with a hyperparameter for, right? Okay, so you could also use the absolute error loss function. We use the square one, and you basically, well, this is how you derive the partial gradients with respect to each of the matrices that you have. So this is not, and then you actually have yet another hyperparameter, which is a learning rate that you need to determine here. And well, not to mention, you even have another one that I didn't mention, but that's typical in matrix factorization, which is the number of latent factors that you want to use, right? But that's usually doesn't change so much, interestingly. Okay, so I'm gonna show you some results now, but is there any question on how tensor factorization works? So it's really the same idea as in matrix factorization, but extrapolating that to an n-dimensional space. So in this case, we were computing the mean average error. We used 3 different data sets. There's not too many data sets out there that add context to it, right? So it's not as easy. You can't really do this on the Netflix data set because you don't have context to add. But there are some here that do have, like the Yahoo or the food. They have 2 dimensionals, and the Adoma Vicious one has 5 dimensions. But they're very small in this case. Okay, and we compared to a couple of different methods. Now, I think that the key point what I want to show here, the reason I added this slide, is we did find that the mean average error when we were using context in all our data sets was lower, right? And that's a pretty strong and key finding, right? It's like, really, if you have context and you can use it, you are going to get better results. And I think that's, for me, one of the sort of like highlights and why I wanted to show this. The idea is, I mean, it's not obvious, right? Because again, if you're using the context, you are adding sparsity, so it could end up being worse. But it turns out that at least using this approach, if you use context, you have significant reduction in the error. So you are improving things. And now, yeah, this one is not so important. This is comparing to other context-aware methods like pre-filtering and so on. And it shows that it's also better. But I think the key issue is that it's good to use the context if you have it. Okay, I'm going to skip through all this slides, but the idea here, key idea that I wanted to show is this one, right? If you don't use context, you're much worse off than if you use context. And most of the other methods do the same thing. They work better than context. And our approach using tensor factorization worked even better than the ones that were out there in the literature. Okay, so this conclusion here is going to lead me to the next topic. So context matters. Tensor factorization offers an easy way. Oh, yeah.
Sorry, because before you go to the next topic, have you compared with other methods of tensor factorization? Because there are more types of tensor factorization, like the one that keeps orthogonal factors, for example. Would there be any benefit of using other?
So this paper came out 6 years ago, I think. So at that time, it was the only tensor factorization approach that at least had been applied to this particular application. So we didn't compare to any other tensor factorization approach. I don't have an answer for that. My answer would be this one here, which is there might be some better tensor factorization approaches, but if I had to bet, I would say, well, why not go for factorization machines? Which I think, in the general case, I would say they probably beat the tensor factorization approaches in most practical applications. But there could be other tensor factorization approaches where you can beat what we were doing. I think that the interesting thing about tensor factorization, though, is that it's a framework that is very similar to the matrix factorization one, and it's easy to understand. If you understand matrix factorization, you understand tensor factorization, and the way you optimize it is very similar. Okay, so factorization machines. So factorization machines were introduced by Stefan Rendel in 2010. And I know we have a student from Stefan Rendel, right? There he is. So Stefan was a university in Germany. What was the university? Constant, yeah. And now he's at Google. And factorization machines became kind of popular. I mean, they did become popular in a small community, but they became popular not only because of the papers, but also because Stefan used them in a couple of the Kaggle competitions, and he won one of them, and he was second in a couple, and it was kind of like known in the community that, hey, this guy on his own and using a method that seems a little bit exotic managed to beat a bunch of other people. So obviously I don't have time. It would take me like an hour to go into the details of factorization machines, but I thought it was important to highlight their usage as a novel method. And I put them in this part of the contextual recommendations because they can be used as a way to do contextual recommendations, but not necessarily. It can be used in the general framework of recommendations without having context. So the basic idea and the way that Stefan explained this is we need, or we would like to have a generalization of regularized matrix or tensor factorization that we would be able to combine with the traditional regression or machine learning approach, right? Because the problem is every time we need to think about a new dimensionality or a new problem that requires of a new dimension to add to our problem, we need to come up with a new learning algorithm. And I kind of simplify things in the case of the tensor factorization approach, and I was using discrete variables. But what if you have continuous variables? And what if you have different kinds of variables? And that kind of messes, gets things a little bit messy, and you need to think about how to optimize for each time you add something new to your problem. Wouldn't it be nice if we had an approach like regression, where you basically throw in features, and you optimize, you have your regularization, and you don't need to worry so much about the model, because the model is always the same, is a regression, and all you need to do is throw in different features. So we would like to combine both things, the power of sort of standard regression and the power of factorizing, because we don't want to do a regression on the original dimensionality of the problem, because it's usually huge and sparse, and we want to be able to reduce dimensionality at the same time that we do our regression. So what we are going to do is treat the input as a real valid feature vector, and then we're going to model linear and pairwise interaction between variables of whatever number of features that we have. So basically the idea here is, and that's the easiest way to understand, we're going to build a polynomial regression, right? So this is not going to be a linear regression, it's going to be a polynomial regression where we're going to have all the possible different interactions between the k features, right? I'll show the formula in a minute. Now, of course, that doesn't work. I mean, polynomial regression doesn't work for a simple reason. Is because you don't have enough data to fit all the parameters that you have in your model to all the different interactions that your features are going to have. So, and that's when factorization comes in. What we need to do is reduce the dimensionality of the space. And how do we do that? Well, using the traditional matrix factorization approach. So we're going to do a polynomial regression, and we're going to factorize the interaction between the features in order to reduce the dimensionality of the problem. And that's the key idea of factorization machines. Polynomial regression in which we factorize the interaction between variables in order to reduce the problem. And in this way, we combine both things, right? The generality of machine learning or regression with the quality of factorization models, especially in high-dimensional sparse problems. So this is how it looks like. So if we have for a number of features that we're going to have D features, right? These are going to be, if we had only this thing here, we would be combining them in a linear regression. But we're adding this term here, which we are adding all the possible interactions between the different features, right? So here we're going to have the XY, XJ feature. And then the key thing here is that we're going to factorize their interaction. So instead of having one single weight for each of these pairs of interactions, we're going to be factorizing this term. And basically, we're going to be optimizing for this other function here where we're minimizing for the error between these two. And we're reducing the order of the problem from a d-squared problem, where we would have all the different pairs of variables interacting, to an order k times d, where d is the original dimensionality, the number of variables that we have, and k is the factors that we decide to factorize to. Okay, so here we're summing this from 1 to k, and we're optimizing this term over here. So basically, this is think about this as a matrix factorization of k dimensions over the interactions between the different variables, different d variables that we have. Okay. So now the interesting thing about this approach and the way that sort of Stefan likes to sell the model is that it's really a generalization over any of the other models that are known, including matrix factorization, tensor factorization, and so on, right? Because depending on how you model your feature space and you apply it to the definition of factorization machines, you're going to come up exactly with the definition of this subclass of problems, right? So basically, if you only have two categorical variables, U and I, right? So this is user and item, and you encode it like this with an indicator variable where you have the user, right? So this is basically for user 1. These are the movies that the user 1 watched, right? So if you encode it like this and you apply the factorization machine formula, you basically come up with the conclusion that this is exactly the same thing as you would do in a matrix factorization. This is a matrix factorization term plus the biases. And the biases, as we saw when I was talking about SVD++, we also apply them when we're doing it the regular matrix factorization approach, right? So you have this basically becomes the traditional matrix factorization approach. If you add, but you can add very simply another term here, which is going to be time, right? So now we have two categorical variables, the user and the item, and we have a continuous variable here, which is time. I don't remember how it was, so exactly how it was converted. I think it was from 0 to 1, meaning 0 meaning midnight, and 1 meaning 20 the next day, right? At 12 p.m. So 12 a.m. Sorry. So basically, but it doesn't matter. The thing is, if you want to add a contextual variable that is continuous, you just plug it in to your model. You add it here like another variable, and you come up with an equivalent equation which turned out to be one way that in another paper they were trying to do contextual recommendations using time in a continuous manner. Right? And in the same way, you can derive from factorization machines the same approach that you could do with tensor factorizations and so on. So you could see even the approach that I was mentioning before in tensor factorizations as a subclass of problems that you can address with factorization machines. Because at the end, it all comes down to building a regression with different terms, and those terms come from the way that you define your problem and you plug it in as you would in a regular regression problem. So there's different papers and different ways to train the factorization machines. So initially, the first papers that Stefan published, he was using stochastic gradient descent or ALS, and one of the problems there is the number of hyperparameters and how do you tune those hyperparameters. That became kind of tricky, right? Because although all the other things are easy to encode into your problem as a regularization, you need to come up with a way to optimize all those hyperparameters, and it's not easy. So basically, he later introduced a way to do MCMC with Gibbs sampling and reduce the number of hyperparameters. And I know for a fact that that's the preferred approach now, to use MCMC for training the factorization machines. And in this case, you can avoid a number of hyperparameters. So, by the way, the learning parameters that you have if you don't use MCMC are the number of factors, which is, as always, the number of iterations, the initialization scale, the regularization if you do SGD and ALS, and you have multiple regularization parameters, just as you did with tensor factorization, and the step size. So you have to you have a hyperparameter search space which can be pretty big. But if you use MCMC, you remove the need to set all of these hyperparameters. Okay. So, any questions about in general and tensor factorization and factorization machines? I of course, because I'm giving sort of like a very broad overview of all these different methods, and I'm not going deeply into any of them, but I think I'm giving you some interesting pointers of things that if you're interested in any of these topics, you should definitely go and read more about them. There are a bunch of papers on factorization machines, and there's a tutorial in KDD, I think, yeah, in 2012 that Stefan did, where you can also find a long version of what I just explained about factorization machines. And he also talks about tensor factorization in that tutorial. Okay, so other novel approaches. Deep learning. I know you had Nando here, right, the first week talking about deep learning, and everybody's talking about deep learning, so I need to talk about deep learning. And we use deep learning in recommendations. It's pretty new, and there are not many examples, and not many public examples. So what I'm going to be describing here are the only two public examples that I know of using deep learning or new generation neural networks for recommendations. One of them is by the guys at Spotify. I already mentioned Eric yesterday, and he actually published this 2 weeks ago in a blog post. So I got it from him. The other one is about us at Netflix using a different approach, an approach that I can't say too much about, unfortunately. So I'm just going to be glossing over what we do in the infrastructure side. But I'll give you some interesting ideas of how you can use this new generation neural nets and deep learning in recommendation. Okay, so this is the post that I was referring to. So Eric posted a couple of weeks ago how they're using recurrent networks for playlist prediction. And playlist prediction is a very important problem for music. Think about Pandora, that's all they do, but that's their business, right? And Spotify have a similar model where basically the idea is it's important to predict the sequence of the things you're going to be listening to, right? It's not only about, this is one recommendation problem that is different from the ranking problem, right? This is not about giving you a list of ranked things and you choose the top ones. This is about giving you a sequence of things to do. And if you're listening to this thing, what should be the next one? By the way, we also have that recommendation problem on the movie space, but it's not so obvious. So anyway, they thought about this idea, or he thought about this idea of modeling this as a recurrent neural net problem, where you basically see the sequence of your observations here, which is the things that you're observing, and you have some hidden, and you have relations between your hidden and your visibles and between the hiddens themselves. And this can be modeled as a recurrent neural net. So there are a number of assumptions that they make in order to make this feasible to compute, and those assumptions not necessarily. I mean, you don't need to believe them from the get-go, right? Because the assumption of the normal distribution, right? Okay, but it turns out that according to what they're saying, the final model worked and worked pretty well. So it means that those assumptions were okay to start with. So the assumption is that the probability of one of the visibles given the hidden is a normal distribution, and then the log likelihood, and therefore the log likelihood of the loss is just the L2 loss, right? The negative of the square of the difference. And then they also go into specifying the activation function of the hidden, and it's going to be a function of the obviously of the activation of the hidden I plus 1 going to be a function of the previous hidden and the previous visible. And the model is completely specified, and you have 3 k² parameters. So basically what you need to do is to find the u and the v that you have here in this activation function, and the w, which are the weights that maximize the log likelihood over all the examples. And you can do that using back propagation as you would do to optimize any neural net, basically by optimizing the log likelihood over all the examples using the square loss. So that's the training part, and then in order to do the prediction, they choose the probability of the visible given the hidden using, well, first they use softmax for this distribution, which leads you to this formula for the probability of the visible given the hidden, and there's a basic problem which has already been solved in the literature with this, which is that this is the denominator here, which is over all the examples that you have, it's a very expensive thing to solve, and it would be unpractical to do a prediction using this particular formula. And the solution, which there's some more details on the blog post, is that you can build a tree structure that implements hierarchical softmax that basically does an evaluation of this, all the softmax formulation in a way that becomes practical and becomes usable in a real system. So again, the idea here is building a recurrent network over your visible, which is the songs that you listen one after the other, and assuming there is some relation between the hidden and modeling this using an L2 loss and a softmax for the probability of the visible given the hidden. And this is, I thought it was an interesting example, simple example of using sort of recurrent neural network. When I was reading it, I was thinking that it was so simple that it was surprising that it worked, but it seems to work, and in talking to Eric, it does seem like it's working pretty well. So this is yet another example of how applying one of these unsupervised deep learning approaches can lead you to good results. So, okay, I think that's it about the application of deep learning in the music case. In our case, again, I can't give many details of how we're using a very different model, by the way, because we're not interested here in modeling the sequence of anything, but we're basically building it as a, say, quote-unquote, standard recommendation approach. And one of the reasons you can see that we are doing this in a different way is the setup that we are describing. So basically, this is another blog post I published like 2 or 3 months ago, and we describe the details of the infrastructure. So we don't say what kind of neural network we're using or in what details for what, but we are saying how we have implemented it. So I think it's an interesting complement to what I was saying before, which is the other way around. So the idea here is for some of the, say, normal applications of deep learning, one of the problems you have is that you have a lot of hyperparameters to tune. And they're not, those neural networks are not easy to train. And how do you combine the training and the optimization of each of the neural nets plus the search on the hyperparameter space, right? And this is what we're doing, and what I described there is how to combine the training of the neural nets and the search on the hyperparameter space. So the training of a single multi-layer neural net is kind of, I was going to say has been solved. I'm not saying it has been solved, but it's pretty obvious that you want to do it on multi-core GPU machine, right? You want to optimize or minimize the out-of-box communication, and there's many examples out there from Google to others that have done a very good job of implementing deep learning and neural net training on GPUs. And that's exactly what we did, right? So we basically used GPUs to train each of the neural nets. Now the interesting thing is that, well, yes, but once you've trained one neural network and one GPU, and you want to train another one, or you train another one in parallel, is how do you figure out which one was the best one? How do you optimize your hyperparameters to understand which is the neural network that you really want to use, right? So the basic idea is you have a bunch of independent neural nets that you throw out there to GPUs, you train them with different hyperparameters, and then you use the best ones, but you need a way to coordinate all of that, right? So the way we did this is we have a central node where we're using, this has already changed by the way, but basically the idea is the same. We're using Spearmint, so Spearmint is an implementation of the Bayesian hyperparameter optimization using Gaussian priors. It's a package that you can download. It's in Python, and it's there are a couple more that are comparable, but Spearmint is good enough for what we're doing. I don't know if anybody has talked about Gaussian processes here. I think, you've talked about it, right? So the idea is instead of doing an exhaustive search in the hyperparameter space, you're better off doing something smarter, and using Gaussian processes is a good way to get started. So we have this central machine where we do the hyperparameter search using Gaussian processes, and we launch, once we iterate and we have a number of hyperparameters or subset of hyperparameters, we launch a different machine, and this is all done in the cloud, by the way, in AWS, Amazon Cloud. So we launch a different machine with GPUs, and we train that network. It comes back to a central node, and this is the sort of like the brain in charge of doing the different hyperparameter optimization steps. So this is how we combine, on the one hand, the power of training on the GPUs for each of the neural networks, and the distributed and environment on the cloud to do the hyperparameter tuning. Okay, so obviously this is a different implementation than the one I was talking about, because here we do have hyperparameters to tune, and here we do have a lot of neural networks that we're optimizing at the same time. Any question about this? Yeah.
Are you using methods like dropout?
Sorry, I didn't get.
Are you using methods like dropout?
Like dropout?
Yeah.
No. And I mean, there's a number of optimizations that we could do to the current setup, but the reality is that as it is right now is optimal enough that it's even more efficient than other traditional methods that we could be using, right? And by the way, this is something that you don't necessarily need to do extremely fast, right? So you can do the training every few hours, so to speak, and this is going to work. Okay, so yeah, and this brings me to something that I've talked about a couple of times, and it's when you think about distributing machine learning or parallelizing machine learning, people usually talk about how to parallelize or distribute like a single particular algorithm, right? And that would be like, for example, the training of a single neural network. And that's what I call the level 3. Level 3 distribution or parallelization. It's good and it's an interesting thing, but in this case, we really can do it using highly optimized CUDA code on multi-core GPUs, and that's really not our main concern. Our main concern is how to distribute on 2 other levels. And on the highest level, and that's something I didn't mention before, but usually when you have a large-scale system like Netflix would or Google would, you're going to have to optimize your models with a different set of hyperparameters for a different region, right? So you can think about if you have a ranking model that is working in the US and another one that is working in Brazil and another one that's working in UK, those are going to be tuned differently. And you need to be constantly retraining using the data that you get on those particular regions. And that's the easiest of all distributions, because basically what you do is they're completely independent. you can communicate data if you will, if you want to share some of the data, but not necessarily. Then the second level of distribution is the one that I was describing before, is when you're optimizing the hyperparameters, and that requires coordination because that requires launching different machines, optimizing different subset of the hyperparameters with a given algorithm, and then coming back and saying, okay, this was the best one. And then finally, the level 3, which is the algorithm itself. How is it distributed or parallelized? Right? And this is something that I usually see, especially in academia, a lot of people talking about this, but not too many talking about the other two.
This training would require the whole complete data set to be stored in GPU memory, right?
Yeah.
Is it a problem?
It could be a problem. In our case, it's we make it in such a way that it's not a problem. So you can make it part of your process in a way that you get sufficient data to train all the parameters you have, and you don't need to distribute this part over here. Okay, well, I have a little bit over half an hour, and I think I'm gonna probably get almost done with many of the things that are left, because these two are a little bit shorter. So I've talked about similarity a couple of times already in the context of recommendations. But in this case, what I want to bring up is a different idea, and it's the idea that in some cases, we might want to recommend things that are similar or a given definition of similarity. So the idea here is that our objective function now, instead of becoming what is it that I think it's going to be best for the user, and I'm going to be ranking on the data that I have from the user on what the user likes the most. Here, what I'm going to be using is the idea of similar, and this could be something that I use, for example, in the context of I've just finished watching a TV show, and I want to recommend something that is similar to the TV show that the user has been watching, just so that person can continue watching something that is related to what was just watched, right? And this is a little bit related to the prediction of the playlist that we were talking about in the song, right? So it's not only about finding something that the user likes, it's about finding something that is similar to the previous thing the user was watching. So when we talk about similarity in the context of recommendations, first thing to keep in mind is that similarity can be defined along many dimensions. So similarity doesn't really necessarily need to mean that those items are similar in terms of content, which was the content-based approach that we talked about yesterday, right? It doesn't necessarily mean that two movies or two books are going to be similar because they have approximately the same context. That could be an interesting input to the similarity function, but not necessarily the only one, right? So basically, you can have similarity in metadata or tags or content, but you can also have similarity in play behavior. And we talked about that when we were talking about the item-based collaborative filtering. You can have similarity in rating behavior. You can say, hey, I'm going to decide that two items are similar if users rate them similarly, and so on and so forth. So basically, you can have as many definitions of similarity as you want, and they're all perfectly valid. And you can learn models for each one of them. And what's more, you can learn an ensemble that combines all of them. And here, the interesting thing is that you can tune and optimize your ensemble to the data that you have, right? So in whatever context you want to present the similarity to the user, you can start with the definition of different concepts of similarity, and then tune your ensemble to the data that tells you whether the user reacts more positively to one similarity or the other. So it's basically a similar idea to the one that I was describing when we're doing the two-dimensional ranking problem, and we had rating prediction, and we had popularity, and I said, well, I don't know whether the user want more popularity or more rating prediction, but I can do that easily if I have data, and then I tune my model, and I find the weights depending on the data that I have. Here is the same thing. So basically, I have 3 or n definitions of similarity. I'm going to put them in an ensemble and then learn the weights depending on the data that I have. In the context of similarity, one important idea and something that works and has been described in the literature many, many times is the idea of graph-based similarities, right? So, given whatever sort of metric that can become a similarity metric, and here I can say, well, I don't know, I can use the cosine similarity between the TF, IDF if they're textual documents, right? I can define a graph which can be directional or not, in which, and in this case, I'm drawing it directionally, meaning that the similarity from fighter to madman is 0.8, but from madman to fighter is 0.3. You can do that. Obviously, it depends on the kind of data and the kind of way you define your metric of similarity. But the basic idea is that you can construct a graph like this, and then you can apply graph-based techniques to find what are the steady-state transition probabilities, or what is the similarity between movies that are not even connected directly. There's been, as I said, a number of works that explain how to do this. I would recommend, if you want to start somewhere, this is a good paper, SimRank, in 2012. And the idea is that 2 objects are similar if they're referenced by similar objects. And the concept here of similarity, and the reason it's called SimRank, it's basically a page rank for similarity. But the other interesting thing that they describe in this paper is how to combine these different notions of similarity. So the idea, I was saying, you can optimize an ensemble for. Here you can do it in the same graph, because the kinds of relations that they were defining in the graph, they were dependent on a so the axis could be depending on a given context or a different one. So they were using citation papers, and they were describing the co-occurrence of papers given the venue, given co-authors, given topic, and they were finding similarities based on how all these different axes were being described in the graph. So this is a good, interesting first approach. It's something that similar things like this are being used as a way to compute that notion of similarity. And again, this is a step beyond what we were saying before, and what we were saying, or I was saying yesterday, where I kind of simplified the notion of similarity and say, well, in the case of content-based similarity is the cosine similarity, or it's basically just the difference between tags. And in the case of collaborative filtering, when we're doing item-based, it's basically just the relation between users who have watched similar things. And here I'm just adding a little bit more of color and complexity to the idea of similarity. But there are methods like the graph-based approaches and the ensembles that can help you find a good definition of similarity. Okay, sorry, I'm going to move on. Social recommendations. This is another novel trend, and it's different to anything that we've talked about before. The idea here is that we're going to be using explicit connections between users to define a notion of trust. And here, the relation between users is not based on co-occurrence, what they watch, what they rate, or anything like that. It's based on explicitly defining, I'm your friend. Right? Is there a way that we can use that in order to infer recommendations. And the idea of trust is central to this, and the idea, you can interpret it as, if you're a person that has a high level of trust in this other person, whatever that the second person likes, you're going to like. Right? So it's not trust in the traditional sense. It's trust in the sense of how much you can trust the recommendation from that user. Something that comes up always is that, well, I may trust this person very well on if that person recommends me clothes, but if not, if that person recommends me music. So there are notions of trust that can be topic specific and take that into account. So, okay, let's skip through that. But the basic goal of many of these trust-based methods is that if you have some kind of graph like this, where you have 3 different people that are connected, well, it's kind of simple to come up with a method in which you can say, okay, how much would the recommendation from A influence B, right? How much can, because there's a direct edge connecting A and B. So basically, you can use this number, however you come up with it, to infer how much B is going to trust A. The trickier question is when you don't have a direct connection, right? And you need to have that in your model. So if C needs a recommendation, and the only person that we knows about that particular movie is A, how do we model the trust that C has on A if there's not a direct edge, right? So we need to find a way to propagate trust in a network. And that's what many of these models will do. So most of these models about trust and social recommendations, they're not so much concerned with the definition of trust between A and B, because that's something that you can come up, quote unquote, easily based on whatever proximity or based on any other definition that you want to come up with. But the idea is, once you have these 2 nodes connected, how do you propagate trust in the network to say, well, if that other node is not directly connected, how it should be influenced by that recommendation? So I'm not going to go into detail, but I'm just putting them up here and putting some references at the end. These are some of the most well-known methods for modeling trust propagation in the network. So there's Avogado and Appleseed, Motrust, and Gobit is very well known. She's actually probably the most well-known person working on trust-based recommendation, and her initial model was called Tidal Trust. So this is, and I'll talk in a minute about that. This is an interesting and very different way of building recommendations to what we have traditionally been doing, right? In the context that we've usually been looking at collaborative filtering, which is co-occurrence of things that people buy. We've been looking at content-based recommendations and what the items are in reality. And this adds yet another different view on the recommendation problem. And it's interesting to, I think there's a lot to be done on this area still. I mean, even though there's been some work, being able to combine, especially the trust-based with all the other more traditional methods, is something that there's still a lot to be done and not that much work. Actually, I was talking to somebody yesterday about it. There's been a couple of papers lately. There was one last year where, in the context of a matrix factorization approach, the strength of the social connection in a social network was used as a regularization factor in the matrix factorization computation. And that was an interesting paper because it was one of the few papers recently that has tried to add this notion of trust or social connection into the collaborative filtering approach, right? So I think it's going to be a growing area of research. Okay. As a side note, this is not even a method itself, but I thought I would mention it here. You can build recommendations based on demographic methods, right? And I think I mentioned it even when I was talking about the index. And the idea here is that you can use, just as you use content-based features on the items, you can use quote-unquote content-based features on the users, right? If you know where the user is from, the age group, and so on and so forth, you can build similarity functions between users and then use them as a way to recommend things. Or you can cluster users based on their demographic features. Okay. So basically, this concludes sort of like all the view that I did on the different kinds of individual recommendation methods. And just to give sort of reminder, we started with the traditional collaborative filtering content-based approaches, and today we've seen that one good way to think about a recommendation is to think of it as a learning to rank approach, and we learn how to build a two-dimensional ranking problem, and we talk about point-wise and pair-wise and list-wise approaches to learning to rank. Then we made the problem a little bit more complicated by turning it from a two-dimensional problem to an n-dimensional and adding context, and we talked about tensor factorizations and about factorization machines. Then we went to see a couple of examples of how deep learning and neural networks are being used now to build recommendations. And finally, I talked about the notion of similarity and graph-based approach to similarities, a way to recommend, and then yet adding another dimension to our recommendations, which come from the social network approach and the strength of the social connection between the users. So with all those methods, and I've mentioned it a couple of times, an idea that comes out many times is that you want to combine them, right? And the easy, obvious thing is to build an ensemble. That's a great way to combine them. But there is some tradition in the recommendation literature of finding different ways to combine approaches in what's called hybrid ways, right? So hybrid recommendations come from this idea here, and this is a paper. I don't remember when this paper was out, but it's pretty old. It's meaning that it's been more than 10 years out. And the idea is pretty simple. If you have a collaborative filtering approach, you're going to get this kind of precision. And I don't remember the scale, what it was on. The idea is, of course, the precision of the collaborative filtering approach is going to increase the more resonance you have in common between people. Then if you have a content-based approach, it's going to be approximately flat. And initially, and that's why content-based approaches are good for co-star, it's going to be superior to your collaborative filtering approach, but at some point, it's going to be surpassed by the collaborative filtering approach. But even better than any of the two is you can combine both of them. And if you combine both of them, you basically get the best of both worlds. Right? Now you get the best performance and almost flat, and you get it both for the co-star case and also once you have more data points.
But it looks like if I have 25 restaurants in common, I would drop the combination and I would just go with collaborative.
You do?
Like if I would extrapolate, then the
this curve might. I mean, theoretically, if two methods are uncorrelated and you combine them, even in an ensemble, right, it's going to be at least as good as the best of them, right? So the idea is that you don't need to. You should by combining them, you would if you do it right, you shouldn't lose anything over the best of the methods that you're combining, right? I know what you mean, that it looks that at some point this curve, but not necessarily. I mean, I think they might end up almost meeting, but you're probably always going to be getting something extra by adding that extra content. Okay, so this is a summary of the different methods for hybridizing recommendations. So I think I'm gonna be going over them quickly, but we have weighted, we have switching, we have mix, feature combination, cascade, feature augmentation, and meta level. So the weighted is probably the first one that you would think about, which is the ensemble weight, right? So the idea is you have different combinations, different recommendations systems that come from different places, like collaborative filtering, content-based, or any other approach, and you find a way to combine them and to build a linear ensemble, for example, and to determine what are the weights and how to combine them. You can think of the learning to rank approach that I was saying as a weighted hybrid method for recommendations, where the weights were determining the popularity and the rating. Now, as I say here, one of the limitations here is that you're assuming that the relative value between the weights is uniform across the different items, and that can be trickier, right? Because depending on the relation might not be linear, might depend on different things that are dependent on the item space or the subclass of items, whether they have more or less ratings, and so on. Okay, switching. In the case of switching, you have some sort of criteria in which you determine whether you're going to be using method A or B or method A, B, or C. And here the idea would be, well, if I have one particular item that doesn't have much data, I'll switch to content-based. If this item I know that has a lot of feedback, I'll use collaborative filtering. And you use that as a condition, right, to determine. And that's what actually the Daily Learner, which is a system, I don't know if it's up still, but it's a system that was using content and collaborative filtering and was using a switching technique in which you were determining which one of the two we're using. And the idea is, in this case, it was using content-based recommendation and having a notion of confidence on how close those two items were based on a definition of similarity in the content domain. And if it didn't have enough confidence, then it would switch to the collaborative filtering approach. And of course, the switching condition can be done in whatever way you want. The mix approach, in the mix approach, you're basically just getting the output of the recommendations from both methods and then defining a way to mix the outputs and the items at the end. And you can think of this as a way to say, well, I'll just use most likely I'll just use collaborative filtering, but for new items that I don't have ratings for, I'll use a content-based approach, and then I'll find a ways to insert and to add them in a way to the output of the collaborative filtering. You can do feature combination, and that's another way to hybridize. And the idea here, how do you combine collaborative information in some method or in a way, and you can do that if you use some sort of regression model, and you add collaborative data and content-based data as features to the rating or the ranking prediction component. Cascade, this is an interesting method in which you basically make a recommendation, build a recommendation based on one particular model, and you use the output of that as the input of the next one. So you can, and in between you can do different things, like you could probably build sort of a ranking approach on the first part of your recommendation, and then take the top of the ranking and feed it to a new recommendation that is going to do a different thing. Or the other way around. You could do build rating prediction recommendation based on collaborative filtering. Say, now I'm only going to take the items that have a predicted rating that is higher than 3. And I'm going to input that in a completely different recommendation system that's going to be implementing a learning to rank approach. Okay. And this is using the output of one as the input of the other. And feature augmentation, you can, this is the idea basically that you use the prediction from one method as a feature to the other, to the next method. So here you're not inputting the output to the input of the other, but actually using it as a feature. And here the example that we were using before of the using the rating prediction as an input to the two-dimensional ranking would be a good example of this. Okay, so I have 10 minutes to just give you a quick walk through some of these things, how we apply them to Netflix. And oh, yeah, one thing that I didn't mention yesterday, I think I got a question after the class, is I talked about the RVM and the SVD, and I'm missing the pictures again here, and said, hey, we're using this in production. And some people ask me when I talk about those two things, they tell me, yeah, sure, but the final prize in 2009 had 104 different methods combined in an ensemble. What happened to the other 102? And the answer is we are not using them in production. And there are a couple of reasons for that. And first reason is the difference between the delta in RMSE between the first year's progress prize and the final prize in 2009 was very small. So it was relatively small for the added complexity of going from 2 methods to 104. So it didn't really, all the complexity in engineering that we had to put in to add all these methods was not really necessary. Well, not necessary. It wasn't really, we were not sure that that was really worth it. The other reason is that we switched our focus at that same time, and we switched our focus from rating prediction, which was our problem in 2006, to many other things which are our problem today. And one of the reasons the reason that rating prediction was so important in 2006 and it's not so important today is the following. In 2006, Netflix was a DVD by mail company. So people, what they would do, by the way, anyone used Netflix DVD at one point? Anyone still using Netflix DVD? Oh, one person. Good. So I use Netflix DVD, by the way. So so the idea when you use a DVD is, or when you're using this kind of product, you put a lot of thought in what you put in your queue, because you're basically optimizing ahead. And you're thinking like, what do I want to watch on the weekend, and maybe with my family or whatnot. So you're really putting a lot of thought. You're thinking about what you want to watch. You're putting it in your queue. If it comes 2 days later and it turns out to be a bad movie, you're really disappointed because you put thought, you waited 2 days, you get your movie and like, oh, this is not what I wanted, right? So you have a lot of incentive to go back to the system and say, hey, this was awful. I'm going to rate it, so next time you recommend me something different. There's a lot of incentive for people to give explicit feedback, and there's a lot of incentive of people to actually put thought into what they decide to watch. In the case of a product like what Netflix is mostly now, which is streaming, this has changed dramatically, right? So now you go in there, you hit play, you watch 5 minutes, I'll just go to something else. So the cost of switching to something different is very low, and the incentive to give feedback to the system is much less. So what we found during time is explicit feedback is now much less and much worse. And on the other hand, we have a ton now of implicit feedback, so we're not really so much interested anymore in doing rating prediction. Now we're interested in building things like ranking and so on, which are based on implicit feedback. And that's, by the way, that's a story that's repeated in many different companies, and you saw companies like YouTube going from a 5-scale rating system to just thumbs up, thumbs down, because they were seeing a similar problem in which the quality of their ratings over time diminished and their rating prediction didn't make much sense. So this is what I'm saying here. We were DVD by mail. Now it's completely different. It's streaming. It's on many devices. Even giving feedback in some devices is kind of like annoying and clumsy. So I like a lot this quote because I think it summarizes some of our feeling and some of the things we do. Is that Netflix? This was posted on a Huffington Post saying Netflix, my list feature, knows you better than you know yourself because of algorithm, and that's really true. This is telling a real story. So we have a list in Netflix where you can add the movies that you want to watch in the future. And a few months back, maybe a year already, we allowed the users to actually sort those things by themselves, right? So basically, you put things there, then you could move them around, put whatever you wanted first, and it was all up to the user. And we did a test in which we said, you know what, instead of letting the users do that, because users are lazy and they don't really know themselves, let's build algorithms that actually optimize for this particular feature, right? So we built an algorithm to sort the list, and guess what? The result of the test was positive, right? So this means that for whatever reason, the automatic sorting that came out of the algorithm was much better, and people were watching much more from that list than before, when we would allow them to find their ideal sorting themselves. This gives you an example, and it points to the fact that almost everything around Netflix is personalized and is really being recommended. And one of the reasons is because users, in general, will tell you, if I ask people, especially the people that are really into Netflix, they will say, oh, I want to do it myself. I want to really, and I'm really into it, and I rate a lot. But the reality is that most people want the algorithms to do the work for themselves. So this slide kind of summarizes the evolution of what Netflix recommendation has been over the last few years. We went from rating prediction, the Netflix prize, to ranking optimization, which is something that we're doing, and I think we're doing pretty well already, to something different, which is what we're doing right now, and we're focusing a lot of effort, which is page optimization. And this is interesting because this is a different concept that there's not much in the literature. There's a lot about ranking optimization, but page two-dimensional optimization, that's a different story. And here you need to take into account attention models, browsing patterns of users, and you need to take into account things like diversity and so on. So it's a really tricky and interesting machine learning problem that we're working on right now. So ranking is what we do in this dimension, right? So this is the typical user interface for Netflix. You have rows, and each row has a ranking. And this ranking is not, obviously, there's a lot of thought put into this ranking, and makes a lot of difference what kind of model we use to rank each of these rows. And we use learning to rank approaches like the one I described before, in which we use things like rating, popularity, and many other things. And, oh, here we go again. I'm missing, I think, for the last couple of slides, maybe I'm better off doing PDF. Okay. sure I have the pictures. Okay. Okay, so another thing we do is put a lot of effort in building algorithms that bring up support and explanation for the recommendation. If you look at this thing here, it has so much information and support for this recommendation. And what we put here makes a lot of difference. Even the image that we put here is going to make a lot of difference on whether you want to click on it or not. And here we have things like, well, this was based on your interest in this, this, and that. So we're giving you hints on what are the things that have brought up this recommendation. We even use the rating prediction. So the rating prediction that we were using before as our objective function now has become a feature, and it has become an explanation, right? So it's a completely different way to think about rating prediction. And of course, we have all this metadata and so on. And we even tell you that it's in your instant queue. This is not called the list, but same thing. And this is also giving you a support for why you should want to watch this. We also have, so I talked about social recommendations and about trust-based. We do have that. So if you connect to Facebook, you will see what your Facebook friends are watching, either as a combination, and here we use some of these approaches, or either individually. I'm going to have to start finishing now. For the rows, we use implicit, explicit, and hybrid taste tests. So we build them based on things you watched before, things you told us you like, or the combination of all of them. And concepts like freshness and diversity are something that we also need to take into account when we're building many of these things. And this is what builds this kind of very interesting roles where you have independent dramas featuring a strong female lead. These are genres that are made up of combinations of different tags, and we make them based on your taste preference. Here, for example, here we give you this row because you told us that you like independent, and that's why you get independent, but also because you watch these two movies that have some of these tags here built into them. Okay, we have similar, I talk about how to build similarity recommendations. We use that in some rows and in many different contexts. For example, when you add something to your list, or when you search for something. And then we have the problem of page composition that I'm not going to go into, but we do have this idea of what's the attention of the user, and we build using both click data and also eye tracking. We have models of attention of where the users, how they browse, and where their attention goes, and we have some information of that going into the model to be able to learn what matters and what doesn't matter. Okay, oops, sorry, I'm going the other way around. Search recommendations, so we treat search as a problem of recommendation. If you search for something like Italy, you're not really searching for a movie that's called Italy. You're asking us to recommend you something related to Italy. If you search for Schindler's List that we don't have, we also want to recommend you something related to what you're searching for. Right? So post-play is also another form of recommendation. You finish watching something, what you get afterwards. And all this are based on algorithms and ideas that I've described before. We don't have on PS3 this new idea of gamification, or how to build recommendations into a game. And all the data we use, metadata, social, impressions, and this is a list of models that are currently in production. And that's it. I'm going to finish with some conclusions and talk about many different topics. I just have a couple of things to add here that, understanding data and users is a very important thing, not only for recommendations, but also for many other things like search, advertising, networks, and so on. Good data is important, but it's also important to be able to optimize the algorithm at the same time that you get data. And actually, let me see. I think my last piece of advice, because I see this happening many times, and it's about this relation between data and models. I've seen time and time again how people throw away ideas or throw away features because they're trying to optimize independently the feature space or the data and the model. And that's something that you need to be very careful with. So I'll give you two examples. If you're using a linear model or say a logistic regression, and you come up with this great idea of like, oh, I'm going to add this feature, but that feature turned out to be non-linear or non-linearly dependent with the output of the logistic regression, it might turn out that your logistic regression is not able to learn it or not able to learn it in a significant way that you're optimizing or you're improving your metrics, right? So what happens there, people have this simple model, they try this new feature and they say, oh, it doesn't work, forget it. And they forget about that feature as something that it's not adding any value. The other way around, you've worked for some time and you have your super optimized linear regression with a number of features, and you say, you know what, let's try a super smart model now, and let's feed all these features into our random forest. It turns out that it doesn't work, or it doesn't add anything significant to your model. What happened there is that you had optimized your feature so much for a linear model that a nonlinear model is not going to add anything to it. So what's the solution here? The solution is you always need to be careful about optimizing both things at the same time. If you're optimizing your features, optimize your model, and the other way around. If you optimize your model, make sure you add features that your new model is going to be able to learn from. And with that, I think I'm over time, so I'm going to just go. You have all the references are going to be on the slide, so I put a bunch of references here, and even online resources where you can learn more about recommendation systems. Okay, thank you very much.
Thank you very much for that lecture. So now our next final lecture.
We usually compare in another fashion, but basically what we do is we have some benchmark that says, hey, using this model, using this model, using it this way. There's no, I mean, really, hard to tell you exactly better. You have to use it kind of weight. Yeah. Let me get out of the way now. Does that make sense?
Oh my goodness. Well, obviously, this that can be but basically, you can tell me yes or no. There you go.
Sorry,
That's.
So
I just need one bit of information, basically.
you need it now? Yeah,
You don't.
I'll say yes. I
If something.
No. I have to get an email, but I need confirmation from a professor right now, but I didn't reply.
Okay.
I'm probably free, so I'll say yes. If he replies the email, I'll let you know. Okay, but
Okay. So 7 or 7:30.
yeah.
Yeah, so.
But it's all this type. So Netflix is a constitutional hybrid.
Oh yeah, actually,
That's if you really have
that's fine. Oh, yes.
No, he can't. Well, they have so many. I have to do so many.
I do know that there's
Well, yeah. Well, it's really nice to Australia. Well, at least only one small connection to in general, that's right. It's very well, it's temporary. You don't have no connection. Oh yeah, that's what I mean. And like in Europe, it will be like
I think probably expect to increase their power.
how much is it?
So I get
I hope that basically, same price.
Apparently people just they
Yeah, I just wanted to see the battery.
better not to get married, you know.
Yeah, I think. Okay, guys, we're starting again. Stan Feldman has his last lecture today, and yes, so I think it's probably a good idea if we start. We're already 15 minutes late, and yeah, there's a lot of content to go through. Okay, awesome. Oh.
Okay, so let's summarize what we had till today. So we talk about dealing with big data, which means streaming and parallel computation, either a lot of machines or a lot of threads. And for this we have the merge and reduce tree. And we define first definition of call set, very general definition, so we can use the merge and reduce tree. You reduce the problem to just reduce a set of 2x point to x point. So we get rid of the big data and we just say how we can, what is the minimum x that we can compress two sets into one, so we can use this framework of all. And then we show some costs to a specific problem, and I try to give you a general solution for the case where cost is just sum of some distance function over the point to a query. We expose the cost of the point to a query, and we reduce this problem to computing two things. Dimension of Q and sensitivity. The first one is usually very easy because it's related to problem computational geometry that people solve for years. And actually, even if you don't know if for the algorithm it doesn't really matter, just tell you how much samples you need to take, and in practice you can just take, depends on the memory that you have, even if you don't know the exact analysis. More harder in theory, and also more important in practice, is the sensitivity, because this defines the distribution of the non-uniform sample that you need to take, which point you need to take with high probability, and which point with small probability. And today, I will talk about, give some examples how you actually bound this sensitivity, reduce this problem also to fast approximation algorithms that's related to the original problem that we want to solve. So I will start with a quick example. So suppose that let's start off with our courses for the SVD problem or the vector multiplication. So what we want is a course set in the sense that for every x that you give me, and A is an input, we have this property. So the input here is a matrix, n by d. D usually is much more than n. We have some epsilon, and what we want is a diagonal. We want a sparse diagonal W. We want to select some rows from A, so the sum for every x, the norm of ax squared and the norm of the weighted rows of A multiplied by x squared will be approximated by, up to epsilon compared to the value that you actually want. So the fact that we want a subset is important. For example, if the input is sparse, so if this is the Wikipedia document term matrix, for example, you want to preserve private sparsity. So that's why you want actually, if the rows are sparse, the subset of rows, the weighted subset will also be sparse. But in general, if you don't care about sparsity, there is a very simple solution. Actually, you can have a core set with no error. So for every x, you have this property with equality. When this is n by d, and this is just d by d, which is kind of analog and related to the exact core set that we have to work for the one mean problem, for the mean sum square distance to a point. As explained yesterday, this is sum square distance to a hyperplane, which is orthogonal to x. And someone knows how to compute such a matrix C, so it's d by d, based on A. So just for every x, this and this will be the same, exactly the same. Any guess maybe? Okay, so actually it's very simple. You already learned the tricks. You can use either the QR decomposition. So if you write A equal QR, the branch mean that you already learned. So I meant this and that. What you get is AX, QRX. But this is a orthogonal matrix. So only need to compute Rx, but R is the by D matrix. More specific case is to use the SVD. Now if I give vector x what you want, is u dvt x squared. You can get rid of the u because it's orthogonal. And dvt is a d by d matrix. But in both cases, we get a matrix that is not subset of the input and we kill the sparsity. But unlike random projection, this is deterministic matrices, and it always works. There's no probability here. But the framework that we talked yesterday about will take weighted subset of the points, and the question is how to bound the sensitivity that we defined yesterday. So for our problem, the sensitivity is for point P, which is a row in A, is the inner product of the row. So we want to maximize over all possible x the contribution of the row, which is P, in A. So one row multiplied by x squared, you get this value, divided by the total cost, which is this. So for a specific row, what is the query x that is dominating the cost, and we must take it for the costs. In order to bound this, first of all, we will compute the SVD of A. And you observe that for some x, P, we have a matrix A, and the ith row of A is just the ith row of U multiplied by dvt. So if A equals U dvt, the ith row of A is the ith row of U multiplied by dvt. So this is actually the ith row of U dvt multiplied by x squared. And here we can replace A by the SVD, which is U dvt. Again, use the orthogonal, so you can ignore it. And we can just put, this is a number, we can just put it inside. And what we get is UI multiplied by this vector normalized. So this is just unit vector. And everything squared. Can we bound this now? So what is this? This is just unit vector. Whatever x give me, this will be unit vector. So we have an inner product of two vectors, and we squared it. So if you have a vector UI, what vector x will maximize the inner product between the two vectors? So inner products, remember, is just a projection. UI, right? The vector himself will maximize the projections on the vectors. So we get that this is just bounded by UI squared. So it tells us that the probability to choose a point in A for our core set should be with respect to this value. So we compute the SVT and take the norm of the corresponding row in A. How many points we need to take? Well, the total sensitivity is the sum of these sensitivities of all the points. The sum is norm UI squared. But since this is a orthogonal matrix, we have here D orthogonal columns. The sum of the squared entries of U is just M. So this multiplied by this dimension gives us the number of points that we need to take. Note that it's independent of the number of rows that you have in A, which is N. It just depends on D. So one of the things that you do, also professors, actually it was quite a shock that they ask me how to compute SVD fast. And you say, oh, that's easy. First of all, compute the SVD, and then sample points according to the SVD. But they want me to ask them how to compute fast SVD, and the first line in the algorithm is compute the SVD. So why does it make sense? Remember? I mean, if the main motivation for using this kind of compression is to do the SVD fast, why it's okay that the first line in the algorithm is said to do the SVD? This reduction. The input is never an output point. You always get about 2D points compressed into D. We never get a huge amount of data. We apply this algorithm only on a small set. So we want to have SVD for all the data, but we are essentially just running small SVD for very small chunks of data. This we can do very fast. Because when you construct a tree, when you give more and more points, we just need this construction. Get to D, compress to D. Get to D, compress to D. And this is kind of the very new kind of paradigm that we use in a coarse construction when we actually use existing single solution just to improve this exactly the same algorithm. So next, let's do the same for a totally different problem, which is the k-mean. And again, thanks to all this framework, we just need to bound the sensitivity of the k-mean or k-median problem. And just take a few lines, and we'll have a course. So again, the implementation of this course is just three lines in MATLAB or Python to the SVD of the matrix and sample point according to the matrix U. Nothing too sophisticated. And then, of course, we plug in the streaming T to handle large data sets. Okay, let's move on to the K-mean problem. So in the K-mean problem, we want that for every point, so we sum the point. So Q is a set of K-center in RD. This PQ means the distance for the point P to its closest center in Q. And you want to approximate this by some weighted set, where C is a subset of P. I will do this for the K-median problem, but the surprising thing for the K-mean is essentially the same. So the optimization problems are usually quite different. K-median is quite hard, and much harder in some sense. For example, the one mean is trivially, but the one median is actually possible to compute in general coordinates exactly. But for the cost of compression, it's almost the same algorithm. So I will just hold the K-median, and for the squared version, when you have this squared, just a simple exercise. So we want that this will be epsilon, the original value that we want, to get 1 plus epsilon approximation. So again, the visit dimension is just the visit dimension of K balls in RD. Quite simple, and it's an exercise from Tensor geometry, so I won't talk about this, and you can just Google it. Results from the 70s. More harder will be to find the sensitivity. Sensitivity is the maximum query, the maximum over every K centers in RD. This is the contribution of the point, the distance to the nearest center, and this is the sum, the cost for all the points. To this query, we want what is the worst. We want to upper bound for this. Of course, trivial upper bound will be 1, but we want the sum of sensitivities will be small. Something like K maybe, and not N. So for this, to solve this optimization problem, we first use the triangle inequality. So suppose that they give me some Q, how we can bound it. So suppose that we have the optimal solution. Now, even if you have a small set, computing the optimal solution for K-mean might be quite hard, so to do the epsilon to the K, and we'll get rid of it very soon. But for now, suppose that we just want to prove coexistence. So suppose that someone already gave us the K-means, and we want to prove that the sum of sensitivity is small. So then you can say the distance from P to your query is this P to the optimal K-mean, which is independent of Q, divided by the same sum. And if you want to go from P to Q, we go from P to Q star, and then from Q star to Q. So we have this other term, Q star Q divided by same distance. How we can bound this? So this is easy. So we have a point P. The point P goes to the center Qi, the optimal solution, and since Q is the optimal solution, it must be smaller than this value. So what we get is that this is less than same thing. Divided by So, so eventually the next term that we need to bound is the, sorry, this is Q star. So this term is independent of Q now. If you to type that this must be larger than the optimal solution. So the sum to the query is more than the sum to the optimal solution. Now we get a term here that is independent of Q, and we can compute in advance. But this term still depends on Q. So we want to bound it in advance before knowing what is Q. For the main observation, again, we can use the triangle inequality. So we have this Qi star in the optimal solution. The query is less than first goal from the optimal solution to P prime. So P prime, we have for every point, we have the projection on the case k-mean, the center in the k-mean. So I will, for every point, the center in the k-mean that belongs to P, we just multiply P prime. So if you want from Q star to Q, you first go from Q star to P prime, and then from P prime to the query. And now we can just sum it over all the points in the ith cluster of the optimal solution. So if we sum each inside, we get that this is the number of points in the ith cluster multiplied by this number. And on the other side, we just have a sum. All the points in this cluster this optimal solution, go to P prime, the center of the point, and from the center of the point, back to the query, to the newest center in the query. But, I have another ball. Let's see if I can switch. Here, this is, okay, we just try to finish the equation. So, go up to there, and this is bounded by sum over all the points. You can just remove this. But instead of summing just the cluster, we just sum over all the points. And what you get is this is just twice the sum of all the points to this P prime Q. So this is the optimal solution. So it must be less than the sum of distance to the query. And this is the same sum again. That's why we have twice this sum. And now if we take this equation, this inequality, I'm sorry, and plug it back here, we get the bound. So what we get is the following bound. We'll be some nice pictures in a few minutes. So, to conclude, the sensitivity is just bounded by this term, which is independent distance from the point to the optimal solution, compared to the sum, the cost of the optimal solution, independent of the specific query Q. And the other term is this divided by sum is 3 prime cube. And if you plug in the last inequality, this sum disappears, and what we get is that this is less than. The first term remains here the same. But if we replace the first statement, what we get is this is just 2 over pi. And this is essentially the sensitivity of the point, the boundary sensitivity of the point, which means that for every point, you should compute the optimal solution for the k-min and take the distance to the optimal solution compared to the optimal solution, plus 2 divided by the size of the cluster in the optimal solution. So if you're in a very small cluster, it will be selected with high probability. Or if you're very far from the original cluster, it will also be selected with high probability. And just a second, what will be the sum? So the sum of this will just be 1 of all the points. It gets sum into size. What will be the sum of this? So 2 over the size of the cluster, the sum of all the points. So that you have pi points on cluster number I, so it will be just 2k, right? This will be the sum of this of all the points, will just be k. And you get again total sensitivity that is independent of n. This is the number of points that we need to take, multiply by the density dimension, which is about dk. Now, note especially that this is independent of d. The dimension just comes from the density dimension, for the dimension of the queries, and to get rid of this, for example, with this projected points on small dimensional subspace using PCA, this was the solar paper last year, and we showed that we can run this algorithm on the small dimensional space. So again, we combine techniques. Another observation is that since essentially we need the epsilon over t approximation, in this case t equal k, so we have to essentially use k squared points in the corsets. Can we get rid of this term? So if you try to bound this equality, you probably won't be able to get rid of this to k. But what we can do is just change the problem. So this k comes from this term. Intuitively, this term say if you have a small cluster, you must take some points around them. What we did to get rid of this k, this was in the stock paper 2 years ago, we say, let's solve a different problem. So suppose that you have the k-mean of good approximation. So take the k-mean, put it in the coset, and now all you have to approximate is the sum of the point to the query minus the distance of the projection of the point to the optimal solution to the query, because this term you already have. So we just have this simple observation. If you want to compute sum of distances to a query, just take the sum of distance for the original point minus the projection of the optimal solution of the k points, plus this projection again. This thing is just k points. Every point goes to a representative, the optimal solution in the k means, but we have only k points in the optimal solution. So this is just k-weighted point with the sum of weighted n. And all you need is to find the sensitivity of this function, and the sensitivity of this function will be without this. You have sensitivity of 1. So in other words, we kind of change the problem. Instead of trying to have cosine for k-mean, we're just trying to solve the cosine for k-mean after we project the points in low dimensional space. And we say, okay, let's also point some good guess before we start, and then just approximate the difference between what we want and what we already take. We kind of have a few steps as a preprocessing, and we have a new problem which much more sensitivity, where the visible dimension is independent of k, and the sensitivity, the visible dimension is independent of t, and the sensitivity is independent of k. So this is generally how we use Corset. We use a lot of tricks for different approach, and this framework, you know, it's helps a lot. It's still an open problem. How, for example, you can compute the first Corset that I showed you with the k-center with the maximum distance in this framework. We only know how to deal with sum or sum squared. We hope to get a more general framework in the next years. And then another problem that we have is that most of the courses depend on some optimal resolution. So in the previous course, it was the SVD. Sometimes, if you have huge data, it's still very hard. If you have d point, d squared time for SVD or d to the CV might be too much time. Solving k means, again, it's an NP-hard problem. So the observation is that we don't need the optimal solution. So what we actually need is a very, very rough approximation that we can compute very fast. Before I forgot some acknowledgement, so I stole some of the slides for k-means from our ellipse presentation, and I direct class and met you for helping with this. The movie of detecting flying quadrotters, the mechanism from the student in Haifa, Sarim Nasser, and the first application of margin reduced trees for corsets by Apparent and Masunda. We generalize it to the parallel case, and the main technique is actually by Sachs from the 70s. But Apparent and Masunda were the first to actually apply it for corsets. So essentially, we use the sensitivity problem to compute some good approximation. And what is a good approximation? So, so if you have a set of points, for example, here I assume that you have the optimal solution, which is, for example, the k point that minimizes sum of square distances or sum of distance to the input. You probably heard in computer science about constant factor approximation for a problem, especially for NP-hard problem, that we sometimes achieve, which means you still return k-centered, but now the cost is at most constant factor compared to the optimal solution. So you're cheating with the cost is much a bit larger than the original cost, but only by a constant factor when you call it 2 approximation, 4 approximation, and so on. Less popular is even more general approximation, which is called the bi-criteria approximation. So not only I give you a few center which constant factor approximation or log n factor approximation to the optimal solution, I also choose a number of center. I use k log n center, for example, instead of k. I still compare the result to opt of k. The opt on the right is for the optimal k center, but I allow you to use more centers and you can choose with the cost. This is so rough approximation, so we usually can compute it very fast, and that's what I want to show you now. And actually, you saw this one algorithm, a few lines of code that is good both for k-mean, k-median, and k-standard, the same result. Again, because we have so many centers there. And the nice thing is that if you look at this proof and you assume that instead of the Q star is optimal solution, you just replace it by this kind of approximation. So the constant size will be only larger by a factor of log n. So the sensitivity will be increased by log n instead of 1. So we have a constant of size log n multiplied by the dimension, log n k multiplied by the dimension. But you can actually, even if you have this rough approximation, what you can do, and this is again related to the comment that I got in the first day, you can compute courses for epsilon equal 1, use this rough approximation, sample points, and then you have a course of size k log n, and which give you just constant factor approximation because you use, say, epsilon equal 1. But the course size will be about k log n, the constant d. But now what you can do is to compute an exhaustive set, the optimal solution for this small set, maybe constant factor approximation, and then compute the course set again using the new approximation. So again, you have first rough approximation, use it for getting small course set with a constant error. Then you solve again the problem on the course set. Now you have a lot of time because the course is quite small. And then we have constant factor approximation, and the constant style will be reduced to k. So again, we're moving from a very rough guess to a better guess more and more until we get cost of size k, and then we can run our original heuristic or algorithm. How this bipartite approximation works, it's extremely general. This is the algorithm. So T will be the counter, and F is the output. Just take random sample. So we don't have any, we cannot do sensitivity because we have no idea where are the important points. We just take random sample. Now, because we don't have anything better to do for now. But what's the problem with random sample? We miss points that are very far. So instead of just going home, we add this sample to the output, compute the distance for each point to its nearest center in the sample, and remove but only half of the point or part of the point that are close to the sample. So if you have outliers there that are very unhappy with your sample, we keep them. We try to approximate them later. We just take the points that are quite happy with our approximation. And we remove them. And we left at the point that we're unhappy with the sample. So we just repeat and sample them again. Add them to the output. Compute distance for each of the original point to this new sample. The point that are left now. Remove the closest point. And continue recursively. So suppose that there are billions of points here and one point here. What will happen? You sample a few points, so probably all of them from here. You reduce half of the points, so this cluster will be reduced by half. And this one will stay here. You sample again. Again, you probably sample all the points from here, half of it will be reduced. After log n iteration, this cluster will disappear. Because every time you cut it by half, and then you will sample finally this point in the end. It's kind of multi-resolution approach to getting one point. And it's not a heuristic. We have a proof. I won't prove it here, but it's quite simple, quite general. That so for the size, so all you need to sample is about k points in each iteration, and we have k log n iteration because every time we remove one function, so we end up with k log n centers, and the running time is actually O of n, because although you have log n iteration every time the input is reduced by half, with the geometric sequence. So it's a very, very fast approximation, and you can prove that it's good for k-center, k-mean, k-median. Beautiful proof, but I don't have time to talk about it. Harder problem might be to talk with what do we have lines. So we want to approximate the points by k lines, for example, or a subspace. So we cannot just sample point and return them because the output is a line. So we can generalize this idea. Just take, again, the input. The output will be now a set of lines that approximate the optimal k lines, for example. And the idea will be, again, we'll have log n iterations. Take a random sample. Now the sample size also depends on the dimension of the subset that you want to approximate, but it's still a very small sample. But now, since we want lines not point, we take all the lines that pass through the input points. To the sample point. So you sample 3 points, you convert them into lines by taking all the pairs of points, put these lines in the output, compute distance for each point to the nearest line in this sample, find the farthest, the closest half. No, it's not balls, it's kind of steps. Remove them, and continue recursively. Again, we have only log n iteration. We have a bit more lines now, because it's square root of the number of points. Every pair is a new line. But if we want just lines or low-dimensional subspace, it shouldn't be too much. And this is the trick when you want to approximate points by few low-dimensional subspaces, for example, for topic selection. I have another few minutes. So I show you practical codes that we use for the iDiary project. Back to the problem when you want to approximate points, for example, by k segments. So again, the sensitivity is for each point in general, if you want weighted subset, is too large, because you already see this is the input point. Every point is sensitivity 1, because we have queries like this. For every point, there is a query which is dominated cost. So SP equal 1, and the sum of SP is n, so we don't have small coset. But the trick was to project the points on the optimal solution for a good approximation. So we first compute the optimal solution. We project the points on the optimal solution, and then based on the sensitivity, we sample point in proportional to the distance to the projection. So intuitively, if you're very far from the projection is not a good representative. You want to select it because with high probability, we're very close to the projection. Since we have the projection, we just select it with very small probability. And the proof of this is again based on the same framework, but now the function is at least, instead of distance from a point to a k-segment query, it's the distance from a point minus the distance of its projection of the optimal solution to the same query, and the sensitivity of this function is bounded. So again, we manipulate the input to have a new problem with a small sensitivity, and then we can have small coset that is based on the weighted points plus all the projected points on the input. And again, because of this range function, plus and minus, we have points with positive weights, and the projection is with negative weights. So the algorithm looks like this. We take the points, compute optimal solution with some good approximation, sample point that are very far, take the projection of the point, compare it to the sample together with the sample point, and this is the final coset. So for example, if we try to take the dynamic problem, the optimal solution on the real data, for about 10,000 points, we get running time of a week. When we run the same solution on the coset, it will took about a minute. And based on this result for small data, we believe that this is still a good run perception approximation, and the theory supports us with this. But the nice thing is that we took a lot of heuristics that we found on the web for solving this problem, and we just run this heuristic on the cosets. And this heuristic, again, we're offline, but now we're able to run it for big data framework when we have millions of points and few computers. And the nice thing you see, so in the optimal solution, the red one, you see that the coset is always bad, of course, than the original optimal solution. But for some of the heuristic, you see the coset is sometimes even better than the result of the existing heuristic. Just kind of nice, and again, we see this phenomenon a lot. The problem that we have with this approach, again, is that just smoothing the signal is not enough, because, for example, when I go from home to MIT, we go to the same road several times. And what we actually want to identify that over time using the same road and the same segment. So we want to deal with this phenomena, not only just smoothing the line, but also find repetition of lines over time, which is a much harder problem. So what we did is to observe that usually we don't do just random walk on the planet. We usually go home, walk, taking the kids to kindergarten, gas station, the park on the weekend. I visit the same places. Sometimes I go to see some other places, but most of the time, kind of just hit a Markov model, same places all the time. And essentially, we have a lot of segments that I'm going to on the time signal, which repeat themselves. So we change the problem, and we show that we actually want a k-line that minimizes the sum of squares distance to the points with the following constraint. When you project all the points in three-dimensional space, the signal, on two-dimensional space, to get some kind of a map, you get only a few segments. This postal algorithm to choose k-segments are that things will repeat themselves over time, so the projection will be a simple map. This is a much harder problem, but fortunately, this is the standard query. The candidate set of query is still k-segments, so we can still use the same coset. It's a very hard problem on the small coset using more sophisticated algorithms and heuristic. And again, solve the problem, and you're still getting these maps when you have a lot of lines that represent the same space, we have the constraint that the projection must be on two-dimensional space must be few lines, and we get much nicer maps that represent the data. And again, now when we have big data, we can run it on Amazon Cloud and MATLAB and using a lot of computers. This was published in JS with Simon and Daniela Ross. And in practice, in our database, what we have now with the GPS is that the original data is just X, Y, and the time. But in the database, we have the K trajectories based on the M popular point that you usually visited. So for each point, you have the segment, or if the same place, the endpoint and endpoint are the same with the letter. And now the trajectory is just a set of letters which segment you visited in each time. And now we can go, for example, to Google API, Google Maps, and ask for the names of these popular places that I'm going to. So every time I visit Starbucks, we still recognize that it's Starbucks, and we don't need to ask Google Maps, which have a very limited query time, queries per day. Only for the popular places, we ask Google once, get the text, and edit to our database. I will skip to the open question because I have only 2 minutes. So we still don't have process for a lot of famous problem machine learning. Deep learning, for example, is one of the neural networks. We have some process for SVM, but I think we can do much, much better, especially for high-dimensional space. Too few implementation. There are some implementation on the web. I hope to change it in the next year. But we need more practical people that actually test them and evaluate and maybe have more information on how to tune them. What I'm trying to do these days in University of Firefly is trying to have courses for more practical application. We start with the system, with the robots, with the Tensor, the live logging, try to understand what is the right problem that you want to solve, and then have courses that is not based on the problem of the theory people, or the people from statistics or machine learning, but actually on a real life problem that you want to solve. And more people that come not from computer geometry and maybe from the practical application that will help us with this suggest courses would be great. Another very interesting direction is private courses. In the same context of live logging and Tensor, we have one paper about private courses based on differential privacy with Hein Kaplan and Cognitium and Amos Fiat. And we were able to prove that unlike in differential privacy, you're allowed to ask few questions and then you won't be given any answer to preserve the privacy of the people, and the question and answer are also quite noisy with a very sophisticated crypto way. The nice thing about Corset is that they give you the private Corset once. It's a noisy database, but then you can run an infinite number of queries on this small compression without losing more privacy in every query. This is making much more sense in practice for people who just want to get noisy database and work on it, and don't want a machine to ask queries that it will stop responding queries at some point. But unfortunately, we have only Corset for K-means problem on low-dimensional space, not for subspace, not for SVP, not for high-dimensional space, and a lot of work there. Also, the implementation is a bit tricky. Unlike in non-private Corset, we just sample points until we're happy. We don't care about the theory. In private Corset, we usually actually want to guarantee the security, not the practical fact that we have good Corset. So it's hard to take small samples. We don't have Corset for active learners yet, to the best of my knowledge at least. So when you don't get input on the fly. And another problem is that when I give all these kind of strange counterexample, I use strange sets. But in practice, you usually have very specific type of inputs. Do not behave like the crazy counterexample in the theoretical papers. And you might want to ask, suppose that I don't want to have Corset for every set P in the world, but I have some assumption that it's well clustered, it looks like this. This assumption might help you to have Corset for the case where in general we cannot have Corset, maybe for the problem assessment, or maybe for a lot of graph algorithms. If you assume something about the graph or data, maybe you can have Corset. Then in general, for every set of input points or vectors under the sun, we cannot have. That's it, I think. I hope you like it. I really enjoyed these talks, and I'll be glad to hear ideas about a new Corset from you an email or later today. And I have, I think, a few, about 2 hours if someone still wants to meet with me I'd be glad to before I leave. Thank you very much.
We're going to hang out here for a few more seconds. I'll sort all the questions I'm moving out. Don't go anywhere just yet. Okay, so the first most important thing of this meeting here is
Actually, why don't we all go to the front?
the front. Okay, Mallory, come on.
So, yeah, we don't know how many people will still be here in the afternoon.
video actually.
But basically,
It's on the broadcast.
it's on the broadcast, so it'll be preserved for eternity. But
Great.
first and foremost, besides what we already said yesterday, I really wanted to thank Mallory, because without her, a lot of this would have been very chaotic, and she helped keeping things very sane. At least a lot more sane than they would have been otherwise, and I want to thank her a lot for that.
Oh, thank you. Thank
And
you so
so-
much. It's been a lot of fun getting to know all of you, and it's always nice to have people come to your hometown and say they like it, and what, and not, say bad things about Pittsburgh. So it was nice meeting all of you, and these guys do great work, and you guys all are going to do great work, and I hope you enjoyed your time here. So thank you, everybody. Thank you, guys.
I know the district thing, so I did it this morning, but Mr. Kozol is partial. Then the two lectures that are swapped. So Marcus is going to be giving a tutorial from 2 to 3, and then Andrew will be talking from 3 to 5. Other than that, though, we'll see you in a few hours. Is there anything else with that?
Well, we'll send out an email about the questionnaire, and it would be great if you could give us feedback. And yeah, sure, it's of course great if you say you loved everything, but I don't think you probably, it's very unlikely that you liked everything to equal amounts. So giving us feedback will actually help us do a better job next time. So, just like on Netflix, you can say, well, some things you like less. Please do so also in our case, such that, feedback helps us. Okay, so thanks.
I have a question.
Yes.
Yeah.
Why do you choose these topics?
Why do we choose machine learning?
No, I mean each individual topics or speakers.
Well, okay, so first of all, we picked people who we thought were great speakers. So, and I hope you all agree, and well, let's give a round of applause to the speakers who are still there. The second thing is, well, we wanted to have somewhat of a focus on scalable algorithms, and that's what, prompted us to also invite people who had some experience in industry or who come from industry to talk about specific things, or that's why we had those 2 tutorials. So, we could have done a theoretical summer school on learning theory, and there are such summer schools, and if that's what you would have wanted, you should have attended that, basically. But the point is, each of the summer schools usually follows a more or less common theme. And this time we picked scalable algorithms and big data. Okay. Any other questions? Okay, then thank you very much, and let's have lunch, and let's be back at 2 p.m. Thank you.
So I'm going to say that one.
Yeah, that's okay. I'll take it. But I'll actually have to
Well, yeah, I'll intercall.
I think it's better in Irvine.
Yeah, I just wanted to
no,
check because you said last night.
No,
I just wanted to make sure.
No,
Yeah, I know you.
No, it's just that.
Right, like, you know, on board, so you know how to walk out.
Lucky you. So you speed is like a basket. You need to kind of send it for. There's like a website. This is but if you have any questions with you, it's better to
Data set.
Go to for lunch with the guy at the warehouse. I would ask you, like, he's an engineer, he wants to be a priest. He actually wants to talk to you.
我知道，但是你这个你是表示的什么意思？对呀。我觉得你还是在那个方面，如果你是要的 matrix 是什么样的 information， 是diagonalizable， 你 general 的话就比较困难，因为你 general 的话，你不知道它是一个东西。比如说，你知道你的 matrix 是那个 diagonalizable， 但是问题是说你要 diagonalize 那个 matrix， 不需要 optimize。是一件但是对 matrix 的话，是为止的，因为有些事情可以说用粗的加更高什么，但是其实要把这个 output 算出来的话，也是到最后可能也要做这种非常累的事情。不过我觉得你这个 approach 还是那个用困难，因为你比如说你想用这个 graph reasoning 的话，那你还知道你的 graph 是什么样子的，你不知道你的 graph 是什么样子的话，你不能说你根本不能有任何的结论。就是我的答案就是说一起看，就是说看你的 data 是什么样子，看你的 matrix， 看你的 graph 是什么样子。在有些情况下，你肯定是有非常多的算法，但是没有这样子的是绝对是没有这样子。
我觉得有些人
对，
但是我只是不知道它体现在哪。
可是你现在是不是你现在算的是那个 trace x， 这不是这样子。
但是这肯定是这是那个我这些算法其实不仅是它的这个结构，
他不想要求别的位置，不需要。
对，我只需要它确实再问另外一个问题，就是说，
那我想想啊，那你就得先把你的 matrix process 一下，你是不需要。
They really are going to think that everything people always complain.
我的那个
那个完全不是，那是完全就是那个，比如说你那个 word sort， 对吧？就是你 word sort 就是那个 word sort， 你们找一个什么到 log， 就是因为就是 algorithm 上面的 algorithm， 就是说数据收集，对不对？如果是 matrix 分块的话，它其实是这样的，也是 matrix multiplication， 只不过是它是这样的。所以它不是一大块，它是一小块小块的成分。然后呢，比如说你的 final product， 你知道这一块应该是打一个应该是这个什么这个。如果你需要这个的话，maybe 如果你是需要 diagonal 的话，你就先把这一块是应该是这个乘以这个，对，然后这一块是这个乘以，是这块是这个乘以。如果你不需要乘以块，就乘两次就行。就必须是一块，但是这不是 这不是数学上的，就是考验。但是这个话你马上如果你真的是要求这里，你实在要整个的 matrix 模块啊，它是要 IT， 那不管怎么样的。但是如果你只需要 diagonal 的话，就可以，就是你可以把它。
也不需要那么复杂，所以已经有算法，就有很多人研究这个问题，这是一个很著名的猜想在这个问题上面。
那可是
做了几十年了，
可是那你不要求每一个位置上的东西。
对，那个是 n 的2点，现在最高的是一个 Berkeley 做的是，现在就大家都拼到小学，然后后面很多位了，就是比如说我做2.5321，学做2.5322，就是这样的，就是 n 的这个。
就是稍微好一点。
对，但是你们可以直接说，就说理论上这里是应该快，没有软件
对，而且就是有些你要说的话，其实它那个它里面有些东西，它是在最 low level 或者是 high level 的那个 optimization， 比如说那个人讲的就是那个 space optimization、time optimization。
看一个你不好意思耽误你那个就说其实也是一个特别的。就外面的讲里面很简单，我举了一个最简单的例子，但是我的问题不是这样，但是差不多可以这么理解，就是说你其实就是一个，比如 CI 是一个常数吧，e 从 C1 到 Cn， 然后 x 比如说也是就是你的 eta， 然后你也从 x1 到 xn。然后你就是 leader， 对，它也是一个 fermentation， 对，它是一个 symmetric group， 对，然后呢，我其实就要。
你应该是那个 I 是什么？
对，
不是 X。
我这里只是一个 leader， 它是最关键的在分母下面，最讨厌的在分母下面，然后外面呢，我是一个对所有的分别的要求。这个怎么算？是怎么算的？
这个
我们不知道呢，这个
但关键是分子上面，如果它在分子上面就非常容易，就说其实它太复杂，我也可以用 action 把它分成 orbits， 然后分成 orbits 来算，那就比较容易。但在分子上面有个最大的问题是这两个不能交换位置，这两个小类不能交换位置，这样也很难。
但是你这个不是一个非常简单的，你就是说在说 root theory， 它你可以就是说没有简单的答案，但是一定是有就是说你可以把这个回旋头，然后呢 rewrite， 然后呢变成一种可以用那个 orbit， 然后来 orbit stabilize。就是你说的那个可以用 Factorization 来算，就是 orbit stabilize， 就是说那个 orbit stabilize 就是把那个 root 的 cardinality 跟那个 set 的 cardinality 是放在同一个公式。你想用的是哪个？一般来说我们用的都是那个，或者是 class equation， 对吧？但是你这个的话，对，最主要是在底下，但是它里面就需要一些 algebraic manipulation。
但是你看我觉得很难把它弄出来，就一旦在分母下面，
需要一点 patience， 但是它没有
这里有什么方向？有什么书可以看吗？
可以看，你是有书，但是要自己去做，你要就比如说是你要就是没有那种，它不是说所有的问题的话都有一个答案，你告诉你就怎么做。如果这个是有快速的算法的话，如果可以用 orbit stabilize， 你去查这个 orbit stabilize。
对，我知道 orbit stabilize， 但是我在分母下面我就不知道怎么用了。
然后你查的，因为它后面有很多一大堆的，因为它是这个名点，它那个有很多的 corollary。它就是那个 theorem 的话，你用 theorem 的时候，你不光要看它的那个 main presentation， 还要看它所有的 variation， 因为有些 variation 的话，你看起来跟那个 main theorem 一点都不一样，但是其实就是一个，所以一定要找它的 variation， 就是找它的，然后找那个
没有什么特别书讲这个。
你任何找一本书就是比较
就是abstract algebra，
对，一定要找什么那个 group action、group theory， 然后找那个 class equation， 然后这方面还有很多那样的那种非常。
我看你好像以前做过 group action， 我昨天查你的那个网页是吧？
不是那个是非常非计算的，对，非计算的。但有很多人对这个很感兴趣就是特别是以前有很多，现在不是非常好的一个 field， 就是他们算出了很多不同的 formula， 你知道吗？就是内 stabilizer 和 class equation 就用两个 theorem 可以里面就是套出一些非常多的 formula。但是你比如说你随便找一个 formula，这样然后你问我哦，这个是怎么比那个把它重写成段？对于我来说，你就是先找一大堆 formula，然后看哪个跟它最相近，然后自己慢慢做。那只有这样的时候。
就用 vocal 用这两个关键词去找。
对，你不要找那个，就找对，最那个最好的 practice 就是那个比较型的本科的那种 class group action 是其实，因为它深的话，它不会对这个气团型的东西认识是不的，是那个比较那个给 graduate student 看的书，或者 research 看的书，全都是 theory。
对，我有一本 group action 的书，这个看几张就看不下去了。
你找他的，你去找那个 class equation 的那个organ stabilizer 的所有的，它会有一大堆这样的。然后你的对，慢慢的细细的去推，对，对，你的是在底下，搁到没有关系啊。
No, yes, go ahead. Tensor. Tensor.还得用来分钟，为什么？下来。 我去加入一方案。
对啊，所以还是我做 Hybridizing，
难怪这里的好像。
对，挺相关的，大家也知道，但是用的肯定没有他们本身专门搞这边的人去深入。对，那是 geometry Hybridizing，另外一块。那你正常你要 application 的话，你就各种比如说 object detection、recognition 是吧 ？segmentation 啊，这些都是用过这边的。那主要是这块就是比如说你 sphere 两个 camera 你怎么算，你怎么恢复它的那个3D图形？
把这些配色的时也当成是个原始词或者怎么的模仿，是这样吗？然后你一个图片上面有几百乘几百的配色，然后你或者把它分成一个 vector，或者是
对，一般是 Factorize 变成一个 vector， 就是一个 feature， 把那个把 feature，
然后做这个地方。
对，然后或者是很早之前的话，他们都是 feature engineer， 就是各种design各种 feature， 然后用一些不是那么复杂的方法 ，back and word 或者是简单的方法去做出来，这个 application， 对吧？那现在的话，现在越来越有这个趋势，你不用什么人工的这种，整个把一个图片扔进去，它自己去。这边的就是它叫 feature learning， 对吧？
那你们说那整个是不一，
主要是跟这些都不一样。主要是的话，它是研究那些计算的，数值计算的，就是你去比如说你尤其那个 sphere 你怎么去 calibrate 这个 camera 参数，对吧？给你一个图像，你拍2个照片，然后你用图像上的这个信息，你怎么去把这个 camera 的3D 位置，然后它那个 focal length。这些参数，这跟本身人没关系，这是geometry的更有优势。对，这块的话，很早以前，computer vision 的人做，现在基本上做的很少。
现在是不是都做后面这个？
现在都做这个应用层面，对，就是 classification 这些，对，现在做这个主要。
3分钟。刚才那个看那个什么，那个家伙不是说是 Stephen Wendell， 不是什么那个 Libre FM， 是什么？Libre FM，Libre FM就是Factorization那个然后你知道Factorization要讲什么？Libre FM， 然后我之前知道这个东西，因为我之前老板参加开发这些时候就拿Libre FM去了1点。然后扔到人 force 里边，然后拿个第1名。但是我不知道这个 FA 就是那个今天说那个 Factorization model。然后刚才看了一下那个人主页，上面说这家伙立刻那个 FA， 那个叫什么？那个 FN， 我的是 Factorization， 对。那个叫什么？那个学早，那个叫什么？Randall 是吧？是叫 Randall 吗？这个你学看这个。就是那个 Steve Randall。他那个节目那个叫什么？就是可能他第一个买这个孩子特火，我不知道是孩子特火，我老板是看见小问题。他们当时做总编辑也是一个能力学，也是一些现在这个东西，这个还比较有趣的，就是现在还有一个 Max 和一些上面这可能是你们选择的身上，可能可以看这个。
是靠接受。
它这个可以把
跟 ophthalmology 结合的。啊？哦，对，是吧？ophthalmology 本来是那个领域啊，好像是那个一会儿没去过的领域。class 2。有人营销嘛，这个就是围绕我这个。
下午一个没啥，这个把行李都拿过来。 我很想问你们电话，我要是有这种经验，它有什么一个弄？说前一个弄一件。我觉得电话我做的还不好看。你想把我的这些塞在哪？上次。整整整理好，把那个东西写出来。上步骤有个学科会。 Pero voy a intentar porque estaba haciendo sobre mi cerebro, pero que corre con el coche, voy a correr los manos que no puede ser este. Es que para mí tienes que hacer muchas cosas para que salga el imagen, no puede ya lo recuerdo. Porque el madre no lo puedo conseguir, porque está haciendo sobre eso. Voy a intentar sobre el coche.
Yeah, some of those I haven't uploaded all of them yet.
que potencialmente no, desde el 3 para el, perdón, para el nivel 1, No, la de software. Oye, tú, ya que estoy saqué los videos y me pongo una duda. Entonces, ya que no sé. A ver, entonces tú como una de no de básicamente preguntas como es mandarme como que destacan los textos.
Put that somewhere where the camera doesn't see it.
Your back. Yeah.
You want full screen, right?
Yeah.
Well, not to chalkboard only.
People do, right? That's the
People
thing.
do. I mean, in programming languages classes, right?
And in interviews,
Oh,
you
yeah.
see the code on the board and say, how did that?
Hopefully, you're not make any mistakes when it goes on the whiteboard.
So I'm all set up outside this kickoff, but that means I won't see you again, so.
Well, probably you will at some conference, right?
I'm sure I will see you sometime. But
Not here.
well, no, here it could be too. Maybe you'll be back in Pittsburgh.
Yeah.
I think it's more likely I will see you back in Seattle. Seattle, I will, don't worry. I am in Seattle, I will, send an email.
And come and give a talk and all that.
Yeah.
The usual academic visitor routine. Okay. Cool.
Yeah. Oh, you
Hmm?
So we're doing some what? Credit transfer. You by credit? I mean, you have to take that up sort of with the school, whatever school you're at. Because it's not an official course run by CND, right? It's just a course that we put together. But I mean, doing like academic credit. So I'm guessing that's going to be actually hard because there's no like graded assignments or anything for it. It's just lectures. And so I think it's going to be kind of hard to get any sort of official credit for it. You could check it out, pick it up with your school.
Well, when you're school. Oh, that's fine.
You can ask your advisor.
You forgot to do
kind of study, but I think that's going to be
You did, but skip T capital. But I don't really know why you left here. No,
Which group is this? What did you say?
Oh,
Okay, can you just send me the email right now with the group numbers and the name? You can look, right? I can do it right now. Yeah, I can try, well, I can try to do it right now, so you guys can see it right now. But send me right now an email with your username. Make sure it's the right email address. I don't know what you think.
Yeah, we need to do you have your own thing?
Yes. Just send your own.
On the platform, right? It's not from that one, but even on Linux, Java is sometimes different ones. Well, Java has the variable is there, but it points to different locations.
Alright, Marcus, you're all ready?
I'm all ready, is it?
No, take your time.
I have a minute.
But I'm gonna head up, so I will see you back.
Take care.
Happy video, the microphone and everything, you can get that, and we'll do the sound check and everything. I think that one's already started.
The camera is already started?
I think this is already started. Ready, was going already?
This one's I'm already on TV, okay.
Yeah, but I think there are 0 viewers, so you don't have to worry about it.
Does it say how many viewers there are?
There's 1 viewer now, look at that.
Hello.
Whoever that
Nice to
viewer
meet you.
is. Alright, so I'll see you, I guess later. Or is it done already? No, this is your email that you yeah, so it's just whatever email you do that email and you have it.
Okay. We'll give it a few more minutes. While we are waiting for the remainder of the audience to show up, I will have to run at exactly 3 o'clock, because that's when I'm picked up to go to the airport and hopefully make my flight. So if you have any questions now or through the talk, do not hold them back till the end of the talk, because I might actually have to cut it very sharp today. So if you have questions now or also during the talk, I can address them in line and then still adjust my talk for time. Okay, I think it is safe to start. But does anyone know about their friends still being out there and coming back from lunch? And it's the last afternoon of the summer school, so you never know who has to take a flight early. Okay, today the title will actually be true. So today we will actually see some resource-aware machine learning built on top of Reef. Different from the last 2 or 3 days. I will not have time for execution of stuff on your laptops. I will show stuff on mine, and I will update the slides after this lecture with kind of pointers to it. And we'll keep the cluster running till Sunday night, so that you can try things by yourself, at which point we will have to shut it down. Speaking of which, someone, probably from this audience or maybe online, submitted a job that required 8,000 containers, someone yesterday. That, of course, will never execute on a cluster with 1,000 containers maximum, and it just sat there, right? That's the reality of resource-managed clusters. You can ask for whatever you want, and then if you require that you get it all in your job, then you will wait for a really long time. Right? So we had to kill that job, obviously. Right? Whoever submitted it, I'm sure it was doing good things like Bitcoin mining or something. But we had to shut it down because it was clogging up the queue for everyone else. It was sitting literally on all of the containers, taking up all the CPUs, and waiting for 7,000 more. Okay. Quick recap of what happened so far. On the day 1, I was talking about how resource management is happening, how
pricing will enter our algorithms at some point when we take the cloud for real and not just as a big cluster. On day 2, we spent a lot of time compiling and running Hello Reef on your local laptops. And I believe at this point this has worked for everyone. So that's great. So you're all set to try things on your own. On the 3rd day, we submitted things to HD Insight. We ran things on the cluster. And by example of the guy who took, or girl who took 8,000 cores off of the cluster, this seems to have worked very well for at least a few of you. I introduced Tang and kind of how configuration is handled within Reef and why we believe it's better than other distributed systems. And I talked about context as a way to hang on to state within your application or within your evaluator. Yesterday then, we kind of shifted from kind of basics of distributed systems and how Reef helps in that space to more machine learning things. I introduced the group communications library, which provides 2 operators that are relevant to this lecture. One is broadcast, one is reduce. And we've seen how you could implement a basic batch gradient descent in Reef. Now, of course, this batch gradient descent is not the most sophisticated algorithm. And I want to show you how you can expand on that and make it slightly more relevant to actual optimization. And we're going to do so by adding line search. Has this been covered in a prior lecture? Who knows how line search is done? Oh, a few. That's good. OK, so remember the algorithm. It was this very simple algorithm where we start with some random vector of weights. And then until convergence, we compute a gradient over all of our data points, and then apply that gradient to the model to make forward progress. Now there's this parameter eta down here, where we really don't know how to set this, right? I mean, I just skipped over it in the lecture yesterday, and if you set it too high, then what will happen is you jump to the wrong side of the function all the time. If you set it too low, it will take forever to converge. So you will always have this problem of, hey, there's this parameter, and now I have to tune it, and it will depend on the data set. Of course, real optimization algorithms don't have the problem of not converging given a different data set. So here's how they deal with it, or one way to deal with it. First of all, why is it not a constant? I mean, most of you will just know this, but I wanted to go over it anyhow. So if you take a plot of the objective function, where you say the y-axis is the objective function, and the x-axis is all the possible w's, and of course, right now, this is only a w of dimension 1. It's not that exciting. In reality, it has a couple of million dimensions in our case. Now, there's obviously a correct solution that you want to end up with, right? The one that minimizes your objective function. Let's call that w star. And up to my drawing abilities in PowerPoint, it is at this point. Right? Could be a little bit to the right now that I look at it, but let's just say it's at that point. Now, what our algorithm does is it computes a gradient at some point, and let's just say up to resolution, this is a gradient, and then does a step along that line. Well, the optimal step in this case would obviously be the one where you go all the way to the optimal, right? You have your descent direction, just go straight to the optimal. And if you do Newton's method or any of the methods that depend on a second derivative, you have an exact way of figuring out how far you shall go. Trouble is, a second derivative is really expensive if you have lots and lots of dimensions. And it's especially expensive when you have to funnel them through a network connection. So that's not really an option. OK, but in this case, you end up with this eta 1. Let's say you look at another point, you compute your eta 2 there, and you would end up with a very different step size. Right? That's just the intuition why it's not a constant. Why can't you find the constant for a data set? Even with one data set, your function might look like that, and then you're somewhat screwed if you take a constant. So now, what is line search? Line search is quite literally what the name says. You have a line. You know that you make progress if you follow that line down here. So let's try to find the optimal point along that line. And of course, we evaluate then the function at these points and choose the optimal. There's any number of algorithms in the literature on how you would go about finding those evaluation points and in which order to evaluate them and all that. That is all very relevant when you're on a single machine, right? Because each of those function evaluations costs you time. Each of those evaluations that you do that you don't actually need costs you unnecessary time. So, of course, there's literature on this. in the distributed setting, the whole cost structure changes. And evaluating one of these for you means that you farm out a model, a point at which to evaluate, which costs some communication, then compute on all the various slave nodes that you have in your cluster, and get back the function evaluation. Whether you do this with 1 point, or 100, or 100,000, the cost is about the same, because the majority of the cost is distributing the model and getting the result back through the network. So different from single machine execution, where we have to be very smart and clever about how we choose the points at which we do the line search, we get away with just doing brute force. This is kind of one of the more interesting aspects in distributed learning, that you often get away with doing brute force, simpler algorithms, because you have more compute and other overheads would shadow whatever you could do to be smart. So how do we do this in brief? So we have our typical setup, and the master broadcasts the model to all the slave nodes. That's the first step. We cannot avoid that because they all need to have a model. Of course, if this is truly the first step, then we can just initialize the same model on all machines with the same random seed, and we avoid the broadcast of the full model at this stage even. And we will see that the master will never have to send a model after this time. Now the slaves do what they always did. They compute a gradient and send it back through the reduced tree into the master, which now has the gradients. So the master then goes ahead and computes a descent direction. Right? In which direction do we want to search? And it computes and it prescribes a pattern on that descent direction. Right? You don't have to actually enumerate all the points, as long as you send the descent direction and some description of in which factors you want to evaluate. So this can be broadcast very efficiently. It's essentially a gradient plus some grid definition, a few bytes at most. So this is as cheap as broadcasting a model. And now what the slaves do is they evaluate the loss function that they have on the data that they have on the points that they have just been set. Right? Because they know the descent direction, they still have the model from the initialization or from the last iteration. They can compute all the W's for the various points that the master wants to evaluate on, and then can go ahead and compute the loss function value for that. They stick all of this back into a vector and then send it up the reduced tree, which again is very efficient because for each point you have 1 dimension, and our model is already 1,000,000 dimensions, so we probably get away with having 1,000,000 possible points along the line search direction to evaluate. So they send this up to the master, which uses this information to compute a new model, to find the optimum point along the line search where the next W shall be evaluated. This doesn't have to be a W star, obviously, right? But it is the best of the ones that have been evaluated. Is that a question, or is that just recovering from last night? Okay, it's recovering from last night. So the master computes a new point where things shall be evaluated. Now, naively, the master would go ahead and broadcast this new model to all of the slave nodes, right? Because we now have a new model, just like in gradient descent, we need to broadcast this. But different from the beginning of the gradient descent algorithm that I showed yesterday, the slaves have all the information they need, but one. They know the model, because that hasn't changed yet. They know the descent direction, because that has been broadcast to them for function evaluation. And the only thing they need is how far to go along that descent direction. So this broadcast at the end of this iteration is very small. You just broadcast the step size to all the slaves, which can then go ahead and enter step 2 of the algorithm again. They now know which model to evaluate next, and they can go ahead and perform the next iteration, compute a gradient, send it to the master. The master sends the descent direction and a pattern of line search to do. They evaluate that, and the cycle continues. So this is a case where this seemingly very bad approach of going ahead and saying, hey, let's just evaluate 1,000,000 points along the gradient is not that bad in practice, because any alternative where you kind of try to have some centralized logic that figures out which points to evaluate would require the master and the slaves to communicate more often, and each of those communications incurs a latency, and that is just completely that completely dwarfs the latency of just saying, hey, let's evaluate on a million points and get the results back. Okay. You're awfully quiet today. So, what we probably do at a later time, no, we will do it now, is I'll show you the code of this. And I put the kind of package name where you find all of this code onto the slides, such that if you want to look at it after the lecture, you can find it. Now this is where a little bit of hackling with computers is involved. Now you see what I see, correct? Yes. Now let's open BGD. So this is in the package simple line search. It has the same structure. It's actually started as a copy of the simple BGD from yesterday. It has all the same classes and all that. And we didn't cover all of it yesterday, so I want to cover at least a little bit more today. So remember in the BGD driver, which is the job driver for this learning task, you do this. Yeah, that's the style where you can see it. What we now have, remember we used to have these three operators. One to tell the slaves what to do, one to broadcast the model, and one to reduce the loss function and the gradient band. Now we have a few more. We still have the one that tells the machines what to do, the control message broadcaster. Then we still have to broadcast the model every once in a while, right? Especially at the beginning. We didn't, for sake of simplicity, didn't implement this optimization of just broadcasting a random seed at the beginning. Then we still need to reduce the loss and the gradient, right? All of these are still there. They're still the same setup as in yesterday's version. Now, we have an additional broadcast to broadcast the descent direction, right? We want to broadcast, hey, this is the point, the direction in which we want you to evaluate the function, and these are the step sizes along that. Then we have an additional reducer, and that's the reducer used to reduce the outcome of the line search. The actual reduce function is very similar, right? It sums up the values in all the dimensions of the vector. But in order to make things more clear, we gave it a separate name. So this is the line search evaluation reducer. That's where all of the slave nodes in the step where they have a descent direction, they evaluate on all the points. They send the outcome of that computation into this operator, which will then send the outcome of it to the master task. The last one that we have to have now is a broadcaster which broadcasts the ETA that we want to use at the end, the step size that we want the slaves to use in their update. In the old version, we just broadcasted the model. In the new version, we don't have to do that anymore. We instead send a single float across the wire, which is a lot faster than broadcasting the model. It still takes some time because everything on the network takes some time. Okay. Now, let me get out of this and show you how this master task and slave task actually looks like. There we go. So any questions on this setup of, whoops, we are in the wrong code base, right? Yeah. Everything clear? Or everything so unclear that you can't formulate a question? Okay. Okay. So the master task, and we didn't go over this yesterday with the simple batch gradient descent, so I want to spend a little time on that. The master task gets, again, everything in Reef is accessible through constructor parameters. It gets the group communication client as one of the constructor parameters. That's the only one that really matters here. The other ones are named parameters for model dimension, lambda, and iterations. So it's not that interesting. Okay, what we do is, on this communications client, oops, why can't I? Okay. On this communications client, we grab all the relevant operators in their local representation. Remember, we are in the master. So this broadcaster that we keep in a variable is the sender for the control message broadcaster. Sorry that I have to scroll through this, but the alternative is to make the font very small. The model broadcaster is, again, the sender for the broadcaster that sends, right? we will see in the slave task that they have the opposite calls. They get a handle on the receiver of those broadcasts. And the sender has a send method, and the receiver has a receive method. I mean, it's fairly straightforward. Loss and gradient reducer, here it's the receiver, right? Because we want the loss and gradient to be received by the master task. And so on. We do this for the descent direction. There's a typo in there, broadcaster. We do it for the line search evaluation reducer. This is again the receiver, because we want to have the evaluations of the line search sent to this node from all others, and the learning rate broadcaster at the end. So remember from my very first or second lecture that a task is essentially something that has a call method. So Reef will instantiate the task and supply it with all the dependencies that I declared as constructor parameters, and then it will call the call method. The call method in this case, first of all, has a for loop, which goes over all iterations unless converged. Right? We have this helper method here, which checks whether we are converged or not. And while we are not converged, we just continue. Now, at a high level, what we do here, so this might be helpful to some of you who are Java programmers or aspiring Java programmers. We play a trick here. Everyone else just not listen for a second. Java has these try-catch blocks where you can put something that's closable into the brackets of the try, and it implicitly calls close when you exit this bracket. We use this in Reef a lot to get timers. We just put everything into a try block with this auto-closable inside, and that will automatically log the timings of things. Often in distributed systems, you want to know why are things slow. Then you discover that it was that one node that was slow, and then you want to figure out what in this node was slow. So that's why we use these timer classes, which say, hey, we are entering iteration number, and then we know when this iteration started and when it stopped. Right? We can get really nice printouts of the timings through this. It's a very neat trick that the Reef development team on the product side of Microsoft has taught me. I like it a lot. Back to the machine learning part of it. So what we do here is we compute the loss and gradient, and I can show you that method in a second. It basically broadcasts the model, gets the gradient back, and all that. We store the loss. It's a pair of a loss and a gradient. So we store the loss in this losses list, which is the one that we keep track, where we keep track of how we are converging and all that. Then we compute a descent direction, obviously, and then we update the model with that descent direction. So far, so straightforward. And then we update the gradient norm, which we use for the convergence criteria. Right? We just say when the norm of the gradient is below a certain value, then we can stop because there's not much information in the gradient anymore. Of course, again, this is a very simple form of a convergence criteria. Right? I'm pretty sure that other lectures during the last 2 weeks have covered much more interesting optimization algorithms that do much smarter things here. Okay. So, do we have, yes. And at the end of it, all it does is, so this is the exit of the loop. Right? So the loop started here where it's highlighted, and this is where it ends. We just put stop onto standard out to see, hey, we are done. And then we just send to all the slave nodes that they are also no longer needed. Right? We use this control message broadcaster and send them a message which says stop, shut down. Right? And then they all shut down and life's good. And then we print out the losses. Note that crucially, in this particular learning algorithm, we never store the model anywhere. That's due to the fact that this is purely an example. But of course, you have the model, right, and you could write it somewhere. But more interesting for an example is to see what is the actually, did we converge or not, right, and in which rate. And then we encode this losses list into a byte array and send it back to the master. To the driver. This is the master task. We send it back to the driver. The driver will also print it out. So when you run this algorithm on HDN side, in the log file of the driver, which is typically the container with the lowest number, because it's the first one that gets started, you will find a printout of a couple of floating point numbers, and those are the losses. Okay. Now let me quickly, because we are already approaching the half point, look at compute loss and gradient. And again, this is all in the one package that I mentioned on the slide, so you can browse this at a later time yourself.
Again, we do this timer thing. Skip that for now. So there's a little bit of code here, which I can quickly introduce. This is already a version of the code that it has some fault tolerance in it. And if one of the slave nodes fails and comes back, this whole trick of never sending the model again doesn't work, because that guy doesn't have the current model. So we have a handler here which gets informed when there are any changes in the topology, and then it says, okay, the next time I do a broadcast, I'm going to broadcast the model, not the descent direction. Right? That's why there is this if here. We can focus on the else. I will talk about fault tolerance for the second half of today's lecture. So what we send out, let me check. We send out to all the various machines. So we want to compute a loss and a gradient, right? And we must assume that they all have the model already. So what we send to them is, hey, we will soon send you an eta, a step size, and then we want a gradient back. That's what we send to the slave nodes. And then the slaves, and then immediately thereafter, we actually send that eta. Right? And the slaves will answer with that. And this is done in the next line, which I unfortunately have to scroll again. So this is where we say, close that. My phone just told me that I need to leave for the airport. If you look at this line, this is the call where we actually get the results back from the slave nodes. We just told them what we want, and now we sit here and wait for their outcome. We just go to the loss and gradient reducer, call reduce on it, which will block. The program will stop at this point until we have all the outcome from those machines. Right? So this might be one line, but it might actually take a minute or two to get an answer back. And then we aggregate that, and we scale it by the number of examples that we've seen and all that, right? The usual math that you have to do such that it's an actual gradient and loss, and then we return that. Right? The other methods perform similar kind of mundane tasks that are fairly straightforward. I want to quickly also show you, once I figure out how, and it jumps to the wrong window again, the slave task. That's the one that sits on all of the various machines and computes things there. Presentation mode. Again, in the constructor, it gets a group communication client, just like the master task. But what it does with that is it does the exact mirror image. So for the control message broadcaster, it gets the receiver. For the model broadcaster, it gets the receiver because it gets the stuff sent to it. For the loss and gradient reducer, it wants a sender because it wants to send losses and gradients up the tree, and so on. Right? It's the complete mirror image. Now, in the call method, we basically sit and wait forever until someone tells this task to shut down, and that's the stop variable. The first thing that we always get in every time something is asked off of the slave task is a control message. Right? There was the stuff where we sent to all of the slaves, hey, we want you to compute a gradient, we want you to update the do a line search or whatever. Now, the control message, there we just switch through, right? In the case of stop, we shut down. That's the behavior that we want. When we do compute gradient with model, we know that the next thing that will come in will be a model, so we sit there and wait for the model to be broadcast. And after that, we compute the loss and gradient on the local data and send that up the tree in the reducer. If we are to compute a gradient with an eta that is being broadcast to us, we receive that, and then we scale the descent direction that was sent to us beforehand, and update the model with that descent direction. Right? These asserts are such that we must assume that someone has sent us a descent direction before, right? Because if no one sent us, if the master didn't send a descent direction, then really bad things will happen. And also, we must have a model. And it updates the models and doesn't update. If it does, if we get a do line search message from the master, we receive the descent directions, and then we evaluate these. Right? There's this line search evaluation method. And they are all local methods, so they are fairly straightforward code. By default, we do nothing. Of course, this should never happen. And eventually, we just return null in this task. because this task doesn't produce any outcome on the control flow channel of read. Okay. So unfortunately, I won't have the time to go through all of the code, but I think this gives you kind of the entrance point where you can start browsing, right? You can then control-click on these various methods, or whatever your IDE uses for jumping. You can say, okay, I'm interested in how these line search evaluations work, and you can have a look at that. Right? Okay, back to slides. Any questions? Okay, I'll just assume that I make enough sense that there are no questions, and not that I make so little sense that there cannot be questions. You're still laughing, so you're still listening. That's good. Okay, now, we started this lecture series with, hey, we want to make machine learning more elastic, right? That's been a bit painful along the way, but the last half hour of this 5-hour lecture, I want to spend on that aspect of it. Because we now have all the bits and pieces to at least do something elastic with, admittedly, batch gradient descent. But you have heard enough other algorithms, and if you connect the dots, maybe you come up with something cool to do with other algorithms in this space. That's my personal hope for this lecture. Okay, let's first talk about a few assumptions that we make here. Because if we assume a real system, this will again be a 5-hour lecture. So let's just assume a few things. So we only consider slave task elasticity in the following. We do not assume that any evaluator could fail at any time. Of course, that is true in practice. In practice, the master can fail, the driver can fail, everything can fail at any time. Also, all but the driver can be preempted. So Jan doesn't preempt the driver because, well, that's your application, but any other node could be preempted. We don't deal with that for the rest of the lecture. And we could have upwards elasticity in all the containers. If you think about truly huge models, you might not want only one aggregation tree to compute the loss and gradient sum, but multiple that end up for different halves of the vector. We don't consider that either. We make our lives easy. The other thing that we assume on the slides, the code that you have in this MLSS GitHub repository actually supports this. On the slides, I'm going to assume that while the code is recovering from one failure, there is not another one in parallel. Of course, in practice, that's not true. You might have one evaluator failing, you are recovering from that, and at the same time, another one is failing. And you need to support this case. For the purpose of the slides, this is just not happening. That's the reality that PowerPoint allows me to create. Lastly, and this is a bit tricky to word right, we assume that failure is not recoverable on its own. If you think about, you have your slave task sitting there, and something in the network connection between that slave and your master fails for 3 minutes. And then someone comes back and plugs the cable back. This task will come back, right? Because it's still sitting there, it hasn't gotten the word that it's supposed to be dead, and it will still send things. So for the sake of this slide deck, we also assume that that doesn't happen. A task that's gone doesn't come back. As a matter of fact, in Reef, we have some defaults that make sure that that actually is true. Right? If you don't want to write a very advanced application, after we told you that a task is dead, it will not come back. Okay, with that said, let's consider task failure. Again, my typical grid picture. We have the master and the slave sitting there, and they do their usual thing of sending broadcast of the model and reducing up the gradients, or broadcast of descent direction and reducing up results. Right? So this goes on. And while it goes on, you at some point might suffer a failure. And I mentioned this earlier when I introduced the broadcast and reduce in Reef. These failures do not lead to a situation where your application hangs, stops, or crashes. We will make it so that to your master node here, it appears as if that node never took part in the computation. Right? It will just get the outcome of all the other nodes. Okay. So after each iteration, the master node will query for topology changes. I mentioned this yesterday when I introduced the broadcast and reduce primitives. We have this API by which you can ask, what in my configuration of the network changed since I last asked? Right? And in this case, this change set will include a removed node. One of the tasks disappeared. At this point, the master has a choice, right? There's no automatism here, and that's very crucial. The master has a choice on how to proceed. It could just go ahead and say, 1 out of 1,000 partitions is gone. It's not going to be that bad, right? So let's just continue. Or it could say, okay, I have the outcome of half of my machines, so let's just scale the learning rate a little bit and wait for machines to come back. In this case, we want to execute the job as is. So we want to make sure that we compute everything on all the data, right? That's the most conservative form of failure treatment we can do. And it's actually the one that all the distributed systems frameworks implement today. If you look at MapReduce or Spark or Hyrax, they all offer this when they say fault tolerance. Faults will not be surfaced to the outcome of your computation. And I believe in machine learning we don't need that, but let's just say we do. So we get a change setback, which then results this master to block. And for that we have a call where the master can say, hey, I want to sleep until something in my topology changes. Right? In the meantime, the driver has gotten notice from Reef about the fact that one node went missing. And it goes ahead, asks for another evaluator, instead loads the data in there, because it kept track where it loaded which data, loads the data in there, makes it part of the computation, and then tells the communication service that, hey, I have a topology change for you. That in turn will unblock the master who sits there waiting for a change. Right? So the master will then say, okay, I can run again. And in the next iteration, this additional node will take part in the computation. Similarly, when you have the failure during a broadcast, it's the same deal, right? Because when we do this block of figuring out whether something changed in the topology, is up to the code that runs in the master task. So in batch grain descent, it's very convenient to ask at the beginning of each iteration. In other cases, you might want to ask in the middle of an iteration to say, oh my gosh, I just did this costly step that never ever may go wrong. If something went wrong, I just want to repeat that part of my iteration. So it doesn't have to be at the end of each iteration. Okay, we do have code for that, and all of the code in the remainder of this lecture will be in this bgd.full example package. It follows the same structure as simple and simple line search. So if you read the first one and kind of understand what's going on there, the second one is just a bigger version there. If you have time at the end of the lecture, I can show you a little bit of that code. As a matter of fact, we had full, and then we made the simple versions, right? So it's not a surprise that they look so alike. Okay, so any questions about fault handling in this case? I want to stress the one fact, and that is the master had a choice in the case of a failure. It had the choice to, for example, continue and ask for an additional evaluator, and then at the time when that evaluator becomes available, make it part of the computation again, right? Because it's very conceivable that if you have 1,000 partitions, and for 10 iterations you only have 999, you will still make progress towards your learning goal. Right? So you don't necessarily have to wait. Okay. Speaking of wait, another case which I had on as a plot at the very beginning of the lecture is ramp up. When you run things on a cluster, you will find that there, especially a shared cluster, which many people use at the same time, you will find that you submit your job and then you wait for it to start. Right? Your job driver might be running, it submitted its query for evaluators, and then it sits there waiting for this query to be satisfied. Right? Why is this happening? Right? Why aren't there containers or evaluators available? Well, in many cases, it's actually a feature and not a bug. Because if you're the person that paid for this cluster, you don't want to have, in the case of yesterday night, 8,000 containers available just in case someone shows up and wants them. Right? You want to have as many of your containers utilized as possible because you already paid for the machine, for the building, for the electricity, and for the air conditioning. Right? So you want to use that, those containers. So what's actually happening is other jobs are running at more than their allocated capacity, and they need to be preempted partially to make room for your job. That takes a little while, But in the end-to-end performance, in the sense of how much compute per dollar can we do on our cluster, this is actually a good thing, right? Because the cluster does more work, and all this time where the 8,000 cores were not used by you, they were used by someone else, right? They weren't sitting just idle. But this adds wait time at the beginning of your job. Sometimes this wait time is actually a bug. And that's when one of the machines happens to be slow, or one of the the network connections is slow. And this can happen to you badly at the beginning of your job, when all of your tasks need to load the data into main memory, right? They all, at the beginning, do the very same thing. They go out to the distributed file system and load their part of the training data. Now, of course, not all of the training data will be on different machines, so that you will experience some congestion on the way to the data. Not all network links will be equally fast. Not all machines will be equally loaded or unloaded. So not all of these tasks will complete this part of the computation at the same time, right? So in that case, it's kind of a bug. And then sometimes, and more often than you really want to, you experience the perfect storm, where the last allocation that you get from Yarn happens to be on a very slow node. Because then you have already your 999 containers sitting there, ready to compute, waiting for the one sucker to load the data, right? And that's just the perfect storm. You just wait for 10 minutes and nothing happens, right? And you wonder why that is. And then if you have the means to look into the processes that are going on, you will notice it's probably just one node that you're waiting for. And for those of you who have used Hadoop or other MapReduce frameworks, this is called a straggler in MapReduce. And it can be very frustrating if it's your last reducer, right? You have this MapReduce job that ran for a day, and everything is at 99.9% completion, and you wait for that one job out of the 10,000 that you submitted to complete. Of course, as Sergey pointed out when I beta tested the slides with him, this can also be an indication that you shuffled wrong, that your distribution of input to the reducers is very skewed, and one of them actually has more work. But more often than not, it's actually just one slow machine. Okay, so now we know where this wait comes from. And in many applications, it's not avoidable, right? Because if you need all the machines at once at some point, you have to wait to get all of them ready at the same time. This is actually the traditional MPI setup. If you submit an application to an MPI cluster, all the processes come online at the same time. They all start communicating with each other at the same time. But given how those clusters are managed, this is usually not a big deal, because they are purpose-built for MPI, and you kind of do armchair scheduling, where you decide, okay, today this research group, tomorrow the other one, and so on, right? So you will not hit that shared resource problem as much as on these commodity clusters. Okay. Now, do we have to wait? Right? That's the other question. Can we change something in our algorithm, in our application that we run on top of these systems, such that we don't have to wait? And I would say yes, we don't have to wait. Because the only thing we do with data, and that's the thing that is connected to the machines, is compute gradients. If we don't have all the data yet, what we do is we compute a gradient on the subset of the data. If we assume that the data is randomly distributed across machines, we have a random subset of the data. Not just any, but a random subset of the data. If we compute a gradient on that, at the very least, the model we get will be a great initializer once we have the full data set. So we will make progress on this. Okay? There's any number of ways you can do this. Let me talk to you through the way that is actually in the code. So what we do is, in the first iteration, we wait till we have one machine. Actually, it might be two, for some technical reason in the reduced tree, which always needs two machines. So once one of these slave nodes comes online, the master unblocks, and we have a communication going. If you look in the code, there's a parameter for the minimum number of slaves that you want before you start. At the end of the, while this is going on, the driver continuously negotiates with Yarn for more containers. Right? It's a separate process. It continuously does that. It tries to get all of the containers that you asked for as quickly into the computation as it can. Right? Whenever one becomes available, it will immediately submit the task that loads the data. And once that is done, it will inform the master that there is a topology change. So at the end of the iteration, when the master asks the group communications library whether there has been any topology change, it will see an added node, an added task. It's not like in the failure case where something is missing, but there's an added task in this case. But different from the failure case, the master never blocks here. It just checks, is there a topology change, yes or no? If yes, add it to my computation. If no, continue on the other nodes. Of course, you can be much smarter there and consider statistics of the data set and all that. But for now, that's all it does. OK, so in this case, there is a node available. It makes it part of the topology, and it starts computing on it. So now we broadcast and reduce on that, and we just have doubled our sample size. And of course, eventually, all of them will come online, and they will be added. Now, with this approach, if you just keep it going like this, failure is also handled in a slightly different way. Because if nodes disappear and you just ignore that fact, the driver will go ahead and add another node, and for a couple of iterations, you will run on less data. But in the grand scheme of things, it's probably not going to hurt you. And that's a very vague statement for at the beginning of the optimization, it's really not going to hurt you. At the end, it probably will. OK. So now the question is, does this actually work in practice, and is it any good? And I want to bring up the figure that I had in the very first day. That is, what we did is we ran on an actually loaded cluster, and we said, OK, let's simulate with the same code. So we are not running MPI versus us or anything like that. Let's simulate with the same code, running batch gradient descent on the splice side data set from the TerraScale learner paper. Let's run the code and first say, OK, we wait for all the machines to become available. They all load the data, and then we start. Right? That's the red line. And in this case, it took about 11 minutes for the last guy to become available. A lot of them were available earlier, but this is when the last guy became available. Now, the green line is where we said, OK, that's fine, but if I have my own cluster where I don't have to wait, is there still a win? Right? In this case, we said, OK, let's just assume that we get all the machines at once, and we subtract that cost from it. And once we get them, they all go ahead and load the data, and they start running. In this case, you still suffer from some of the stragglers, right, for about roughly 10 minutes. Or, no, it's less than that. That's here. It's like 2 or 3 minutes, where some of the machines take a little longer to load the data than others. And you're still suffering from this wait time at the beginning of an iteration. Of course, in other computational frameworks like MapReduce, you would already start, but you would encounter this barrier where everyone has to meet it at the end of the first iteration. So you can't really escape this even if you use MapReduce. And then the blue line is the approach that I just presented, where we said, OK, as soon as we have 2 machines, yes?
So if we are doing online learning, like
Yes.
online gradient descent, how do you do this allocation? That is the best way.
So if you do online learning in a distributed fashion, I don't have a good answer for how to do resource elasticity. That's actually one of the open questions, right? I was very honest at the beginning when I said, hey, we don't really know how to do resource elasticity yet. In this case, we know how, but in others, we don't. OK, so the blue line is the approach that I just showed. As soon as we get 2 machines, we start computing, and we add machines over time. And of course, as those of you who have worked with this data set know, it's actually a pretty poor fit for linear learners. We just used it because it's very big. The actual objective function value is still terrible even after convergence with the linear learner. And that's why you make a lot of progress early on. Right? Nevertheless, if you hit one of these data sets and just want to discover that it is not learnable with a linear learner, what you will see is that the elastic approach is essentially done by the time the unelastic approach can start computing. That's, of course, in more hard data sets where you have a more traditionally shaped learning curve, you will see that not to that extent, but you will always see it because you can always make progress on the first few data samples that you have before you enter the main loop. OK. The code for that is the same as for failure handling. It's also in the full. There are a couple of command line parameters on how you can switch between the various fault handling primitives, like waiting for machines to come back or actually just merging them in. And I encourage you to have a look at the code after the lecture. And maybe we will in the last 3 minutes or so. Before that, I want to kind of point you to a couple of questions that I have and maybe some of you want to work on. What can we do with this insight, right? Because we just related a systems principle or systems concept of machines becoming available and not available to a machine learning concept of we have a varying sampling rate and what do we do about it, right? There could be other places where this comes up and where we can have good answers. So first of all, it could be other models, right? I mean, learning linear models with batch gradient descent is only interesting for so long. Graphical models could be very interesting because you will find when you have the need to distribute them, you also distribute the model parameters. And then a machine failure means that you lose some of the model parameters. Can we deal with that? There's a paper, I tried to find the reference this morning, I didn't, I'll put it on in between today and pushing the slides out, where they do this for PageRank executed on a graph. And what they do is they compute an imposter node in the graph that represents a whole clique of the underlying graph and accumulate the PageRank updates for it. When the node comes back, they redistribute all the PageRank updates. So something like that, maybe there's a general principle. Of course, in deep learning, you have the same problem, right? You distribute all your model parameters. And what does it mean for a learning network to not have a couple of neurons, right? I mean, we know that it's pretty lethal for a brain, but maybe for our learning networks, it's not. Maybe we can do something, right? I mean, if you look at the results that they have with dropout, maybe there is something here that we can do. Of course, in dropout, it's unclear to me, right? Someone should look at it, and maybe some of you. There are other elasticity approaches, and I already mentioned one of them. When data disappears, the two versions that I presented here were make it come back and wait till this happens and continue, which is the trivial case, or just completely ignore the missing data. But you can, of course, have any number of approximation tricks that you can play. So one thing that we thought about is if other nodes all contain a sample of each other, right, then you can just replace the missing node with a sample that is stored on another node. Right? Then you would still make progress. Another thing that we tried in a paper last year at the NIPS Big Learn workshop is when a node disappears, we just keep the last gradient around. We just reuse the gradient, which is a simple way for saying the fancy version where we say, hey, we just assume the function is linear. And then the gradient would be perfect, right? And of course, this is not a perfect approximation, right? And if you keep this running for too long, you will see that you start diverging if this happens on too many of your nodes. Again, if you only have 1 out of 1,000 partitions missing, the benefit of that over just ignoring the failure for a few iterations is not that strong. Still, better approximations can be built. Lastly, there could be other relationships between these resources that you have and machine learning. And one line of thought is very straightforward. If we have varying sampling rates, and our algorithm is phrased in estimates of some statistical quantity on our training data, if we have varying amounts of training data visible at any moment in time, this means that our estimates have higher or lower variance. That in turn can be used to change learning rates, change update rules, all of that. Right? This is a very straightforward relationship. Maybe there are others. This is again based on data. If you have models, this gets, if parts of your model disappear, this gets much more interesting. Okay. Lastly, and this is kind of one of the grand challenges if you want to make machine learning appealing to a much wider crowd than today, which is arguably already a lot, is can we relate the outcome of the machine learning task to the resources we put into it? Because at the end of the day, that's the cost that you have. Every single container minute costs you something. A cent or so. I don't know what the actual price is. If you can get to a good enough solution with fewer containers, it will cost less. it's more likely to be done, right? Because as I think Deepak said that during his lecture, where someone asked me, hey, could you do this much more often than once a day? Yes, you can, but it costs money to do that. You have to build the clusters, you have to maintain them. And if you can do it with less, that's always good. Similarly, if you can relate the outcome quality of your learning algorithm to the amount of resources consumed, you can ask questions like, hey, the resource manager just offered me 200 containers for the next 5 minutes. Should I take it, right? Because using those will incur some cost of shuffling the data around. That is where the database community is really good at figuring out how much that will cost you, right? There's literature. Now the question is, how much more benefit will you get out of the 200 nodes for 5 minutes, and is it worth it compared to the cost of shuffling and reconfiguring your computation? And the crucial ingredient missing is how many containers, what is a container worth to me in terms of accuracy of my classifier, AOC of my classifier, something like that, right? So there are really open questions here from a theory side, how we relate these things. Okay, conclusions. I think I have suitably told you the first step, right? It's distributed applications are incredibly hard in practice. Not only because they are hard in principle, which is you have things that run in parallel and they can happen in any order and you need to deal with it, but they are also hard in practice because it's just so much harder to debug a system that's running on a couple of hundred machines than to debug one that is in your MATLAB window. Secondly, I think we can't avoid it as a community because the way the cloud is going with this race to the bottom in pricing and the race to the bottom in terms of the unit that you buy from hours to minutes and pricing being spot pricing, it's just too attractive as an economic model not to succeed. And then if machine learning, let me phrase it the other way, lots of applications cannot be resource elastic. If you have a petabyte of numbers and you want the average and you want it for sure and you don't want the want a sketch, then you have to compute that, right? All the SQL databases in the world will have to do that. They are also trying to convince their users that, hey, if you can get a good enough estimate, maybe that's good enough. But many applications, you cannot really change what you compute in response to the available resources. I think in machine learning we can, because in many cases, especially at the beginning of optimization and all that, not having all the data is not that bad. So we can react in more interesting ways than the MapReduce way of saying, hey, whenever something fails, we'll just happily re-execute it. So I think there's some value here that's unique to machine learning. I said that. I think it's a promising research direction that hasn't been done much. No one has done much in this space. And I hope that I convinced you that Reef provides a useful abstraction in this space. And the abstraction of Reef is very thin, right? If you compare Reef to MapReduce or, let's say, a distributed version of MATLAB on the extreme case, the distributed version of MATLAB will hide all of what I taught about, right? It will give you your matrices, you multiply them with each other. If something fails, they will quietly reinstantiate it, and all you know about it is it took a little longer than otherwise, right? That's the beauty of those systems. The other extreme is you code things to bare metal, right? You SSH into a couple of machines, start your process, and they talk to each other. Between those two approaches, Reef is much closer to the latter, right? It is a natural expression of the underlying distributed system. So when things fail, we tell you about it. When things are done, we tell you about it. When resources become available, we tell you about it. There's absolutely no policy in Reef that would do anything with that information. That's all up to the application. But if you want to work on this level and kind of exploit the underlying systems infrastructure, then Reef makes that a lot easier than if you were to code straight up against bare metal and try to figure out how to open a network connection between your two nodes and detect that the other guy is no longer answering and all this stuff that is in Reef that makes this kind of work so much easier. I want to again say that all of Reef is open source, so you can go ahead and play around with it. If you find bugs, as one of the audience members did, please file a bug report. We tend to be responsive to those. The code is on Maven Central, which means that most people will not have to compile it. We do a release on the 21st of each month, and if you look into your calendar, today is the 18th. So on Sunday or Monday, there will be version 0.6 out. That's the version that we used for the summer school. So remember, whenever you compiled, you had this long string 0.6/snapshot. That means it's the current development version of version 0.6. So beginning Sunday, you probably won't have to compile it yourself anymore. We know that it works on pretty much all of the Hadoop 2.2s that are out there. We've never tried with Hadoop 2.0. It should work. We just haven't tried, right? And I mean, it was never really deployed by anyone. I think Yahoo deployed the first clusters as 2.2. HD Insight is on 2.4. I don't know what the current version of Cloudera is. With that, I'm coming to a close pretty much in the last minute. If you have any questions after the summer school, send me an email. If you have questions about Reef, go to the website. We have a couple of papers up, and we also have a mailing list there for developers that are using Reef. Thank you. Okay, I'm taking questions while I'm packing. That's not because I'm rude, but that's because my flight's leaving.
Actually didn't make it.
No.
Because we ran out of storage on it about 3 minutes ago.
Really?
Yeah, so the last 2 minutes are not on.
Oh, okay. All the open research questions are not on. So they're all yours, they're not for the public.
Sorry.
That's okay.
You can do it before the next lecture.
Yeah, return forever.
I'll show you the
Every time someone's going
I mean, I know that the particular is thinking down the same lines. They unfortunately are kind of hamstrung by the fact that they have a consortium that has to read the API consortium. Yeah. There's a ton of literature on how to make this elastic operate. No one has built that because they can't agree or understand. That's the shocking realization. Yeah. Well, they do, right? There are all these proposals out there. But because none of them is perfect, right? You are buildings with all software. You can't change that in incompatible ways. Reef API is completely incompatible with API. Those are the semantics that are built. They have a hard time making that step and saying, okay, we have any words.
Change the error code.
Exactly. I am afraid about this. Oh yeah. They are trying to escape this from.
The one thing is make sure that
So they just transform their
actually, with the first one, I was writing
the next generation is they know this because the machines are so reliable.
Okay. So this is
Cradles. When Cradles is just doing 100,000 they tell you all. Okay, I see.
Marcus, thanks. So that's all that's on it. The end of task conclusion.
Okay.
I'm really sorry.
That's all right.
I'm really sorry.
I give this talk a lot, especially the conclusion. Okay, I gotta see you. Thanks for coming.
That's great. Thanks for coming.
Look at Isaac.
Sure, okay, yeah.
Are you getting paid for fun?
No.
I can try this afterwards.
No, afterwards.
Yeah.
The camera. You're responsible for the camera.
Yeah.
Don't worry about my laptop.
I can give you my card.
Yeah. Which resolution are you going to pick? Andrew, which resolution are you going to pick? Because this determines how I point the camera.
Which resolution? Or what are the choices?
Yes. Well, basically, the cropping on the left depends a little bit on which screen resolution you pick.
Oh, okay.
And that, again, in turn, influences where I point the camera at. Now, it's basically, if you just go into full screen mode.
Yeah, I will be in full screen.
Yeah. Okay, thanks. That means you'll actually have a little bit more space on the right.
Okay. Is this sort of the limit of what we can see over here?
You probably have another 10-15 centimeters. Actually, if you can stay where you currently are, that would be great. We say I'm going to try and focus on you.
What's the resolution of the camera?
If you didn't shave, you'll see it. Can you do sun check?
Yep.
Okay, just talk normally. That's 1, 2, 3. Anyway.
1, 2, 3.
Okay, this is weird. Why does it respond?
Can you hear me?
Can you say it again?
Testing.
Okay, that's good.
Is there a card I need to insert for the laser?
So what's that?
Is there a card I need to insert for the laser point?
Yeah, no.
I don't see it here, unless it's in the bottom.
The bottom, yeah. Yeah.
Yes. Also, but we can stop it. I think we will probably stop it because it's not so exciting what's happening.
You don't want to get this?
It's fine, actually.
No, I didn't have it.
You can.
I don't know why I did that. No, it does. It's also. It's a lot already.
Oh, yeah. They should use scientific notation. Don't think I'll ever have inbox 0.
I guess I can introduce, this is the last lecture of time. All right, we'll start recording again. Are we recording now?
Yeah.
All right, well, hello everyone. For the last time, this will be the last lecture of MLSS. Hopefully you've enjoyed it, and thank you for those that stuck around for the very, very end. Andrew, again, speaking about kernels and Gaussian processes.
Thanks, Nico. It's been nice being at summer school, and I'm really glad to be here to talk a little bit more about developing kernel methods, especially for pattern discovery. I was thinking about machine learning summer schools last night, and actually when I started my PhD, they were doing machine learning summer school at my university, so it was a really nice experience. And Carl Rasmussen, one of my favorite academic writers and speakers, gave a lecture there, and he told a story about how when he was teaching a class, he thought he'd given the last lecture for that class, but found out he actually had to give another one. And because he didn't have anything prepared, he actually just exactly repeated what he said in the previous class. And he was a bit nervous about this, but he was surprised to find out that the students actually really loved it. And wish professors did that more, because just seeing the material a second time really helped things sink in, and you could sort of delve a little bit more into what were the sort of fundamental concepts in the talk. I'm not going to exactly repeat the last lecture, but I will talk about what I think are a few key concepts regarding Gaussian process inference and kernel learning, so that we can more fully appreciate these kernel methods that we'll be talking about later that will build and scale up for pattern discovery and representation learning problems. And please, at any point, if anything's unclear, even if it's just notation, feel free to ask a question. The sooner you ask a question, the better. So a Gaussian process is formally defined as a collection of random variables, any finite number of which have a joint Gaussian distribution. This notation that we see here, f is distributed as a GP, means that any collection of values here, we can think of them as function values in a lot of cases, any collection of function values evaluated at any collection of input points has a joint Gaussian distribution, a mean vector mu, and a covariance matrix K defined by the mean function, little m, and the covariance kernel, little k, of the Gaussian process. So to be extremely concrete, we were considering airline passenger numbers as a function of time in the last lecture. So each of these function values could be different airline passenger numbers indexed by different times, and the indices in this case are the x's. So we can use this model to define our prior order functions, and we can sample from that model. So to create this picture on the left with the black dots, I basically just chose a bunch of input points or input times. Here I've labeled it t on the horizontal axis, and I created my joint multivariate Gaussian distribution using my mean function, which in this case was just a 0 function, which is represented by the blue curve, and my covariance matrix, which is defined by the covariance kernel that we chose. And we talked about all sorts of different covariance kernels in the last lecture, and we'll mention a few again this time. And once I did that, I basically just got the black dots. I sampled from exactly the same distribution 2 more times to get the purple curve and the green curve. In that case, I just joined the dots together. Now, if we observe some data, we can perform Bayesian inference to determine the posterior distribution over functions conditioned on these observations, which are denoted by crosses. The blue curve here is the posterior predictive mean of that Gaussian process. So this is what we use to make point predictions. The gray shade shows 95% of the posterior predictive mass. So this gives us a sense of our uncertainty. And the black, purple, and green curves are just sample functions from this Gaussian process posterior. Very, very importantly, I can't really stress this enough, likely functions under this Gaussian process, the properties of likely functions under this Gaussian process model are controlled by the covariance kernel. So whether these functions look smooth, whether they're periodic, whether they follow some kind of Brownian motion, whether they have some kind of mixture of those sorts of covariance structures, is all encoded by the covariance kernel. And if we have a very flexible kernel, that we can actually learn from the data, then we can automatically learn an interesting representation, which will allow us to do things like extrapolation. So to be a little bit more detailed, suppose we have our vector of observed data. So again, I'm just saying, why are our observations? They could be noisy, they could be airline passenger numbers, but maybe we haven't sort of recorded them that precisely. Indexed by input locations X. We could use some kind of standard regression assumption, like we have additive Gaussian noise. So each point is described by some underlying noise-free function, which we're modeling as a Gaussian process, plus additive Gaussian noise. And then we can try and infer the posterior distribution over our Gaussian process evaluated at our test input locations, which is denoted by this vector f star here. So if we have m points that we're trying to make predictions, the dimensionality of this vector f star will be m by 1, conditioned on our data, and our training inputs, the inputs at which we have our observations, and our testing inputs. So, as a first step towards this goal, I've written down the joint distribution of our observations and our test inputs. At first, when you're studying Gaussian processes, the idea of doing inference and making predictions might seem a bit intimidating because it might seem like somehow you have to represent the Gaussian process at all points in your input domain. And we're saved by the fact that we only actually need to represent the Gaussian process where we're interested in querying that Gaussian process, namely at the training points and at the test points. Now, in this model that we've defined here, the noisy data actually is a Gaussian process with the covariance kernel that we've chosen for our noise-free Gaussian process, plus this noise term that we've added here. So basically say we have our data, which is just a vector of observations. It's equal to this vector f, which is our noise-free model evaluated at the training inputs, plus some kind of additive noise. So mu is just a noise variable that gives us this noise variance sigma squared. And so the distribution of y is just going to be Gaussian with, in this case, mean 0, if we've chosen a 0 mean function for our Gaussian process, and covariance matrix k plus sigma squared I. Does anyone have any questions about that stuff? Okay, and f star is just our Gaussian process queried at our test points. So f star is just, say, this m by 1 vector, and it's got a Gaussian distribution with this covariance matrix k star star. So the ijth entry of this covariance matrix would be defined by our kernel evaluated at test points I and j. And here we've written down the whole joint distribution over our training observations and our noise-free Gaussian process evaluated at the test input points. Using standard Gaussian identities, we can derive the conditional distribution of the GP at the test inputs given our noisy observations y and our kernel hyperparameters theta. So our kernel will be parameterized by these theta variables here. And when we do that, we derive equations 3 and 4 here. So the predictive distribution here is a Gaussian distribution with the mean described by equation 3 and covariance described by equation 4. We use equation 3 generally to make point predictions, and we use equation 4 to get our predictive covariances, which is mostly used. You just take the diagonal of that to get a sense of our predictive uncertainty. So the gray shade that you saw in the previous slides was created using equation 4. A funny thing about equation 4 is that it doesn't explicitly depend on our observations y like our predictive mean does, but we said that our kernel hyperparameters, if we're doing kernel learning, will depend on our observations, and so will the noise variance, and therefore this term will actually also depend on the observations. Now, to learn our kernel hyperparameters, we can use the marginal likelihood of our data, which is, in this case, in the context of a Gaussian process, is the likelihood of our data having integrated away that Gaussian process so that it's just a function of our kernel hyperparameters. The marginal likelihood we argued last time will generally favor a model of appropriate complexity that will fit the data. So on the right, I've shown the predictive mean of a Gaussian process with an RBF kernel using 3 different length scales. The red using a really big length scale, the pink using a really small length scale, and the green using a length scale that was determined through marginal likelihood optimization. The analytic form of the marginal likelihood under the assumption of IID Gaussian noise is expressed in equation 8, and this is the function that we optimize to get this fit that we see by the predicted mean in blue in the figure on the right. The marginal likelihood pleasingly compartmentalizes into model fit and model complexity terms. So, for example, if we had a very, very tiny length scale, we could really fit tons of data sets with that process, but the functions would look really wiggly, and they'd be crazy, and they probably wouldn't generalize. The complexity penalty is what keeps things sane, and it's automatically calibrated, and it comes out as a result of integrating away the Gaussian process. Of course, if we wanted to be fully Bayesian, we could put a distribution of our parameters. We have uncertainty about these kernel hyperparameters, and we can represent that with a probability distribution, and we can try and integrate them away. Unfortunately, this integral is typically intractable, so we would have to resort to methods like MCMC. People tend to do this in some applications, like Bayesian optimization, which has become popular for tuning deep neural networks, but typically the marginal likelihood is sufficient for training these kernel hyperparameters. Of course, you could try to plot what the posterior of our hyperparameters look like, given what seems like a reasonable prior in our data, and that might give you a sense of whether sampling is actually worthwhile. If it's fairly sharply peaked, then it's fairly well determined by the data, and sampling won't be much different than optimization. So we also looked at these linear basis function models. This is a very standard parametric model. It includes models such as like a polynomial model with coefficients that we're trying to learn from the data. If we just put a Gaussian prior over the free parameters in this model, we can follow standard Bayesian parametric modeling procedures to derive the predictive distribution. Just infer posterior over these parameters, and to make predictions, we can integrate away the parameters, and we can write out an analytic solution. And it looks quite intuitive. For example, mu n here is the predictive mean that we get for the free parameters, and the predictive mean for our predictions is given by mu n transpose times our basis functions. So it's fairly straightforward. However, we said that if we have a distribution over these parameters, we also induce a distribution over functions. And we can start working in function space directly instead of parameter space, which is very nice because often we have more intuitions about functions than we do about parameters in a parametric model. And if these basis functions happen to be infinite dimensional, then we can actually work in this dual space using kernels with finite amounts of computational power. So to get a sense of this, we basically just said, okay, let's suppose we have some parametric model. And we have some distribution over the parameters. We can actually sample from this distribution and then condition on those samples to draw a corresponding sample function. And we can keep doing that and get really a sense of the distribution that we've induced over functions. And this is actually something that Radford Neal did when he was trying to decide on good priors for Bayesian neural networks. He would sample from the distribution over the parameters in that Bayesian neural network and then draw the corresponding induced function. And this is really a beautiful property of Gaussian processes, that instead we don't need to worry about the parameters so much, we can actually just look at the covariance kernel and see how that affects the induced distribution of our function, and it controls this distribution in a very intuitive way. So we can characterize the properties of these functions by looking at the moments. So suppose we want to calculate the expectation of f of xw. Let's just do the expectation of W transpose times basis function, which will just be 0 because the expectation of our parameters W is 0. And the covariance between a pair of function values evaluated a pair of inputs, so I could call this xi and xj or x and x prime. It's just a pair of inputs in our input space. Can also be worked out in the same kind of way. It's just the expectation of f j e x y e j. We know these terms are going to be 0. We worked out the predicted mean was 0. And this term is just going to equal phi transpose e w transpose phi. And that just equals, and this is evaluated at xi and xj. And that just equals phi of xi transpose 6w phi of xj. So basically, we've entirely encapsulated this linear basis function model with a Gaussian process that has this mean function of 0 and this covariance kernel k. It's any collection of function values here will have a joint Gaussian distribution. Now let's imagine instead that we're considering a specific type of basis function. So suppose our model is f of x equals the sum, so we're not using vector notation anymore, weights times the basis functions phi I of x, and let's put some distribution on the weights. So let's put it equal 10, 0, sigma j. So we just let the variance of these weights scale with the number of components we have, j. And let's say we use Gaussian basis functions. These basis functions are centered on the point ci. So if we have two basis functions, for example, and we have points c1 and c2, in our model replace basis functions centered on points c1 and c2. Now, let's let the distance between the I plus first center and the I center equal delta c, which is equal to 1 over the number of components we have. And let's also let the number of components approach infinity. Now, just before we derive what the covariance function of a linear basis function model is, regardless of what kinds of basis functions we're using. And that just equals, for this example, now, if we let j approach infinity here, then we can see that this sum here actually approaches a Riemann sum. It'll become an integral. And we'll be integrating from our first center to our last center over our basis functions. We can take these limits of integration from minus infinity to infinity. So we have infinitely many basis functions densely dispersed across the real line. We can plug in these exponentials for the basis functions and actually compute this integral analytically and recover the RBF kernel. And this is far and above the most popular kernel in use with Gaussian processes.
Yeah, question. Mm-hmm. If j goes to infinity, then the distribution of W will be like a Dirac delta function?
So
the variance will get smaller and smaller.
that's correct, yeah. If that has to happen for the sum to converge.
But we don't care about it in the integral.
No. This is with respect to this integral with respect to C. So we can actually write out this like this is equal to just x C over 2l squared, and this is equal to x minus C. And this is an integral that we can do. So we talked about how different popular kernels affect the properties of likely functions under a Gaussian process. And we went through this example, which I think is quite instructive because we can look at different trends in the data and then try and choose an appropriate combination of kernels to model these trends. So the goal is basically to look at this data here and try and perform extrapolation. So we can actually, might as well just put the answer. We can actually separate the medium-term trends, the long-term trends, and the cyclical trends that we see in the data. The long-term trend is denoted by this dashed blue line on the left. We could model that, for example, with a polynomial kernel or a linear kernel, but we're not doing that because we don't want to restrict our model to say that CO2 concentrations are just going to keep increasing forever. So instead, we'll use a RBF kernel here to model this long-term rising trend, denoted by K1. Now, the seasonal changes look roughly periodic. They've got increasing amplitude. We can model this quasi-periodicity by first taking a periodic kernel and multiplying it with an RBF kernel. The periodic kernel here has a period of a year, but you'll notice that there are a lot of hyperparameters here, theta 3, theta 4, theta 5, that we're going to try and learn from the data. Now, if we look at the green curve on the left, we see that it seems kind of multi-scale. Unlike those sample functions I was showing earlier on from a Gaussian process that looked very smooth and they were all sort of varying on the same scale, you can see that the function perhaps looks a little bit more wiggly on the left than it does on the right, and there seem to be different kinds of scales in the data. Rational quadratic kernels were defined to model that kind of data. So we'll use a rational quadratic kernel for the medium-term irregularities in K3, and it's got a lot of hyperparameters that we want to learn as well. And finally, we want to model the noise. So we can say that there's IID Gaussian noise, which is just modeled by this theta 11 squared parameter and this delta function. So basically, if you have a noise-free Gaussian process and you add IID Gaussian noise, that'll be a Gaussian process, and its kernel will be the same as the kernel from the noise-free Gaussian process plus this Dirac delta function, basically, and theta 11 squared here is the noise variance. And we may believe there's correlated noise as well. And let's model that with an RBF kernel as well. And like I said last time, you could say, okay, well, isn't there a lot of degeneracy in this model? Couldn't you interchange the roles of K1 and K4? And that's exactly right. Once we train the hyperparameters, hopefully the value of theta 1 will be a lot greater than the value of theta 9. The signal variance will be a lot greater than the noise variance. And indeed, it can interchange roles, and so the results of the model will have to be intelligently interpreted. Are there any questions about this example? Okay. Once we do that, we can perform extrapolation quite nicely. It's fairly confident in its predictions. We can interpret the values of the learned hyperparameters to learn a little bit more about our data set. Nonetheless, though, a lot of the interesting pattern discovery in this example has been done by a human. In principle, we should be able to automate whatever we did when we looked at that data and write it down as an algorithm and have a computer perform that job, or better yet, just have some kind of flexible kernel learning algorithm which will automatically learn a representation of the data that will enable extrapolations on simple data sets like this, but also on much more challenging problems and large-scale problems as well, where flexible kernel learning will be most useful. Lots of training instances provide us with some kinds a special opportunity to learn a lot of rich structure and data that we wouldn't otherwise have. I briefly talked about different ways of scaling up Gaussian processes, and I'll talk a lot more about those today. I mentioned inducing inputs, which have been quite successful. The basic idea behind inducing input approaches is to assume that the Gaussian process vector that we're interested in, evaluated at the training points and at the test points, are independent, conditioned on knowing some inducing points u, which are described by a Gaussian distribution with some covariance matrix KUU. When we make that assumption, our predictive equations look like equations 16 and 17 here. And to evaluate these equations, we only need m squared n operations instead of n cubed operations, where m is the number of inducing points that we've chosen. And there are lots of different approaches within this family of scalable Gaussian process methods. And the different approaches correspond often to different additional assumptions about the conditional distributions active in U and or F started in U. And this family of approaches is very nicely described in this review paper that I've listed and will be in the references. And by the way, the slides will be up online at some point. These approaches have been used to scale up standard Gaussian process methods with kernels like the RBF kernels from about 10,000 points to about 50,000 points. Which is very good, and it seems to work quite well. Although I'm not saying that this is definitely the case, but it's certainly worth thinking about what it means to scale up a Gaussian process, for example, with an RBF kernel and maybe a single length scale hyperparameter. Suppose that length scale hyperparameter is really small. By definition, that means we're not going to be using a lot of the data in making predictions. So does it really mean a lot to say we can run this on 50,000 data points? We might only need 100 data points to make the predictions that we're actually interested in. Likewise, if the length scale is very long, perhaps we could subsample the data in a reasonable way and still make pretty good predictions. So it's always worth thinking about whether we should actually be scaling up the model before we start putting a lot of work into making it run on 50,000 points, for example. And 50,000 points isn't really a lot, and we can make these models scale to much bigger data sets. So now we'll move on to part 2 of the talk, where we actually try to build these expressive kernel-ready approaches. We talked about these briefly last time, but I think it's worth introducing them again now that we've reviewed background on Gaussian processes. So we looked at the CO2 data set, we modeled different patterns, and we determined how to extrapolate on this problem by choosing combinations of kernels by hand that seemed appropriate. We could also consider other kinds of extrapolation problems, like this data set, where we look at the blue training data and try to make predictions in this missing region between -5 and 5. We could use a Gaussian process with, for example, any of these popular kernels. I've just written them out for one-dimensional inputs, just for notational clarity. They're all stationary kernels. They can always be expressed as a difference between the input points x and x prime. Notice that a lot of these kernels have the bias that points nearby in the input space will be more correlated than points far away in the input space. That's a very useful bias to have quite often. They all have length scale hyperparameters, which control the rate of variation for likely functions under a Gaussian process using these kernels. And these are the extrapolations we make in all the curves but the green curve if we use a Gaussian process with any one of those kernels individually. And we shouldn't be that surprised by those extrapolations because there's not much structure we can learn using these kernels, just a length scale, for example. In the late 90s, when neural networks research was still very popular, and I guess it's really popular now as well, David Mackay wrote a review article on Gaussian processes, pointing out that neural networks were first motivated to discover a lot of interesting structure and data through adaptive hidden basis functions. And Gaussian processes at the time were becoming really, really popular and sometimes even being treated as a possible replacement for a neural network. So he pointed out that the Gaussian processes, the kernels that we were using at the time, are very nice in a number of applications. They're basically smoothing devices, so we should be careful about necessarily calling them a replacement for Gaussian processes. An answer to that criticism is to build more expressive covariance functions and try to learn the free parameters of those covariance functions, or even go so far as having, for example, a non-parametric distribution over kernels, which is something we'll look at later on. So there have been several approaches to building more structured covariance functions. You can incorporate GPs into neural network-like architectures, which has been attempted in various different ways. And often these models are quite interesting and successful, but also quite task-specific. You don't get closed-form expressions for the kernels quite often, and inference is very involved. Compositions of kernels can be used quite successfully. Multiple kernel learning is an example. Again, often people will use Gaussian kernels and just focus on learning certain types of structure, different types of length scales, for example. If you were to be very flexible, if you were to have some kind of arbitrary composition of kernels, it would be hard to know what kind of distribution over functions you're working with. So you might have kind of strange inductive biases, and it might be kind of hard to learn information from the data. If you have just a single realization from a stochastic process, so we're assuming that these data sets, like the airline passengers, are basically drawn from a Gaussian process, it's very hard to say much about the covariance function unless you make strong assumptions. So if we just assume that the kernel is any positive definite function with equal probability, a priori, we're not going to learn very much from the data. So assumptions like stationarity, assuming that covariances are invariant to translations in the input space, provide us with the useful inductive bias for doing kernel learning. And any stationary kernel can be expressed as an integral of a spectral density using Wagner's theorem. So this theorem is very useful because it allows us to think about spectral densities sometimes instead of kernels, and sometimes it's a lot more natural to consider spectral densities than stationary kernels. For example, we saw in the last lecture that you can derive the Mathieu kernel by modeling the spectral density as a student T distribution. If we take the Fourier transform, so basically the kernel, the stationary kernel k tau, and the spectral density S are Fourier duals of one another. If we take the Fourier transform of a RBF kernel, then we get a Gaussian density centered on the origin. And if we take the Fourier transforms of lots of popular kernels, we see sort of similar looking spectral densities centered on the origin. And this gives us intuitions about what happens if we take arbitrary additive compositions of these kernels. It's like doing spectral density estimation with, for example, a combination of Gaussian densities centered on the origin, which isn't necessarily a function we would want to use in general for density estimation. So one approach to building more structured kernels would be to model the spectral density with a scale location mixture of Gaussians. We know that with enough components in this model, we'll be able to model any density function to arbitrary precision. But even with a small number of components, we'll have a lot of flexibility, because if we have even a small number of components in a scale location mixture of Gaussians for density estimation, we can approximate a number of densities quite well. And therefore, if we use this model for kernel estimation, we can approximate a number of stationary kernels quite well. And if we plug a scale location Gaussian mixture into equation 163 for the spectral density, and take this inverse Fourier transform, we can analytically recover a closed form kernel. If we just have one mixture component, it looks a bit like equation 165. One caveat is the spectral density has to be symmetric, so we actually use a symmetrized mixture. Equation 165 essentially forms a basis for all stationary kernels. And the parameters are quite interpretable. The mu's are the frequencies in sort of the time domain, but the location, the centers of our Gaussians in the frequency domain, and the variances here, the sigma squares, are bandwidth parameters like inverse length scales, and they're the variances of our Gaussians in the spectral domain. So we can use a spectral mixture in, for example, a standard Gaussian process regression model where we're assuming ID Gaussian noise here for our observation model. And then we can learn the free parameters of the spectral mixture kernel by optimizing the marginal likelihood. And once we've done that, we can condition on these learned hyperparameters to make predictions using Gaussian process predictive equations that we derived earlier. And when we do that, we get the predictions that we see here in black and the predictive uncertainty that we see here in gray shade. That shows 95% of the predictive mass. And we can also look at the learned spectral density. It's trivial because we actually derived this example by modeling a spectral density, and we can just plug in the mu's that we've learned and the sigma squares that we've learned and draw the corresponding Gaussians in black here on the right. And we will see peaks at the frequencies of interest, and the wider the peaks, the less sort of certain about how much we think those frequencies should generalize.
Say you have a function with a lot more noise. Typically how many components would you need to in the spectral mix?
Well, we'll actually consider that almost exact question later on, but if you have more noise, you don't necessarily need more components. You just will have more trouble generally recovering the covariance structure, although if it's white noise, then that can actually often be quite easy to filter. And in this experiment, which is basically just a sanity check, we sampled from Gaussian processes using known out-of-class kernels, like the math-hearing kernel, which is quite heavy-tailed, and tried to recover what those kernels are. So these pictures aren't actually of observations. The green is some kind of true kernel that we've used with the Gaussian process. We sampled some data, added some noise to that data, recovered the kernel using the dashed black curve, which is just basically what the spectral mixture kernel is trained to after we've learned those data hyperparameters. And so this just shows that we can recover out-of-class kernels. And the red curve in both of these figures shows what the squared exponential, aka the RBF kernel, is trained to. And you can see that, for example, the true kernel on the left is a math-hearing kernel, so it has heavy tails. No matter what length scale we give the RBF kernel, it's not going to be able to model this math-hearing kernel too well. And the pink curve here is the empirical covariance estimate, which assumes stationarity as well. It's basically like if you took product of the data points for the covariance and then averaged that product across all data points that were equally spaced apart, you get the empirical covariance for that lag, for that spacing. The reason that it's sort of oscillating all over the place is because it doesn't have this nice bias that covariances generally decrease as a function of distance in the input space. And then we looked at another example. In this case, the observations were sampled from a discrete time autoregressive Gaussian process with negative covariances. Such Gaussian processes are often used in natural sound modeling, although they're not always called Gaussian processes. You can see that these blue observations almost look a little bit like a natural sound. This again is just to do sort of kernel reconstruction. We took that data and then reconstructed the kernel of that Gaussian process in black using the spectral mixture, and the truth is shown in green. And the learned spectral density is shown in black in the bottom figure, and you can see that there's a spike at about a frequency of a half corresponding to the sort of oscillations that we see roughly every 2 units. In this blue data, the sort of very noisy looking purple curve is the empirical spectral density estimate, which we derived last time by optimizing the marginal likelihood of a GP with a circulant kernel with respect to the kernel itself. This is that sinc function example. The truth is shown in green. This data set was actually created using a mixture of 3 sinc functions. If you're not familiar with sinc functions, it's just sine x over pi x, maybe sine pi x over pi x, for example. The only other time I'd ever actually seen this function was in high school calculus when they were showing examples of L'Hopital's rule. But I've used it again here. It's come back. And the truth is reconstructed with the spectrum mixture kernel in the dashed black curve. And it's almost an exact reconstruction, which is perhaps even a little bit worrying. Is this overfitting? You can test that a bit by looking at the test likelihood of the predictions rather than just say the mean squared error of the predictions, and the test likelihood is actually quite good, as we'll see. What the spectral mixture model has done, though, to make predictions on this data is quite interesting. This is actually a non-stationary pattern. It could be a stationary pattern in principle, but I created by mixture of 3 sinc functions, one at -10, one at 0, and one at 10, so it's non-stationary. But it's embedded it into a larger stationary pattern. And this is something we can always do. We can just keep repeating sinc functions every 10 units, turn a non-stationary data set into something that looks stationary. And this is something perhaps a human would do if they were forced to extrapolate and you said, what's going on at x equals 100, I would guess a person would probably draw something that looks a bit like a sinc function. So, in that sense, maybe they're sharing an inductive bias with this model. And we can see that that's happened when we look at the learned covariance function. A correlation function is just a scaled covariance function, scaled by the signal variance or amplitude parameter that we have. And the learned spectral density, again, is shown in the right in black, and the spectral density learned from a Gaussian or an RBF kernel is shown in red. And we can also do the same thing on the airline data set, predictions using a GPU with the spectral mixture kernel in black, the confidence or credible set shown in gray shade, 95% of the predictive mass. The empirical spectral density in this case looks a little bit more interesting. We do see peaks that correspond to the learned spectral density of the spectral mixture kernel. It's just a bit more noisy. And it's kind of nice. We can see this sort of correspondence, and maybe this even suggests that we could use the empirical spectral density to initialize our model. So in case you've forgotten, the empirical spectral density is just equal to the Fourier transform of the data, the absolute value of that squared, divided by the number of data points that we have. And we're looking at log spectral densities in this case. And this is just a table of results where you can see that the model is making good predictions in terms of log likelihood and mean squared error. So log likelihood is often a good check to see if we're overfitting. If we're doing it on the test set.
If you try to predict a car function or some function with jumps, will you get the aliasing effect just like you would do with Fourier function?
Can you repeat the question? If you had a function with jumps?
If you have a Haar function and you want to approximate the Haar function with or any functions like
some kind of step function, okay.
Yeah. Do you get an aliasing effect because your kernel looks has a periodic structure?
I think if you just saw like a single sort of step, then it might not model that with a periodic component. I'm not sure. But you do see aliasing in this model unless you control for it. So we saw aliasing in the CO2 example where we had a spike in the spectral density past a frequency of 1, even though the data were recorded monthly. And so that doesn't really make sense. And what happens is it'll just get aliased back. So suppose it's at 1.2, it'll get aliased back to a frequency of 0.2. You can, obviously, in the optimization procedure, you can control for that and just say, okay, well, there's something called the Nyquist frequency. And if you have regularly sampled data, which is just equal to half the sampling rate of data, and if we ever learn a frequency greater than that, or just penalize anything that sort of learns a frequency greater than that so that you're constrained within, let's say, a frequency of 0 to the Nyquist frequency. So I guess the thing is, like, if you have input intervals that are 1 unit apart, you can start using really high frequency functions and make exactly the same predictions as the low frequency functions. And just for the audience, that's what aliasing means. Did that answer the question? So I said earlier that flexible models are going to be most useful on large data sets. So it's very desirable to try and scale up this spectral mixture model. And in order to do that, we might have to do different things than we would do if we were just scaling up a standard Gaussian process model. One very promising approach is just to look at the existing structure in the model and try and use that to make sometimes even exact predictions without any additional simplifying assumptions. And a general purpose method for doing that is to try to decompose the covariance matrix into a Kronecker product of smaller matrices. So recall that the bottleneck the computational and bottleneck in Gaussian process inference and learning is having to compute k inverse y, where k is an n by n covariance matrix, and y is an n by 1 vector of observations. And to do kernel learning with the marginal likelihood, we also need to evaluate log determinant k in addition to this k inverse y term. So if the kernel decomposes as a product of kernels operating across each input dimension separately, so xi and xj could be multi-dimensional inputs. They could be spatial locations, for example. X could represent a latitude and a longitude, so it's a vector. And if the kernel does have this property, an RBF kernel, for example, has this property because we can write a multivariate Gaussian for the RBF kernel as a product of univariate Gaussians. And our inputs are on a multidimensional grid as defined in this equation here, where these variables are just our inputs for each separate dimension. And so this basically means, to give a concrete example, if we were considering spatial statistics, for every latitude in our grid, we'd also have a longitude. Then K will decompose as a Kronecker product of matrices operating over each input dimension separately. So if we're just considering a two-dimensional example, suppose we have an image, basically, which would generally satisfy these requirements, and it's 1,000 by 1,000 pixels. In that case, our covariance matrix, which is built up by evaluating our kernel at every pair of inputs, would be 10 to the 6 by 10 to the 6 entries. We can write that as this Kronecker product of two other covariance matrices. This is the covariance matrix built up using, for example, the RBF kernel operating on just the inputs from the first input dimension, so moving, for example, across the horizontal of the image. And that will just be 10 to the 3 by 10 to the 3. And this is the covariance matrix built up operating on the second input dimension. And to get the eigendecomposition of K into an orthogonal matrix of eigenvectors times the diagonal matrix of eigenvalues, transpose of this Q matrix, we can just take the eigendecomposition of K1 and K2. And so that's extremely powerful. Essentially, this eigendecomposition allows us to evaluate K inverse Y and log determinant K. And so we essentially reduce the problem from one with 1,000,000 data points down to a problem with 1,000 data points from a computational perspective. And we can make exact predictions, exactly the same predictions as we would make if we were to actually do the Cholesky decomposition on a 1,000,000 by 1,000,000 matrix, which is obviously impossible. Normally we'd be limited to probably 1,000 by 10,000 by 10,000 matrix or something like that on sort of a personal computer. So if we were just to write out this sort of calculation of interest in doing inference and predictions, we can re-express it in terms of these matrices Q, V, and Q transpose. So if we have Q, V, and Q transpose, that computation is actually quite trivial, and the log determinant of a matrix will just be a sum of log eigenvalues. Now, suppose we actually don't have a full grid. Like suppose we're considering land surface temperatures and there's ocean and that's creating a lot of missing inputs. Or we could just have missing data, or we could have an image and there could be a large missing region. So suppose we even have like 90% missing inputs, but we still want to exploit this bit of grid structure to make our predictions a lot more efficient and scalable. How would we try and do that? One way to do that is to use imaginary points to complete the grid, and then just put infinite noise on those points so that they don't interfere with our inference and predictions. An issue with that approach, initially, is that the relevant matrices that we're looking at don't actually have this Kronecker structure anymore. You can show, though, that by adding infinite noise for these imaginary observations, the predictive moments won't be affected. So suppose we have m training points, and then after augmentation, we have our n total points, and we have w imaginary points. this procedure won't have any corrupting effect on inference. And we can use an iterative method, actually, to solve for this equation of interest, Kn plus Dn inverse y, where Dn is just a diagonal matrix which represents our noise model. The first part of it will just be our normal noise variance, and the rest of it will just have these sort of infinite entries. And Kn is Kronecker, and Dn is just a diagonal matrix. We can use a preconditioning matrix which ignores these imaginary points in following this iterative procedure. And then we can scale things up again. And we can similarly compute the log eigenvalues that we're interested in. So the spectrum mixture kernel in the form that we derived actually doesn't decompose as a product across input dimensions, but we can always create a kernel that behaves a bit like the spectrum mixture kernel that does, just by taking a one-dimensional spectrum mixture kernel and then taking a product across input dimensions to create a spectrum mixture product kernel that operates on multi-dimensional inputs. Each spectrum mixture kernel in this product will have its own hyperparameters that we want to learn, which are denoted by theta p. We're imagining we have capital P input dimensions and little p. Each hyperparameter here is indexed by little p in this product. So to be very concrete, if we had an image, for example, and we're trying to do regression on this image, there would be two spatial input dimensions corresponding to pixel locations, and the observations would be one-dimensional, and they would be pixel intensities. So suppose we use this very basic regression model with the spectrum mixture kernel. We learn the hyperparameters, for example, running BFGS on the log marginal likelihood. We make predictions by looking at this predictive distribution condition on these learned hyperparameters, and we exploit the Kronecker structure of the spectrum mixture product kernel to scale up our inference and learning procedures. Now, this first set of results is mostly to try and separately understand the effects of the model specification and the scalable inference that we're using. So the first image, the training data, is just this. So we have this tread plate pattern, basically, this texture, and the black shows missing data. And we want to recover this testing region, which is shown in panel B. And the full data set is shown in panel C. And actually, we'll make predictions on the training region, too, because it tells us interesting things about our model. So panel D shows the recovery of this texture using this model that we've defined, and I'm just calling GPAT now. Panel E shows the predictions of using another scalable model for kernel learning called SSGP that happens to be parametric versus non-parametric. So the GPAT model is non-parametric in the sense that the kernel is derived from an infinite basis function expansion. Panel C uses the spectrum mixture product kernel, but with a very popular inducing input approach to scalability. So same model, different scalable inference algorithm as panel D. And panels G, H, and I use Gaussian processes with popular kernels. The SE kernel is just the RBF kernel, and the scalable Kronecker inference that we used in panel D. So notice that in panel E, the model has actually picked up some interesting structure. It picked up a diagonal pattern, but without the non-parametric representation, it appears hard to capture all of the information in the training set. Panel F isn't really able to discover anything interesting. We used as many inducing points as we really could and still run this on a computer. But you can imagine if you were looking at a texture and you could only see some small subset of pixels, you probably couldn't extrapolate a very interesting pattern, and that's basically what's happened here. Panels G, H, and I are interesting because even though the extrapolations are all the same and are very incorrect, the training region is actually represented perfectly, unlike in panels E and F. And this is from the non-parametric representation. So the information capacity of the model is quite large, but it's still a smoothing model, so it's not able to make these extrapolations. Now, this is another example. It's a little bit more challenging, and it helps us further understand the behavior of these algorithms. So NIPS is one of our favorite conferences in machine learning. And this provides a bit of extrapolation, a bit of interpolation, and, some mixtures, and we have some artifacts in the data set, some straight lines. And we can see GPAP is able to recover the texture. We've also added lighting artifacts and all sorts of other things to try and make the problem a little bit more challenging. And a GPU with a map-hearing kernel and the scalable counter inference is actually able to remove a lot of these artifacts fairly nicely. So you can imagine that a GPU with a smoothing kernel and counter inference might be good for image denoising. And it's possible that something like that has been done. I think it would be very, very good. It probably has been done. But the black box there isn't extrapolated very nicely. You can see a lot of smearing where there are larger missing regions. And we can see the same kind of thing happening in the bottom row there. So you might be wondering how we choose how many components we have in the spectral. But yeah.
Oh, two slides ago, is it in
2 slides or?
Yeah, in the last 3 GPs, is it in the middle predicting the mean to training data? Gray square?
Sorry?
Is it predicting the mean of the training data in this gray square?
So the predictions are from the predictive mean of the Gaussian process using under these different kernels.
So the gray square that it is predicting is also the mean of
That's the predictive mean of the Gaussian processes. So all the predictions are using the predictive mean. Good question. So thinking about this more, I think there is actually an interesting TPAMI paper by Alad and John and some others on using smoothing kernels for things like image denoising with Kronecker methods. Now, imagine we have lots of components in our model. And we're not sure if we actually need that many components or whether we actually might even need more components. So the question is how do we know how many mixtures to use in this Gaussian mixture representation of the spectral density? So if we use too many, a lot of these components won't be useful for explaining the data. And the log determinant complexity penalty will try to shrink them to 0 because having non-zero weights in the model in this mixture will increase the eigenvalues of this covariance matrix K. So if the extra flexibility isn't helping the model fit term of the marginal likelihood, it will shrink away to 0. And you can see that this is happening. So as a proxy for model selection, we do marginal likelihood optimization. So we have 2 input dimensions in this case, and on the left are the parameters for the first input dimension, and on the right are the parameters for the second input dimension. I'm just showing the weights and the frequencies. There's also these bandwidth parameters. You can see many of them are trained to 0. If you see this happening, though, you probably should try running the model again with fewer components. But it's nice that you can get a sense of model specification through the marginal likelihood. Of course, we could also try and do inference over the number of components using something like reversible jump MCMC, but that might be computationally expensive and not worth it, especially since we have this nice proxy for model selection and the marginal likelihood. This just shows us all the panels together. So we ran this model on all sorts of different textures. I've shown some of them here. And got very good results in every case. We did speed and accuracy stress tests. So on the left is a log-log plot of the runtime that it takes to evaluate a marginal likelihood for a particular model and any relevant derivatives. So if you have lots of components in the model, you'll need more derivatives and therefore a bit more runtime. In the black, we see the scaling of a Gaussian process with an RBF kernel and using the Cholesky decomposition. And so the slope of that curve is roughly 3, which is right because it should be cubic scaling. All the other curves roughly have a linear slope, which is roughly indicating some kind of linear asymptotic scaling with the number of data points. However, with these inducing input approaches, like FITSI with the spectral mixture kernel, you probably actually would want more inducing points with more data points. So we use the same number of inducing points for all the training sets here, which might actually make us think that the model is a bit faster than it would be in practice if you were using it appropriately. SMP25 in this case is 25 mixture components, for example. So it's kind of cool that we actually use GPAT 100, which has 100 mixture components. It actually means 601 kernel hyperparameters in this case. And it's actually running really, really quickly. We can actually run this model sometimes on data sets with hundreds of thousands of points, make exact predictions, and it all happens in under maybe 5 minutes. Which from a GP perspective is quite exciting. On the right, we have an accuracy stress test. Basically, what we've done is we've taken that metal tread plate pattern, we just keep increasing the hole in the center to test how far the model can extrapolate given limited information. We can see that once we have about 60% missing data in the center, the performance of this GPAT model becomes roughly equivalent to the performance of these other models. For comparison, the hole that we saw in a few slides ago shows 25% missing data. We can also do image inpainting. So here we basically see this texture, which is obscured by this apple stain. And we want to create a mask and then extrapolate the missing region. So we basically break everything apart into the red, blue, and green channels and extrapolate them separately and then bring it all together at the end. This pattern has shadows and irregularities, and it's quite convincingly reconstructed by this model. And I think it's worth pointing out that this model isn't a specialized inpainting algorithm. It's a regression algorithm, basically. And it's just got a very flexible kernel, and it's learning a lot of correlations through this kernel to be able to perform tasks like this, which are normally performed by very, very specialized models. For example, the most popular models in computer vision for inpainting are patch-based models. And essentially, they work by taking a pixel or a group of pixels on the outer edge of the patch, and then finding another group of pixels in the image such that the neighborhoods are very similar, and then copying those pixels in. We also ran this on this rooftop example, again, quite a famous example. For image inpainting, you want to get rid of the rooftop just to draw the bay. You can't see it in the image, but it actually is able to reconstruct subtle features like for example, waves in the water. There's a lot of non-stationarity in this image. You can also notice there's a huge amount of missing data. This is a paper by Hayes and Efros, where they actually use a large batch of images, thousands or maybe even 10,000 images, to try and do this extrapolation. And it's funny because boats were actually placed in the water once it did the extrapolation. And this really emphasizes that the objectives of these algorithms are quite different as well. A lot of image inpainting algorithms are evaluated by human perceptual comparisons, trying to make it look good to a person, whereas this model is trying to basically optimize some kind of principled loss function, the GPAT. And sometimes these objectives are even at cross purposes, because we could never actually predict from this image anyway that there are boats in the water. And even if we thought there were boats in the water, we couldn't predict what they'd be, like motor boats or sailboats, and what orientations they'd be in and where they'd be in the water. Of course, this other algorithm saw boats in coast on other sort of similar looking images, but still we wouldn't be able to predict the details of those boats. This is just another sanity check, where we've now constructed a three-dimensional data set using out-of-class kernels and tried to reconstruct what the true kernels are using this GPAT model, and we're able to reconstruct the truth quite accurately, even though these kernels look quite sophisticated, quasi-periodic, and heavy-tailed, for example. And this is actually a video, so we basically, this is sort of like some kind of texture that's evolving with time, so we can treat two of the input dimensions as x's, and the other dimension is as time. And the idea basically is you have some video and you have some large sequence of missing frames, and you want to extrapolate all of those frames rather than, for example, doing one step ahead predictions, or just looking at some kind of missing patch of one frame individually, in which case you would use an inpainting approach. Now, when I describe those patch-based methods, you could probably tell immediately that they would only apply to things like spatial correlations. You wouldn't be able to easily extend those models to things like video extrapolation. Of course, they do have models for video textures and so on, but again, that requires a lot of work, and often they're fairly specialized to those situations. This kernel is automatically learning these spatial and temporal correlations. It's making very few assumptions about the data set itself. This data set has a lot of data points. for a Gaussian process, and the training time was very fast. In fact, if you have a data set that meets roughly this grid assumption that we have, and it's higher dimensional, like 4 or 5 dimensional, then the algorithm will be really, really fast because it's sort of operating on each input dimension separately. Early on, we said if we had an image, a 2-dimensional example, we can sort of bring it down from 10 to the 6 data points to 10 to the 3 data points. Well, if you imagine we had another matrix here and we had sort of 10 cube by 10 cube for each of these, it's sort of like bringing 1 billion data points down to 1,000 data points, for example. And this example is also to emphasize the generality of the model. We don't necessarily need to apply it to computer vision problems. Suppose we have, for instance, we have land surface temperatures. There's a lot of missing data, and we want to predict what the land surface temperatures will be far into the future. So this is a fairly standard, I think, spatial statistics problem, and conventionally you would try and handcraft a combination of kernels to model this problem. What we did in this example is to take the first 9 years of data and then try to predict a whole year ahead. The picture shows the last 12 months of training data and the forecast made using an RBF kernel. So we can see that it eventually just goes back to this prior mean. It's not making very sensible extrapolations. In this figure, we show the forecasts using this model GPAT again. And again, it's quite a few data points, and the training time is quite fast, and there's quite a lot of missing data, and we can make these kinds of convincing extrapolations. Perhaps even more interestingly, we can learn very rich kernels on this real data and try to interpret those kernels to really understand the data that we're modeling. So before it, we handcrafted a combination of kernels. We are, again, doing all the interesting pattern discovery, whereas here the kernel is learned and we can sort of interpret the patterns that are discovered by the model. And the model will be more and more successful at doing that, often the more and more data we have. So, for example, the learned correlations for the y dimension here in the middle panel on the top have heavy tails, they're quasi-periodic. The correlations of time are, again, quasi-periodic and heavy tails. And these correlations are quite interesting in their own right. So to summarize what we found with GPAT, we basically tried to separately understand the effects of using different kernels, different inference and learning algorithms, parametric versus non-parametric representations. We found that a fully non-parametric representation, which is given by this spectral mixture kernel, meaning that this kernel corresponds to a linear basis function model with an infinite number of basis functions, was a very useful ingredient when it was combined with the scalable inference that exploited existing model structure, and when we used these highly expressive kernels. A lot of these applications were previously inaccessible, and it'll be interesting to try and brainstorm what kinds of applications we can apply these models to. Of course, we could keep building more and more expressive kernels. We could try to incorporate these sorts of models into a neural network-like architecture. So we have the kind of depth that we have in deep learning models to learn even richer representations of the data. And we'll talk about that a little bit more. But again, what I've been doing is it uses the marginal likelihood, but it's not fully Bayesian. And we can imagine actually wanting a distribution over kernels in the same way we have a distribution over functions with the Gaussian process. So before, we were sort of drawing functions from this Gaussian process and then inferring a posterior. But couldn't we also imagine sort of drawing kernels from some kind of stochastic process and inferring posterior over those kernels? And this would be nice because we're representing uncertainty over these kernels, and we can sort of have a whole posterior distribution over kernels, and we can sort of figure out what the support of these models are and what the inductive bias might be. So one way of inducing a distribution over kernels is simply just to place distributions over the parameters, for example, of the spectral mixture kernel. And we can sample from this prior on the left. So on the left, basically, I've shown sample functions from this process prior over kernels using the blue, black, red, and pink curves. The green function shows the sample mean kernel, and the gray shade shows 2 standard deviations about that sample mean. On the right, I've color-coded everything in the same way. I basically conditioned on each of these kernels and sampled from the corresponding Gaussian processes. And this is quite exciting because we can see a lot of variety in the behavior of these functions. We can see this sort of quasi-periodicity, smoothness in parts, multi-scale behavior. There's really a rich sort of library of structures that's been encoded by this distribution over kernels. And the goal is to observe some data and then look at the posterior over the kernel. Now, suppose we want to extend this model to non-stationarity. So we spent a lot of time thinking about stationary kernels, and for good reason. It's a very useful inductive bias, but also often we would want to have, there are at least times where we certainly want to have a non-stationary model as well. So how can we build a non-stationary model but still extract information from the data? If stationarity is a good inductive bias, this process construction over stationary kernels provides a nice clue. We could somehow have support for all sorts of non-stationary kernels, but concentrate that support on stationarity so that the model can extract structure from a lot of different data sets. It can be used sort of as a black box, but if there is obvious non-stationary in the data, it can still respond to that non-stationarity. Now, we looked at various ways of constructing non-stationary kernels in the last lecture. And one of those techniques was amplitude modulation. So the spectral mixture kernel is basically a sum of these sort of base kernels that we derive. We can imagine, for example, that that sum is actually input varying. So if we take a slice through any sort of particular time, we have a different spectral mixture model. And we know that these spectral mixture models with enough components can converge to any stationary kernel. So if we're having that kind of model actually adapt with the inputs, we can develop a very, very flexible model over non-stationary kernels as well. And so here I've basically just taken an amplitude modulator and drawn from samples samples from this non-stationary process. And you can see that now the behavior of these functions certainly is not invariant to translations in the input space. Here I've actually just depicted these covariance matrices that I used to sample these functions just on the previous slide. So again, you can see this kind of non-stationary behavior compared to the squared exponential or the RBF kernel in the bottom right. This is just for one input dimension. This is just a summary of spectral mixture kernels. And again, I'll provide the slides, so there'll be lots of opportunity to look at all the references. I'll now move on to another few exciting recent models for very scalable kernel learning and inference with kernel machines. So we've appealed to Bogner's theorem quite a lot in this talk. Again, it specifies a deterministic relationship between stationary kernels and spectral densities. Imagine we want to approximate the integral in equation 174. We could do that by actually treating the spectral density as a probability distribution and then sampling from that density function. So if we did that, we'd get basically a simple Monte Carlo sum. So I'm not sure if you guys are familiar with the idea of simple Monte Carlo. But basically, if we have some kind of integral, we can treat this as the expectation of f under the probability distribution p, and this is going to be approximately equal to where xi is drawn from p of x. So the expected value of this sum is going to be this integral, and the variance of this estimator will decrease as 1 over j. So we can use the same trick to try to approximate the integral in equation 174. Now, if we just directly sample from the spectral density, we'll end up with some kind of imaginary kernel. So we can use a trick that it's a valid Monte Carlo procedure to actually sample pairs, Sj and minus Sj from the spectral density. And when we do that, we recover this expression in equation 177. It's then interesting to note this is exactly the same kernel we get if we use a linear basis function model with trigonometric basis functions, so Fourier basis. And this result basically provides a theoretical justification that with enough basis functions, we could converge to any integral, or sorry, any stationary kernel, because we know that this sum will actually converge to the integral eventually. We could actually interpret this model slightly differently by instead saying, suppose we want to model the spectral density as a bunch of point masses. Then again, the integral would have this result that we see in equation 177, and the locations of the point masses, the delta functions, will be given by the samples here. So basically, the samples define point masses in the spectrum. More generally, this provides a way of constructing a basis function expansion efficiently. This is described in random kitchen instincts and also in SSGP. So the general procedure is to compute this empirical feature map, for example, if we're trying to approximate a Gaussian kernel. So we said we had to sample from this density function. If we take the Fourier transform of an RBF kernel, then we get a Gaussian density. So if we're trying to approximate basically a GP or kernel machine with an RBF kernel, then we're going to be wanting to sample from a Gaussian density function. If we want to sample from a different kernel, like or we want to approximate a different kernel, like a Mathieu kernel, then we can sample from a T distribution, because that's what we get when we Fourier transform a Mathieu kernel. The idea is choose the kernel you want to approximate, sample from the corresponding spectral density to create a finite basis function expansion. And when we do that, we can perform inference very efficiently and hope that the basis function expansion can approximate the non-parametric kernel as well. So the insight behind fast food is that sampling from this Gaussian matrix, Z, can be approximated very well for this purpose using Hadamard matrices. And we can reduce computing the feature map, which is really the cost of interest here, from O n log d, time and O n storage, from O n storage, from ND storage to order n storage and ND operations to n log d operations, where d is the input dimensionalities and n is the number of basis functions. So that's equal to j in the example that we gave previously. And this is the whole fast food procedure written out and all of the necessary components. This is a slide from Alex Smola, and it basically shows a couple interesting things. First of all, if we use the exact, for example, RBF kernel, we get pretty much the same performance as if we use either a random kitchen sinks or a fast food basis function expansion. So both of these approaches are approximating this RBF kernel very, very well. And additionally, the fast food approximation is just as good as the random kitchen sinks approximation, but can be significantly more efficient. Another thing that was pointed out in this paper that was quite interesting is that on the data set with lots of input dimensions, the approximation to the Mathieu kernel had much better performance than the approximation to the RBF kernel, and they talk about this concentration and measure effect. So this is kind of an open question in kernel methods. How do we model, how do we choose a good kernel when we have a really high dimensional input space? And this is something that isn't answered by GPAT, for example. The issue is the Euclidean distance measure often breaks down when we are looking at really high dimensional input spaces. And these kinds of situations are especially relevant, for example, in classification settings. So it'd be really nice to have a kernel that works well in high input dimensions, and there's some insight into why the math theorem kernel works better than the Gaussian kernel in high input dimensions. So far we basically assumed that we know what kernel we want to use, and then we derive a way of approximating that kernel with a finite basis function expansion. The purpose of doing that is for efficiency. So if we have fewer basis functions than we have data points, this will be much more efficient than just using the standard dual space representation. So basically we approximate the kernel and go back from the kernel representation back into the basis function representation. But we can also use this as a way of doing kernel learning. So before I said we sample the points from the spectral density. Well, I also said that those points correspond to point masses at different locations determined by the sampling procedure. So couldn't those point masses actually end up being hyperparameters in our marginal likelihood in the basis function representation? And can we just optimize with respect to those frequencies? And the answer is yes, but you can overfit doing that, because sometimes you'd have as many frequencies as you have. Well, you would have as many frequencies as you have basis functions. And you can imagine that the likelihood surface might be very multimodal as well. So you can actually harmonize fast food with this spectral mixture approach as well. And imagine that instead, your spectral density is modeled by a scale location mixture of Gaussians, and this is what you're sampling from. You could do the sampling part if you want to have a decent initialization, and then you can sort of fine-tune the few hyperparameters that you're left with, which would be sort of the locations of these mixtures and the width of these mixtures. So instead of controlling all the spectral points individually, you're just controlling groups of these spectral points, and we're sort of harmonizing both the spectral mixture model and this fast food model for something that's very efficient and very general purpose, doesn't make assumptions about the locations of the input points. For instance, and can be used for quite flexible kernel learning. So at this stage, I'm just asking, are there any questions? Is there anything that you think would be worth going over in a bit more detail?
You have been showing this in spectral density class. You were showing the 1D example, right?
Yes.
Do you need an assumption that the interaction terms between different random variables have small modes unimportant?
The interaction terms between different random variables are important?
Yeah, is it like your input variables are independent of each other?
So for the scaling up in the Kronecker approach, we assumed that we had our kernel composed as a product across input dimensions. So this still allows us to have a rich model of correlations across the inputs. It sort of corresponds to a soft prior assumption of independence. A very much more restrictive assumption, and this is actually used quite often, and it's different, is saying instead of the kernel being a product across input dimensions, it's actually a sum of kernels acting on each input dimension separately. And those are called additive kernels or additive Gaussian processes. Sometimes you might have a more rich model. So I mentioned input dimensionality is actually an issue. Sometimes if the input dimensionality is very, very high, and that's because, for example, the Euclidean distance measure sometimes isn't very good for high-dimensional inputs. One potential solution to this problem is to say, imagine we have our persistent covariance matrix is just a kernel. We can say that that's equal to a kernel operating on input dimensions, d1 up to d5 times for xi, xj, plus another kernel operating on d6 and d7, plus another kernel which maybe operates on all the input dimensions, and that can be a fairly rich model, and it helps us sort of obviate this problem that we have with high-dimensional inputs. But if you were just to have a kernel that was operating as a sum across each individual input dimension, that would be extremely restrictive, and you wouldn't get a model that performs very well at all in general. So we can see evidence that this product assumption is less restrictive. I mean, it's something that's encoded in the Gaussian kernel, for example. In this pattern, for example, because there are sort of diagonal correlations across the two input dimensions in this case, and that's picked up fairly well by the model. So it's just sort of a soft prior assumption that could even be sort of a nice inductive bias. There have been examples. So the RBF kernel looks like I just like erasing. I don't like changing Blackboard. Just looks like but instead, I've seen this term replaced with something that looks more like an inner product of xi and xj with respect to some kind of covariance matrix, basically, which captures a lot of correlations across the different dimensions. I think there's a paper by Chris Williams and others in the late 90s called something like Gaussian process feature detection that uses something like this. The issue is when you have a covariance matrix like that, you end up with a lot of hyperparameters to learn, and sometimes they can be quite difficult to learn. So if you have like a 100 by 100 covariance matrix, you might end up with a lot of parameters there to learn, and it can be quite a challenging problem. Although in other sort of machine learning contexts, often we talk about learning 100,000 parameters, but in sort of a Gaussian process or a kernel context, even 5 hyperparameters is maybe a little bit more than normal. So we talked up to sort of 601 hyperparameters, but 1,000 hyperparameters could be kind of a big deal, depending on the exact situation. Another approach, so if we're just sort of brainstorming about what kind of kernels we could create that might be good for high input dimensions, we could imagine doing some kind of projection of the data set. So our projection of the input, so we could take our KRBF, and so it's basically operating on xi, xj, some pair of inputs, and we could transform that so that it's acting on some kind of projection of the inputs. And basically, W again would be treated as sort of a matrix of hyperparameters. Like this was already dependent on L, so one of our theta hyperparameters. So W will just basically fall out into the marginal likelihood again, and this is something we could optimize, and we could probably think of a smart way to initialize this matrix as well. And so this is actually probably, even though it's very simple, probably a very good idea. If you had a high-dimensional input space, this would be like a factor model where you have some kind of P by Q or Q by P. Something like that. So you're just projecting the inputs into some lower dimensional space. We could probably think of all sorts of fun things to do with this. You could imagine even trying to do some kind of like neural network transformation of the inputs and trying to learn the parameters of that transformation through marginal likelihood optimization. And this would be another way of doing kernel learning, actually. Because if you can transform the input space, then you can, and then apply an RBF kernel in the transform space, then you can actually learn a lot of interesting structure. I think the reason that isn't often that is because it can be a very difficult optimization problem. Yeah, so this sort of approach could be turned into kind of a flexible kernel learning approach. Another way, as we said, was to develop sort of interesting covariance functions is to think even in a multitask setting. So if we consider a neural network, for example, we have our input layer, which is our vector x. It's going out to our hidden units. And these are connected to our outputs. So you can have y1 of x to p of x. This would be f1 of x up to fq of x. And basically, we have some kind of matrix of weights that's bringing us from this layer over to this layer. So this is really a multitask model, and I haven't talked much about multitask Gaussian processes, and it's kind of interesting that we don't really consider multi-output models that much in a kernel machine setting, even though actually they are quite natural. I think it's just an artifact of it sometimes being a little bit harder to do than it would be in a neural network setting. So often we're not doing a regression from Rm to R1. Quite often we actually want to do regression from Rm to Rj, where j is greater than 1. And we don't want to just assume that all the outputs are independent, because typically someone will just treat that as, say, j separate regression problems, and quite often that's not the right thing to do. So it's worth thinking about how we want to actually induce correlations across the different output variables. So a very trivial way to do that is simply to say, okay, well, if we want to use a Gaussian process model, we could write our outputs as some kind of p-dimensional vector. This is just p by 1. And we have some kind of matrix here, which is p by q. So it could be some kind of factor representation. And then we have a q by 1 vector. Each entry is a separate Gaussian process. And so that basically corresponds to each of these nodes in this network structure as being a Gaussian, as an independent Gaussian process. And now we have correlations because each output actually shares hidden basis functions. And so this would be a first step towards building a multitask Gaussian process. And this is called the semi-parametric latent factor model, actually. You can actually work out, in this case, that each of these outputs would be a different Gaussian process. And the kernel of these Gaussian processes would be equal to a sum of the kernels used in these Gaussian processes. Incidentally, neural networks have also been used in a very different context for kernel learning. There's a paper by Ruslan Salakutinov and Jeff Hinton, where I don't know if I remember exactly what they did, but it was possibly along something like along the lines of something like using like an autoencoder, a deep autoencoder, to learn a new representation of the inputs, and then applying, for example, an RBF kernel to that new feature space that was discovered by the network. And so it's a way of combining sort of two different worlds in machine learning. You can imagine also, we talked a little bit about what might happen if we were to make the weights in this mixture input dependent. Then we actually have a non-stationary kernel model, which is essentially what we did when we talked about building a non-stationary process over kernels earlier on. Basically, you can imagine that each of these GPs, for example, were different Gaussian processes, each with one component spectrum mixture models. So you get sort of a full spectrum mixture through the weight matrix, and then if you make that weight matrix input dependent, then you now have an adaptive mixture, spectrum mixture models. But this could also be quite flexible, even if you just had RBF kernels inside this this node vector here, because now you have an adaptive mixture of length scales, for example. You have an adaptive mixture of covariance structures, so it's a way of mixing different things together. I guess since we're on the topic, one other thing that perhaps isn't explored a lot, although a number of papers have been written about it, is heteroscedasticity with Gaussian processes. And there are a number of different ways we might want to approach heteroscedasticity. So heteroscedasticity often simply means we have input-dependent noise variances. So a concrete example of that would be, imagine we were measuring the position of a rocket as it leaves the Earth. The further away it gets, the more uncertain we are about its position. So we might have some kind of model, and instead of saying yx is Gaussian with mean f of x and some kind of constant variance, we actually make this dependent on x. And the question is, what would be a good model for this variance function? So if we were to just let f of x equal 0, for example, and we were to let sigma squared equal x squared, then if we were to sample this data, we would see that eventually it would get sort of very dispersed. The noise variance is increasing. But we can also imagine if we had a very flexible model both for f And for sigma squared, there could be a lot of degeneracy. How do we know what to explain as signal and what to explain as noise? And I think this is a good example of where we might want to, again, think about sort of things like inductive biases. So if we imagine, for instance, that actually our model is something like, we just write this out equivalently, we could write this as f of x plus, you could have some kind of sigma squared x epsilon. We could, where epsilon is just sort of a standard Gaussian variable, we could rewrite this so it's maybe f of x times g of x plus g of x epsilon, and we could let f and g both be Gaussian processes, for instance. And the reason we might want to do this, instead of just saying f and sigma squared are Gaussian processes or transform Gaussian processes to make them positive, is although we have the same amount of flexibility in this model and more degeneracy, we'd also have this nice bias that the magnitude of the signal and the magnitude of the noise generally will be encouraged to increase and decrease together, which is actually quite often a reasonable assumption, and it allows us to extract information, interesting information from our data set. So I've actually found in a more complicated setting where I'm considering what's called sort of multivariate heteroscedasticity, this can be very important. The model that sort of has a flexible representation for both the mean and the noise, or the multivariate mean and the multivariate noise covariances, tends to perform much more poorly than a model along these lines that actually shares between the mean and the variance, or the mean and the covariances. So does anyone have any other sort of general things they might be interested in brainstorming or discussing? So I mentioned that you would probably want to transform these Gaussian processes if you were to use them in something like this. So a Gaussian process applies probability mass to the whole real line. We know, for example, that a variance parameter has to be positive everywhere. So probably the basic thing someone would do in that case is just say that we'll model our variance function as an exponentiated Gaussian process where f is some kind of GP. But this sort of begs the question of whether we should then be assuming that our data is log normal distributed, which is the assumption in this model. It seems a little bit arbitrary. So we could do something even a little bit more sophisticated and just have some kind of flexible transformation that's parameterized, and then learn the parameters of that model through the marginal likelihood, for instance. And this would actually be, in a way, a type of density estimation. So we'd be doing density estimation on this latent variance function. And that's actually kind of cool because it's not necessarily as obvious how to do density estimation on some kind of latent variable like that as it would be on something that's observed. And it would be happening automatically through some kind of transformation like that. Often, though, I find that the Gaussian assumption, I mean, if there's an obvious case, like you have strictly positive data, yes, it's usually good to transform, but often I find that the Gaussian assumption of a Gaussian process isn't particularly limiting. The covariance kernel, for example, is going to be a lot more important in terms of trying to make really good predictions than, say, adjusting to get a particular distribution. But if you do see, for example, that your observations have a very skewed distribution, it's certainly worth, for example, taking a log transform before modeling it with the Gaussian process. You'll get better results. I mean, that's just a good rule of thumb anyway. We should always try and look at our data and see how we can pre-process it so that the data fit the assumptions of our model. For example, a zero mean function. That's certainly worth discussing as well. I mean, the mean function of a Gaussian process isn't really discussed that often, and it can be quite important. First of all, there is often degeneracy between the covariance function and the mean function, and this is part of the reason. But also, I've heard arguments that we should often only use parametric instead of non-parametric models, because the parametric models will generally correspond, for example, to some kind of well-motivated physical model for data. So we might be considering nuclear magnetic resonance, for example, and we have a good model of what's called free induction decay. It doesn't matter if you know exactly what that is, but it's well modeled by something that looks like a bunch of trigonometric functions with parameters that have physical interpretations. So I think someone in, for example, chemical engineering might be very opposed to saying, oh, let's just use a GP to model this, when they already have this very well-motivated physical idea of how to describe the data. Well, I don't think those models are really at cross purposes. Again, it comes down to sort of this supported inductive bias argument. You could always include that motivated physical model into a Gaussian process by making it the mean function of your Gaussian process. And then you'll have this distribution over functions, and you can concentrate the support of that distribution around this prior physical model however you would like. Or you could even learn how we want to sort of concentrate that support as part of our inference procedure. And the parameters of that physical model will drop out, again, into the marginal likelihood. And basically doing that reflects our belief that, even though this is a well-motivated physical model, it's almost certainly not entirely correct. And so we should, in principle, try to represent that uncertainty in some way. Other processes recently, like T processes, have been of interest in certain cases. So I think it's quite natural to ask, well, if you can have a Gaussian process, couldn't you define any kind of elliptical process in a similar way, any kind of distribution that's characterized by a covariance matrix could in principle be turned into some kind of process with properties controlled by a kernel? And that's true. It turns out that the predictive distributions of these processes end up being often quite similar to the predictive distribution we've got with the Gaussian process, or sometimes intractable, in which case it wouldn't be worth the effort. But there could be subtle differences, for example, between a Gaussian process and the T process that are orthogonal to the choice of the covariance kernel that we have. So, for example, if we say that F is a GP, and it has zero mean and some kind of parameter times k. Let's just say this is an RBF kernel parameterized by theta. And we put an inverse gamma prior on this parameter. We can actually integrate that parameter away analytically, given data, and use this as a way of deriving a T process, basically. So this is f of x conditioned on a, f of x, once you've integrated away, this parameter will have this T process distribution. And we can calculate the predictive equivalence of this distribution as well. And earlier on I said it was kind of strange that the observations didn't actually appear in our predictive variances or predictive covariances. In this case they would. And that's quite sensible because we basically integrated away conditioned on this scaling parameter A away conditioned on the data. And there are some sort of very subtle differences between these kinds of processes beyond the moments that we see here. For example, T distributions have this property called tail dependence that we don't see with Gaussian distributions. So one way of sampling a random variable is to take a sample from a uniform random variable and then transform it through the inverse CDF of the variable you're interested in. So suppose you want to sample, this would be a bad way of sampling a Gaussian random variable, but you could sample from a uniform generator and then pass it through an inverse Gaussian CDF, and you would get a sample from a Gaussian random variable. So this suggests a way of basically taking a distribution, let's just consider bivariate distributions, and then creating other types of distributions with marginal distributions that we're interested in. So suppose we sample from a Gaussian distribution, we'll see some kind of sort of elliptical sort of behavior. We have sort of our two variables, x1 and x2, and we have our bivariate Gaussian distribution over these variables, and these are the samples we get. And then we transform marginally all of these x2 variables with a Gaussian CDF. That will bring it, that will transform those those samples so that they'd be sampled from a uniform variable. And we can do the same with the other component. And then we end up with some kind of bivariate distribution that has uniform marginals. And then we can take that bivariate distribution and transform the marginals again so that we have bivariate distribution that's a t distribution, not a t distribution, it has t marginals, but isn't a t distribution. And we created that distribution by starting from a bivariate Gaussian distribution. And what's interesting to note is that even if this distribution that we started with, this Gaussian distribution, has the same rank correlation coefficient as the t distribution that we might be looking at, the bivariate t distribution, and that rank correlation coefficients are invariant to these kinds of transformations, the dependency structure you'll see is very different. Whatever you get when you follow this procedure will look very much different than samples from a bivariate t distribution. And one way they'll look different is the bivariate t distribution will have what we call tail dependence. So you'll see large values of one variable sort of strongly correlated with large values of the other variable. And this could be interesting in defining something like a T process, because that process will also have this tail dependence, and that's orthogonal to the choice of kernel that we're using. And you can imagine this might be useful, for example, in financial modeling. We talked very briefly last time as well also about working with Gaussian processes, and we have non-Gaussian likelihoods. So in a lot of the examples we considered today, we just assumed ID Gaussian noise. If we're doing classification, we can assume a different observation model. We can say that the probability of our class label given our Gaussian process is equal to the logistic sigma transformation of our Gaussian process. And then we can write down our likelihood from that expression, and we can try and compute our predicted distribution, our Gaussian process at a test input, given our vector of class labels, and that will just be equal to, I mean, it's a bit of algebra to get the exact conditional distributions, and it's something that's worth thinking about at home. This is just the standard Gaussian process predicted distribution, which is Gaussian, and this is the posterior over our Gaussian process functions conditioned on the training data. And if this distribution is Gaussian, then we don't have an analytic predicted distribution anymore. So a lot of effort has been placed in trying to approximate this distribution as a Gaussian distribution. There are, or by sampling from this distribution, basically, to be able to compute this integral. This model is obviously quite similar to a support vector machine, harder to work with in general because you have to do this sort of approximate integration. I would say the advantage of this probabilistic approach is if you have, for example, an interesting kernel and a lot of parameters, the resulting approximate marginal likelihood you get would provide a very natural way to try and learn those parameters. You can also imagine tons of other settings, though, where you wouldn't have analytic inference with the Gaussian process. For example, you might be modeling the rate function for integral spike train, which would be described by a Poisson process. And you might want to model that with the Gaussian process. And again, that's something you're going to want to be positive, so you could exponentiate a Gaussian process, for instance, and then just follow this sort of general way of doing approximate inference with Gaussian processes to try and figure out how to make predictions. And this is something that's actually been done quite a bit. And I actually saw a nice paper that did this where you just had sort of time series data, and it exploited Toeplet structure in the kernel to make really, really fast predictions. They were the same kind of predictions that you would make with a Cholesky decomposition. And that model was run on data sets up to maybe 100,000 points. It's quite a nice paper by John Cunningham. All right, that concludes this lecture. If you have any offline questions, definitely feel free to email me. The slides will be available. Also, a good introductory book on Gaussian processes is called Gaussian Processes for Machine Learning. It's by Carl Rasmussen and Chris Williams, and it's available free online. And there are also a lot of other resources. That book in particular has MATLAB code freely available, and in fact, the spectral mixture kernel has now been added to that package. So, and with some demos, including some of the demos we've shown in this talk, so you can just sort of press play on the MATLAB script and reproduce a lot of the results that we've seen in the talk so far. And if you're playing with that, if you have any questions, you can ask me, or if you have any queries about working with any of the other models we've discussed as well. Thank you.
All right. We like say a final goodbye. Okay, now that this is actually the last lecture, so you don't have to record this. It's fine. You're not, right? You're just not.
Well, don't record.
I would say don't record. Well, to those that are still here, stuck around to the very end, thank you for that. Hope you enjoyed the whole time. We are going to send out a survey tonight that will have some responses, and if you can respond to that, it would be much appreciated. We will also, I know we've been delinquent about touching out materials recently. We will put the materials up to the website.
It has a lot to do also with, speakers are humans. And, well, when was the last time you replied to all your emails within half an hour? And when was the last time you submitted a paper a week before the conference deadline? So keep that in mind when you look forward to the slides.
So they will come. They will be coming.
The video should be up by
videos
tomorrow.
Alex has been doing, so he's been much better at it. But anyway, again, thank you very much for coming. We've really enjoyed this. Hopefully you have too. Send us emails to follow up, and we really, really had a great time. Thank you.
The last brave speaker.
It's a hard gig being the last time you've sat there for 2 weeks.
This is an amazing amount of bravery. So thank you very much. Thank you. Okay, thanks online.
Bye everyone.
Bye. We have exactly 0 viewers left.